Section 1 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Lynn Thompson. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. The Translator's Preface. English writers who have spoken of Goethe's doctrine of colours have generally confined their remarks to those parts of the work in which he has undertaken to account for the colours of the prismatic spectrum and of refraction altogether, on principles different from the received theories of Newton. The less questionable merits of the treatise, consisting of a well-arranged mass of observations and experiments, many of which are important and interesting, have thus been in a great measure overlooked. The translator, aware of the opposition which the theoretical views alluded to have met with, intended at first to make a selection of such of the experiments as seem more directly applicable to the theory and practice of painting. Finding, however, that the alterations this would have involved would have been incompatible with a clear and connected view of the author's statements, he preferred giving the theory itself entire, reflecting, at the same time, that some scientific readers may be curious to hear the author speak for himself even on the points at issue. In reviewing the history and progress of his opinions and researches, Goethe tells us that he first submitted his views to the public in two short essays entitled Contributions to Optics. Among the circumstances which he supposes were unfavourable to him on that occasion, he mentions the choice of his title, observing that by a reference to optics he must have appeared to make pretensions to a knowledge of mathematics, a science with which he admits he was very imperfectly acquainted. Another cause to which he attributes the severe treatment he experienced was his having ventured so openly to question the truth of the established theory. But this last provocation could not be owing to mere inadvertence on his part. Indeed, the larger work, in which he alludes to these circumstances, is still more remarkable for the violence of his objections to the Newtonian doctrine. There can be no doubt, however, that much of the opposition Goethe met with was to be attributed to the manner as well as to the substance of his statements. Had he contented himself with merely detailing his experiments and showing their application to the laws of chromatic harmony, leaving it to others to reconcile them as they could with the pre-established system, or even to doubt in consequence the truth of some of the Newtonian conclusions, he would have enjoyed the credit he deserved for the accuracy and the utility of his investigations. As it was, the uncompromising expression of his convictions only exposed him to the resentment or silent neglect of a great portion of the scientific world, so that for a time he could not even obtain a fair hearing for the less objectionable or rather highly valuable communications contained in his book. A specimen of his manner of alluding to the Newtonian theory will be seen in the preface. It was quite natural that this spirit should call forth a somewhat vindictive feeling, and with it not a little uncandid as well as unsparing criticism. The doctrine of colours met with this reception in Germany long before it was noticed in England, where a milder and fairer treatment could hardly be expected, especially at a time when, owing perhaps to the limited intercourse with the Continent, German literature was far less popular than it is at present. This last fact, it is true, can be of little importance in the present instance, for although the change of opinion with regard to the genius of an enlightened nation must be acknowledged to be beneficial, it is to be hoped there is no fashion in science, and the translator begs to state once for all that in advocating the neglected merits of the doctrine of colours, he is far from undertaking to defend its imputed errors. Sufficient time has, however, now elapsed since the publication of this work, in 1810, to allow a calmer and more candid examination of its claims. In this more pleasing task, Germany has again for some time led the way, and many scientific investigators have followed up the hints and observations of Goethe with a due acknowledgment of the acuteness of his views. It may require more magnanimity in English scientific readers to do justice to the merits of one who was so open and, in many respects, it is believed, so mistaken an opponent of Newton. But it must be admitted that the statements of Goethe contain more useful principles in all that relates to harmony of colour than any that have been derived from the established doctrine. It is no derogation of the more important truths of the Newtonian theory to say that the views it contains seldom appear in a form calculated for direct application to the arts. The principle of contrast, so universally exhibited in nature, so apparent in the action and reaction of the eye itself, is scarcely hinted at. The equal pretensions of 7 colours as such, and the fanciful analogies which their assumed proportions could suggest, have rarely found favour with the votaries of taste. Indeed, they have long been abandoned even by scientific authorities. And here the translator stops. He is quite aware that the defects which make the Newtonian theory so little available for aesthetic application are far from invalidating its more important conclusions in the opinion of most scientific men. In carefully abstaining, therefore, from any comparison between the two theories in these latter respects, he may still be permitted to advocate the clearness and fulness of Goethe's experiments. The German philosopher reduces the colours to their origin and simplest elements. He sees and constantly bears in mind, and sometimes ably elucidates, the phenomena of contrast and gradation, 2 principles which may be said to make up the artist's world, and to constitute the chief elements of beauty. These hints occur mostly in what may be called the scientific part of the work. On the other hand, in the portion expressly devoted to the aesthetic application of the doctrine, the author seems to have made but an inadequate use of his own principles. In that part of the chapter on chemical colours which relates to the colours of plants and animals, the same genius and originality which are displayed in the essays on morphology, and which have secured to Goethe undisputed rank among the investigators of nature, are frequently apparent. But one of the most interesting features of Goethe's theory, although it cannot be a recommendation in a scientific point of view, is that it contains undoubtedly, with very great improvements, the general doctrine of the ancients and of the Italians at the revival of letters. The translator has endeavoured in some notes to point out the connection between the theory and the practice of the Italian painters. The Doctrine of Colours, as first published in 1810, consists of 2 volumes in 8vo and 16 plates with descriptions in 4to. It is divided into 3 parts, a didactic, a controversial, and an historical part. The present translation is confined to the first of these, with such extracts from the other 2 as seemed necessary, in fairness to the author, to explain some of his statements. The polemical and historical parts are frequently alluded to in the preface and elsewhere in the present work, but it has not been thought advisable to omit these allusions. No alterations whatever seem to have been made by Goethe in the didactic portion in later editions, but he subsequently wrote an additional chapter on entopic colours, expressing his wish that it might be inserted in the theory itself at a particular place which he points out. The form of this additional essay is, however, very different from that of the rest of the work, and the translator has therefore merely given some extracts from it in the appendix. The polemical portion has been more than once omitted in later editions. In the first 2 parts the author's statements are arranged numerically, in the style of Bacon's Natural History. This, we are told, was for the convenience of reference, but many passages are thus separately numbered which hardly seem to have required it. The same arrangement is, however, strictly followed in the translation to facilitate a comparison with the original where it may be desired. And here the translator observes that although he has sometimes permitted himself to make slight alterations in order to avoid unnecessary repetition, or to make the author's meaning clearer, he feels that an apology may rather be expected from him for having omitted so little. He was scrupulous on this point, having once determined to translate the whole treatise, partly, as before stated, from a wish to deal fairly with a controversial writer, and partly because many passages, not directly bearing on the scientific views, are still characteristic of Goethe. The observations which the translator has ventured to add are inserted in the appendix. These observations are chiefly confined to such of the author's opinions and conclusions as have direct reference to the arts. They seldom interfere with the scientific propositions, even where these have been considered most vulnerable. Preface to the first edition of 1810. It may naturally be asked whether, in proposing to treat of colours, light itself should not first engage our attention. To this we briefly and frankly answer, that since so much has already been said on the subject of light, it can hardly be desirable to multiply repetitions by again going over the same ground. Indeed, strictly speaking, it is useless to attempt to express the nature of a thing abstractedly. Effects we can perceive, and a complete history of those effects would, in fact, sufficiently define the nature of the thing itself. We should try in vain to describe a man's character, but let his acts be collected, and an idea of the character will be presented to us. The colours are acts of light, its active and passive modifications. Thus considered, we may expect from them some explanation respecting light itself. Colours and light, it is true, stand in the most intimate relation to each other, but we should think of both as belonging to nature as a whole, for it is nature as a whole which manifests itself by their means in an especial manner to the sense of sight. The completeness of nature displays itself to another sense in a similar way. Let the eye be closed, let the sense of hearing be excited, and from the lightest breath to the wildest din, from the simplest sound to the highest harmony, from the most vehement and impassioned cry to the gentlest word of reason, still it is nature that speaks and manifests her presence, her power, her pervading life, and the vastness of her relations, so that a blind man to whom the infinite visible is denied, can still comprehend an infinite vitality by means of another organ. And thus, as we descend the scale of being, nature speaks to other senses, to known, misunderstood, and unknown senses. So speaks she with herself and to us in 1,000 modes. To the attentive observer she is nowhere dead nor silent. She has even a secret agent in inflexible matter, in a metal, the smallest portions of which tell us what is passing in the entire mass. However manifold, complicated, and unintelligible this language may often seem to us, yet its elements remain ever the same. With light poise and counterpoise, nature oscillates within her prescribed limits, yet thus arise all the varieties and conditions of the phenomena which are presented to us in space and time. Infinitely various are the means by which we become acquainted with these general movements and tendencies. Now as a simple repulsion and attraction, now as an unsparkling and vanishing light, as undulation in the air, as commotion in matter, as oxidation and deoxidation, but always, uniting or separating, the great purpose is found to be to excite and promote existence in some form or other. The observers of nature finding, however, that this poise and counterpoise are respectively unequal in effect, have endeavoured to represent such a relation in terms. They have everywhere remarked and spoken of a greater and lesser principle, an action and resistance, a doing and suffering, an advancing and retiring, a violent and moderating power, and thus a symbolical language has arisen, which, from its close analogy, may be employed as equivalent to a direct and appropriate terminology. To apply these designations, this language of nature to the subject we have undertaken, to enrich and amplify this language by means of the theory of colours and the variety of their phenomena, and thus facilitate the communication of higher theoretical views, was the principal aim of the present treatise. The work itself is divided into 3 parts. The first contains the outline of a theory of colours. In this, the innumerable cases which present themselves to the observer are collected under certain leading phenomena, according to an arrangement which will be explained in the introduction. And here it may be remarked that although we have adhered throughout to experiment, and thoroughly considered it as our basis, yet the theoretical views which led to the arrangement alluded to could not but be stated. It is sometimes unreasonably required by persons who do not even themselves attend to such a condition, that experimental information should be submitted without any connecting theory to the reader or scholar, who is himself to form his conclusions as he may list. Surely the mere inspection of a subject can profit us but little. Every act of seeing leads to consideration, consideration to reflection, reflection to combination, and thus it may be said that in every attentive look on nature we already theorize. But in order to guard against the possible abuse of this abstract view, in order that the practical deductions we look to should be really useful, we should theorize without forgetting that we are doing so. We should theorize with mental self-possession, and, to use a bold word, with irony. In the second part we examine the Newtonian theory, a theory which by its ascendancy and consideration has hitherto impeded a free inquiry into the phenomena of colours. We combat that hypothesis, for although it is no longer found available, it still retains a traditional authority in the world. Its real relations to its subject will require to be plainly pointed out. The old errors must be cleared away, if the theory of colours is not still to remain in the rear of so many other better investigated departments of natural science. Since, however, this second part of our work may appear somewhat dry as regards its matter, and perhaps too vehement and excited in its manner, we may here be permitted to introduce a sort of allegory in a lighter style, as a prelude to that graver portion, and as some excuse for the earnestness alluded to. We compare the Newtonian theory of colours to an old castle, which was at first constructed by its architect with youthful precipitation. It was, however, gradually enlarged and equipped by him according to the exigencies of time and circumstances, and moreover was still further fortified and secured in consequence of feuds and hostile demonstrations. The same system was pursued by his successors and heirs. Their increased wants within, the harassing vigilance of their opponents without, and various accidents compelled them in some places to build near, in others in connection with the fabric, and thus to extend the original plan. It became necessary to connect all these incongruous parts and additions by the strangest galleries, halls, and passages. All damages, whether inflicted by the hand of the enemy or the power of time, were quickly made good. As occasion required, they deepened the moats, raised the walls, and took care there should be no lack of towers, battlements, and embrasures. This care and these exertions gave rise to a prejudice in favour of the great importance of the fortress, and still upheld that prejudice, although the arts of building and fortification were by this time very much advanced, and people had learned to construct much better dwellings and defences in other cases. But the old castle was chiefly held in honour because it had never been taken, because it had repulsed so many assaults, had baffled so many hostile operations, and had always preserved its virgin renown. This renown, this influence lasts even now. It occurs to no one that the old castle is become uninhabitable. Its great duration, its costly construction, are still constantly spoken of. Pilgrims wend their way to it. Hasty sketches of it are shown in all schools, and it is thus recommended to the reverence of susceptible youth. Meanwhile the building itself is already abandoned. Its only inmates are a few invalids, who in simple seriousness imagine that they are prepared for war. Thus there is no reason here respecting a tedious siege or a doubtful war. So far from it we find this eighth wonder of the world already nodding to its fall as a deserted piece of antiquity, and begin at once, without further ceremony, to dismantle it from gable and roof downwards, that the sun may at last shine into the old nest of rats and owls, and exhibit to the eye of the wondering traveller that labyrinthine incongruous style of building, with its scanty makeshift contrivances, the result of accident and emergency, its intentional artifice and clumsy repairs. Such an inspection will, however, only be possible when wall after wall, arch after arch, is demolished, the rubbish being at once cleared away as well as it can be. To effect this, and to level the site where it is possible to do so, to arrange the materials thus acquired, so that they can be hereafter again employed for a new building, is the arduous duty we have undertaken in this second part. Should we succeed, by a cheerful application of all possible ability and dexterity, in raising this Bastille, and in gaining a free space, it is thus by no means intended at once to cover the site again, and to encumber it with a new structure. We propose rather to make use of this area for the purpose of passing in review a pleasing and varied series of illustrative figures. The third part is thus devoted to the historical account of early inquirers and investigators. As we before expressed the opinion that the history of an individual displays his character, so it may here be well affirmed that the history of science is science itself. We cannot clearly be aware of what we possess till we have the means of knowing what others possessed before us. We cannot really and honestly rejoice in the advantages of our own time if we know not how to appreciate the advantages of former periods. But it was impossible to write, or even to prepare, the way for a history of the theory of colours while the Newtonian theory existed, for no aristocratic presumption has ever looked down on those who were not of its order, with such intolerable arrogance as that betrayed by the Newtonian school of deciding on all that had been done in earlier times, and all that was done around it. With disgust and indignation we find Priestley, in the history of optics, like many before and after him, dating the success of all researches into the world of colours from the epoch of a decomposed ray of light, or what pretended to be so, looking down with a supercilious air on the ancient and less modern inquirers, who, after all, had proceeded quietly in the right road, and who have transmitted to us observations and thoughts in detail which we can neither arrange better nor conceive more justly. We have a right to expect from one who proposes to give the history of any science that he informs us how the phenomena of which he treats were gradually known, and what was imagined, conjectured, assumed, or thought respecting them. To state all this in due connection is by no means an easy task. Need we say that to write a history at all is always a hazardous affair? With the most honest intention there is always a danger of being dishonest, for in such an undertaking a writer tacitly announces at the outset that he means to place some things in light, others in shade. The author has, nevertheless, long derived pleasure from the prosecution of his task, but it is the intention only that presents itself to the mind as a whole, while the execution is generally accomplished portion by portion. He is compelled to admit that instead of a history he furnishes only materials for one. These materials consist in translations, extracts, original and borrowed comments, hints and notes, a collection, in short, which, if not answering all that is required, has at least the merit of having been made with earnestness and interest. Lastly, such materials, not altogether untouched, it is true, but still not exhausted, may be more satisfactory to the reflecting reader in the state in which they are, as he can easily combine them according to his own judgment. This third part, containing the history of the science, does not, however, thus conclude the subject. A fourth supplementary portion is added. This contains a recapitulation or revision, with a view to which, chiefly, the paragraphs are headed numerically. In the execution of a work of this kind some things may be forgotten, some are of necessity omitted, so as not to distract the attention, some can only be arrived at as corollaries, and others may require to be exemplified and verified. On all these accounts, postscripts, additions, and corrections are indispensable. This part contains, besides, some detached essays, for example, that on the atmospheric colours, for as these are introduced in the theory itself without any classification, they are here presented to the mind's eye at one view. Again, if this essay invites the reader to consult nature herself, another is intended to recommend the artificial aids of science by circumstantially describing the apparatus which will in future be necessary to assist researches into the theory of colours. In conclusion, it only remains to speak of the plates which are added at the end of the work, and here we confess we are reminded of that incompleteness and imperfection which the present undertaking has in common with all others of its class. For as a good play can be in fact only half transmitted to writing, a great part of its effect depending on the scene, the personal qualities of the actor, the powers of his voice, the peculiarities of his gestures, and even the spirit and favourable humour of the spectators, so it is, in a still greater degree, with a book which treats of the appearances of nature. To be enjoyed, to be turned to account, nature herself must be present to the reader, either really or by the help of a lively imagination. Indeed, the author should in such cases communicate his observations orally, exhibiting the phenomena he describes, as a text, in the first instance, partly as they appear to us unsought, partly as they may be presented by contrivance to serve in particular illustration. Explanation and description could not then fail to produce a lively impression. The plates which generally accompany works like the present are thus a most inadequate substitute for all this. A physical phenomenon, exhibiting its effects on all sides, is not to be arrested in lines, nor denoted by a section. No one ever dreams of explaining chemical experiments with figures, yet it is customary in physical researches nearly allied to these, because the object is thus found to be in some degree answered. In many cases, however, such diagrams represent mere notions. They are symbolic resources, hieroglyphic modes of communication, which by degrees assume the place of the phenomena and of nature herself, and thus rather hinder than promote true knowledge. In the present instance we could not dispense with plates, but we have endeavoured so to construct them that they may be confidently referred to for the explanation of the didactic and polemical portions. Some of these may even be considered as forming part of the apparatus before mentioned. We now therefore refer the reader to the work itself, first only repeating a request which many an author has already made in vain, and which the modern German reader, especially, so seldom grants. Si quid novisti rectius istis, candidus imperti, si non his uteri mecum. End of section 1.
Section 2 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Nathan Rosequist of the Art Monastery Project, www.artmonastery.org. Theory of Colors by Johann Wolfgang von Goethe, translated by Charles Eastlake. Introduction. The desire of knowledge is first stimulated in us when remarkable phenomena attract our attention. In order that this attention be continued, it is necessary that we should feel some interest in exercising it, and thus by degrees we become better acquainted with the object of our curiosity. During this process of observation we remark at first only a vast variety which presses indiscriminately on our view. We are forced to separate, to distinguish, and again to combine, by which means at last a certain order arises which admits of being surveyed with more or less satisfaction. To accomplish this only in a certain degree, in any department, requires an unremitting and close application, and we find for this reason that men prefer substituting a general theoretical view or some system of explanation for the facts themselves, instead of taking the trouble to make themselves first acquainted with cases in detail and then constructing a whole. The attempt to describe and class the phenomena of colors has been only twice made, first by Theophrastus, and in modern times by Boyle. The pretensions of the present essay to the third place will hardly be disputed. Our historical survey enters into further details. Here we merely observe that in the last century such a classification was not to be thought of, because Newton had based his hypothesis on a phenomenon exhibited in a complicated and secondary state, and to this the other cases that forced themselves on the attention were contrived to be referred, when they could not be passed over in silence, just as an astronomer would do if from whim he were to place the moon in the center of our system. He would be compelled to make the earth, sun, and planets revolve round the lesser body, and be forced to disguise and gloss over the error of his first assumption by ingenious calculations and plausible statements. In our prefatory observations we assumed the reader to be acquainted with what was known respecting light. Here we assume the same with regard to the eye. We observed that all nature manifests itself by means of colors to the sense of sight. We now assert, extraordinary as it may in some degree appear, that the eye sees no form, inasmuch as light, shade, and color together constitute that which, to our vision, distinguishes object from object, and the parts of an object from each other. From these three, light, shade, and color, we construct the visible world, and thus at the same time make painting possible, an art which has the power of producing on a flat surface a much more perfect visible world than the actual one can be. The eye may be said to owe its existence to light, which calls forth as it were a sense that is akin to itself. The eye, in short, is formed with reference to light, to be fit for the action of light, the light it contains corresponding with the light without. We are here reminded of a significant adage in constant use with the ancient Ionian school. Like is only known by like. And again of the words of an old mystic writer, which may be thus rendered. If the eye were not sunny, how could we perceive light? If God's own strength lived not in us, how could we delight in divine things? This immediate affinity between light and the eye will be denied by none. To consider them as identical in substance is less easy to comprehend. It will be more intelligible to assert that a dormant light resides in the eye, and that it may be excited by the slightest cause from within or from without. In darkness we can, by an effort of imagination, call up the brightest images. In dreams objects appear to us as in broad daylight. Awake, the slightest external action of light is perceptible, and if the organ suffers an actual shock, light and colors spring forth. Here, however, those who are wont to proceed according to a certain method may perhaps observe that as yet we have not decidedly explained what color is. This question, like the definition of light and the eye, we would for the present evade, and would appeal to our inquiry itself, where we have circumstantially shown how color is produced. We have only, therefore, to repeat that color is a law of nature in relation with the sense of sight. We must assume, too, that everyone has this sense, that everyone knows the operation of nature on it, for to a blind man it would be impossible to speak of colors. That we may not, however, appear too anxious to shun such an explanation, we would restate what has been said as follows. Color is an elementary phenomenon in nature adapted to the sense of vision, a phenomenon which, like all others, exhibits itself by separation and contrast, by commixture and union, by augmentation and neutralization, by communication and dissolution. Under these general terms, its nature may be best comprehended. We do not press this mode of stating the subject on anyone. Those who, like ourselves, find it convenient will readily adopt it, but we have no desire to enter the lists hereafter in its defense. From time immemorial it has been dangerous to treat of color, so much so that one of our predecessors ventured on a certain occasion to say, "The ox becomes furious if a red cloth is shown to him, but the philosopher, who speaks of color only in a general way, begins to rave." Nevertheless, if we are to proceed to give some account of our work, to which we have appealed, we must begin by explaining how we have classed the different conditions under which color is produced. We found three modes in which it appears, three classes of colors, or rather three exhibitions of them all. The distinctions of these classes are easily expressed. Thus, in the first instance, we considered colors as far as they may be said to belong to the eye itself, and to depend on an action and reaction of the organ. Next, they attracted our attention as perceived in, or by means of, colorless mediums. And lastly, where we could consider them as belonging to particular substances. We have denominated the first physiological, the second physical, the third chemical colors. The first are fleeting and not to be arrested. The next are passing, but still for a while enduring. The last may be made permanent for any length of time. Having separated these classes and kept them as distinct as possible, with a view to a clear didactic exposition, we have been enabled at the same time to exhibit them in an unbroken series, to connect the fleeting with the somewhat more enduring, and these again with the permanent hues, and thus, after having carefully attended to a distinct classification in the first instance, to do away with it again, when a larger view was desirable. In a fourth division of our work, we have therefore treated generally what was previously detailed under various particular conditions, and have thus, in fact, given a sketch for a future theory of colors. We will here only anticipate our statements so far as to observe that light and darkness, brightness and obscurity, or if a more general expression is preferred, light and its absence, are necessary to the production of color. Next to the light, a color appears which we call yellow. Another appears next to the darkness, which we name blue. When these in their purest state are so mixed that they are exactly equal, they produce a third color called green. Each of the two first named colors can, however, of itself produce a new tint by being condensed or darkened. They thus acquire a reddish appearance, which can be increased to so great a degree that the original blue or yellow is hardly to be recognized in it. But the intensest and purest red, especially in physical cases, is produced when the two extremes of the yellow-red and blue-red are united. This is the actual state of the appearance and generation of colors. But we can also assume an existing red in addition to the definite existing blue and yellow, and we can produce contrariwise by mixing what we directly produced by augmentation or deepening. With these 3 or 6 colors, which may be conveniently included in a circle, the elementary doctrine of colors is alone concerned. All other modifications, which may be extended to infinity, have reference more to the application, have reference to the technical operations of the painter and dyer, and the various purposes of artificial life. To point out another general quality, we may observe that colors throughout are to be considered as half-lights, as half-shadows, on which account, if they are so mixed as reciprocally to destroy their specific hues, a shadowy tint, a gray, is produced. In the 5th division of our inquiry, we had proposed to point out the relations in which we should wish our doctrine of colors to stand to other pursuits. Important as this part of our work is, it is perhaps on this very account not so successful as we could wish. Yet when we reflect that strictly speaking these relations cannot be described before they exist, we may console ourselves if we have in some degree failed in endeavoring for the first time to define them. For undoubtedly we should first wait to see how those whom we have endeavored to serve, to whom we have intended to make an agreeable and useful offering, how such persons, we say, will accept the result of our utmost exertion, whether they will adopt it, whether they will make use of it and follow it up, or whether they will repel, reject, and suffer it to remain unassisted and neglected. Meanwhile we venture to express what we believe and hope. From the philosopher we believe we merit thanks for having traced the phenomena of colors to their first sources, to the circumstances under which they simply appear and are, and beyond which no further explanation respecting them is possible. It will, besides, be gratifying to him that we have arranged the appearances described in a form that admits of being easily surveyed, even should he not altogether approve of the arrangement itself. The medical practitioner, especially him whose study it is to watch over the organ of sight, to preserve it, to assist its defects, and to cure its disorders, we reckon to make especially our friend. In the chapter on the physiological colors, in the appendix relating to those that are more strictly pathological, he will find himself quite in his own province. We are not without hopes of seeing the physiological phenomena, a hitherto neglected, and we may add, most important branch of the theory of colors, completely investigated through the exertions of those individuals who in our own times are treating this department with success. The investigator of nature should receive us cordially, since we enable him to exhibit the doctrine of colors in the series of other elementary phenomena, and at the same time enable him to make use of corresponding nomenclature, nay, almost the same words and designations as under the other rubrics. It is true we give him rather more trouble as a teacher, for the chapter of colors is not now to be dismissed as heretofore with a few paragraphs and experiments. Nor will the scholar submit to be so scantily entertained as he has hitherto been, without murmuring. On the other hand, an advantage will afterwards arise out of this, for if the Newtonian doctrine was easily learnt, insurmountable difficulties presented themselves in its application. Our theory is perhaps more difficult to comprehend, but once known, all is accomplished, for it carries its application along with it. The chemist who looks upon colors as indications by which he may detect the more secret properties of material things, has hitherto found much inconvenience in the denomination and description of colors. Nay, some have been induced after closer and nicer examination to look upon color as an uncertain and fallacious criterion in chemical operations. Yet we hope by means of our arrangement and the nomenclature before alluded to bring color again into credit, and to awaken the conviction that a progressive, augmenting, mutable quality, a quality which admits of alteration even to inversion, is not fallacious, but rather calculated to bring to light the most delicate operations of nature. In looking a little further round us, we are not without fears that we may fail to satisfy another class of scientific men. By an extraordinary combination of circumstances, the theory of colors has been drawn into the province and before the tribunal of the mathematician, a tribunal to which it cannot be said to be amenable. This was owing to its affinity with the other laws of vision which the mathematician was legitimately called upon to treat. It was owing, again, to another circumstance. A great mathematician had investigated the theory of colors, and having been mistaken in his observations as an experimentalist, he employed the whole force of his talent to give consistency to this mistake. Were both these circumstances considered, all misunderstanding would presently be removed, and the mathematician would willingly cooperate with us, especially in the physical department of the theory. To the practical man, to the dyer, on the other hand, our labor must be altogether acceptable, for it was precisely those who reflected on the facts resulting from the operations of dyeing who were the least satisfied with the old theory. They were the first who perceived the insufficiency of the Newtonian doctrine. The conclusions of men are very different according to the mode in which they approach a science or branch of knowledge, from which side, through which door they enter. The literally practical man, the manufacturer, whose attention is constantly and forcibly called to the facts which occur under his eye, who experiences benefit or detriment from the application of his convictions, to whom loss of time and money is not indifferent, who is desirous of advancing, who aims at equaling or surpassing what others have accomplished, such a person feels the unsoundness and erroneousness of a theory much sooner than a man of letters, in whose eyes words consecrated by authority are at last equivalent to solid coin, than the mathematician whose formula always remains infallible, even although the foundation on which it is constructed may not square with it. Again, to carry on the figure before employed, in entering this theory from the side of painting, from the side of aesthetic coloring generally, we shall be found to have accomplished a most thankworthy office for the artist. In the sixth part we have endeavored to define the effects of color as addressed at once to the eye and mind, with a view to making them more available for the purposes of art. Although much in this portion, and indeed throughout, has been suffered to remain as a sketch, it should be remembered that all theory can in strictness only point out leading principles, under the guidance of which practice may proceed with vigor and be enabled to attain legitimate results. End of introduction. Recording by Nathan Rosequist of the Art Monastery Project. www.artmonastery.org.
Section 3 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dylan Campbell. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 3. Part 1. Physiological Colors. 1. We naturally place these colors first because they belong altogether or in a great degree to the subject, to the eye itself. They are the foundation of the whole doctrine, and open to our view the chromatic harmony on which so much difference of opinion has existed. They have been hitherto looked upon as extrinsic and casual, as illusion and infirmity. Their appearances have been known from ancient date, but as they were too evanescent to be arrested, they were banished into the region of phantoms, and under this idea have been very variously described. 2. Thus they are called color adventici by Boyle, imaginari fantastici by Rossetti, by Buffon, color accidentale, by Schurfer, Scheinfarben, apparent colors, ocular illusions and deceptions of sight by many, by Hamburger, vitia fugitiva, by Darwin, ocular spectra. 3. We have called them physiological because they belong to the eye in a healthy state, because we consider them as the necessary conditions of vision, the lively alternating action of which, with reference to external objects and the principle within it, is thus plainly indicated. 4. To these we subjoin the pathological colors, which, like all deviations from a constant law, afford a more complete insight into the nature of the physiological colors. Effects of light and darkness on the eye. 5. The retina, after being acted upon by light or darkness, is found to be in two different states, which are entirely opposed to each other. 6. If we keep the eyes open in a totally dark place, a certain sense of privation is experienced. The organ is abandoned to itself. It retires into itself. That stimulating and grateful contact is wanting, by means of which it is connected with the external world and becomes part of a whole. 7. If we look on a white, strongly illumined surface, the eye is dazzled, and for a time is incapable of distinguishing objects moderately lighted. 8. The whole of the retina is acted on in each of these extreme states, and thus we can only experience one of these effects at a time. In the one case, 6, we found the organ in the utmost relaxation and susceptibility. In the other, 7, in an overstrained state, and scarcely susceptible at all. 9. If we pass suddenly from the one state to the other, even without supposing these to be the extremes, but only perhaps a change from bright to dusky, the difference is remarkable, and we find that the effects last for some time. 10. In passing from bright daylight to a dusky place, we distinguish nothing at first. By degrees the eye recovers its susceptibility, strong eyes sooner than weak ones, the former in a minute, while the latter may require 7 or 8 minutes. 11. The fact that the eye is not susceptible to faint impressions of light, if we pass from light to comparative darkness, has led to curious mistakes in scientific observations. Thus, an observer, whose eyes required some time to recover their tone, was long under the impression that rotten wood did not emit light at noonday, even in a dark room. The fact was, he did not see the faint light because he was in the habit of passing from bright sunshine to the dark room, and only subsequently remained so long there that the eye had time to recover itself. The same may have happened to Dr. Wall, who, in the daytime, even in a dark room, could hardly perceive the electric light of amber. Our not seeing the stars by day, as well as the improved appearance of pictures seen through a double tube, is also to be attributed to the same cause. 12. If we pass from a totally dark place to one illumined by the sun, we are dazzled. In coming from a lesser degree of darkness to light that is not dazzling, we perceive all objects clearer and better. Hence, eyes that have been in a state of repose are in all cases better able to perceive moderately distinct appearances. Prisoners who have been long confined in darkness acquire so great a susceptibility of the retina that even in the dark, probably a darkness very slightly illumined, they can still distinguish objects. 13. In the act which we call seeing, the retina is at one and the same time in different and even opposite states. The greatest brightness, short of dazzling, acts near the greatest darkness. In this state we at once perceive all the intermediate gradations of chiaroscuro and all the varieties of hues. 14. We will proceed in due order to consider and examine these elements of the visible world, as well as the relation in which the organ itself stands to them, and for this purpose we take the simplest objects. Footnote 1. The German distinction between subject and object is so generally understood and adopted that it is hardly necessary to explain that the subject is the individual, in this case the beholder, the object all that is without him. End of section 3.
Section 4 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Nathan Rosequist of the Art Monastery Project, www.artmonastery.org. Theory of Colors by Johann Wolfgang von Goethe, translated by Charles Eastlake. Part 1, Section 2. Effects of black and white objects on the eye. 15. In the same manner as the retina generally is affected by brightness and darkness, so it is affected by single bright or dark objects. If light and dark produce different results on the whole retina, so black and white objects, seen at the same time, produce the same states together which light and dark occasioned in succession. 16. A dark object appears smaller than a bright one of the same size. Let a white disk be placed on a black ground, and a black disk on a white ground, both being exactly similar in size. Let them be seen together at some distance, and we shall pronounce the last to be about a fifth part smaller than the other. If the black circle be made larger by so much, they will appear equal. 17. Thus, Tycho de Brahe remarked that the moon in conjunction, the darker state, appears about a fifth part smaller than when in opposition, the bright full state. The first crescent appears to belong to a larger disk than the remaining dark portion, which can sometimes be distinguished at the period of the new moon. Black dresses make people appear smaller than light ones. Lights seen behind an edge make an apparent notch in it. A ruler behind which the flame of a light just appears seems to us indented. The rising or setting sun appears to make a notch in the horizon. 18. Black, as the equivalent of darkness, leaves the organ in a state of repose. White, as the representative of light, excites it. We may perhaps conclude from the above experiment that the unexcited retina, if left to itself, is drawn together, and occupies a less space than in its active state, produced by the excitement of light. Hence, Kepler says very beautifully, Certum est vel in retina causa picturae, vel in spiritibus causa impressionis, existere dilatationem lucidorum. It is certain that, whether as a retinal image or the impression it makes on our spirit, light has an enlarging quality. This from Paralipomenon in Vitellionem, page 220. Schurfer expresses a similar conjecture. Footnote by Goethe's scientific friend Thomas Johann Seebeck. Leonardo da Vinci observes that a light object relieved on a dark ground appears magnified. And again, objects seen at a distance appear out of proportion. This is because the light parts transmit their rays to the eye more powerfully than the dark. A woman's white headdress once appeared to me much wider than her shoulders, owing to their being dressed in black. It is now generally admitted that the excitation produced by light is propagated on the retina a little beyond the outline of the image. Professor Plateau of Ghent has devoted a very interesting special memoir to the description and explanation of phenomena of this nature. See his Memoir sur les radiations, published in the 11th volume of the Transactions of the Royal Academy of Sciences at Brussels. End of footnote. 19. However this may be, both impressions derived from such objects remain in the organ itself and last for some time, even when the external cause is removed. In ordinary experience we scarcely notice this, for objects are seldom presented to us which are very strongly relieved from each other, and we avoid looking at those appearances that dazzle the sight. In glancing from one object to another, the succession of images appears to us distinct. We are not aware that some portion of the impression derived from the object first contemplated passes to that which is next looked at. 20. If in the morning, on waking, when the eye is very susceptible, we look intently at the bars of a window relieved against the dawning sky, and then shut our eyes or look towards a totally dark place, we shall see a dark cross on a light ground before us for some time. 21. Every image occupies a certain space on the retina, and of course a greater or less space in proportion as the object is seen near or at a distance. If we shut the eyes immediately after looking at the sun, we shall be surprised to find how small the image it leaves appears. 22. If, on the other hand, we turn the open eye towards the side of a room and consider the visionary image in relation to other objects, we shall always see it larger in proportion to the distance of the surface on which it is thrown. This is easily explained by the laws of perspective, according to which a small object near covers a great one at a distance. 23. The duration of these visionary impressions varies with the powers or structure of the eye in different individuals, just as the time necessary for the recovery of the tone of the retina varies in passing from brightness to darkness. It can be measured by minutes and seconds, indeed much more exactly than it could formerly have been, by causing a lighted linstock to revolve rapidly so as to appear a circle. Footnote by Thomas Johann Siebeck. The duration of ocular spectra produced by strongly exciting the retina may be conveniently measured by minutes and seconds, but to ascertain the duration of more evanescent phenomena, recourse must be had to other means. The Chevalier d'Arcy, in Memoirs of the Academy of Science, 1765, endeavored to ascertain the duration of the impression produced by a glowing coal in the following manner. He attached it to the circumference of a wheel, the velocity of which was gradually increased until the apparent trace of the object formed a complete circle, and then measured the duration of the revolution, which was obviously that of the impression. To ascertain the duration of a revolution, it is sufficient merely to know the number of revolutions described in a given time. Recently, more refined experiments of the same kind have been made by Professors Plateau and Wheatstone. End footnote. 24. But the force with which an impinging light impresses the eye is especially worthy of attention. The image of the sun lasts longest. Other objects, of various degrees of brightness, leave the traces of their appearance on the eye for a proportionate time. 25. These images disappear by degrees, and diminish at once in distinctness and in size. 26. They are reduced from the contour inwards, and the impression on some persons has been that in square images the angles become gradually blunted, till at last a diminished round image floats before the eye. 27. Such an image, when its impression is no more observable, can, immediately after, be again revived on the retina by opening and shutting the eye, thus alternately exciting and resting it. 28. Images may remain on the retina in morbid affections of the eye for 14, 17 minutes, or even longer. This indicates extreme weakness of the organ, its inability to recover itself, while visions of persons or things which are the objects of love or aversion indicate the connection between sense and thought. 29. If, while the image of the window bars before mentioned lasts, we look upon a light gray surface, the cross will then appear light and the panes dark. In the first case, the image was like the original picture, so that the visionary impression also could continue unchanged, but in the present instance our attention is excited by a contrary effect being produced. Various examples have been given by observers of nature. 30. The scientific men who made observations in the Cordilleras saw a bright appearance round the shadows of their heads on some clouds. This example is a case in point, for while they fixed their eyes on the dark shadow, and at the same time moved from the spot, the compensatory light image appeared to float round the real dark one. If we look at a black disk on a light gray surface, we shall presently, by changing the direction of the eyes in the slightest degree, see a bright halo floating round the dark circle. A similar circumstance happened to myself, for while, as I sat in the open air, I was talking to a man who stood at a little distance from me, relieved on a gray sky, it appeared to me, as I slightly altered the direction of my eyes, after having for some time looked fixedly at him, that his head was encircled with a dazzling light. In the same way, probably might be explained the circumstance that persons crossing dewy meadows at sunrise see a brightness round each other's heads. The brightness in this case may be also iridescent, as the phenomena of refraction come into the account. Thus again it has been asserted that the shadows of a balloon thrown on clouds were bordered with bright and somewhat variegated circles. Beccaria made use of a paper kite in some experiments on electricity. Round his kite appeared a small shining cloud varying in size. The same brightness was even observed round part of the string. Sometimes it disappeared, and if the kite moved faster, the light appeared to float to and fro for a few moments on the place before occupied. This appearance, which could not be explained by those who observed it at the time, was the image which the eye retained of the kite relieved as a dark mass on a bright sky, that image being changed into a light mass on a comparatively dark background. In optical and especially in chromatic experiments, where the observer has to do with bright lights, whether colorless or colored, great care should be taken that the spectrum which the eye retains in consequence of a previous observation does not mix with the succeeding one, and thus affect the distinctness and purity of the impression. 31. These appearances have been explained as follows. That portion of the retina on which the dark cross was impressed is to be considered in a state of repose and susceptibility. On this portion, therefore, the moderately light surface acted in a more lively manner than on the rest of the retina, which had just been impressed with the light through the panes, and which, having thus been excited by a much stronger brightness, could only view the gray surface as a dark. 32. This mode of explanation appears sufficient for the cases in question, but, in the consideration of phenomena hereafter to be adduced, we are forced to trace the effects to higher sources. 33. The eye after sleep exhibits its vital elasticity more especially by its tendency to alternate its impressions, which in the simplest form change from dark to light, and from light to dark. The eye cannot for a moment remain in a particular state determined by the object it looks upon. On the contrary, it is forced to a sort of opposition, which, in contrasting extreme with extreme, intermediate degree with intermediate degree, at the same time combines these opposite impressions, and thus ever tends to a whole, whether the impressions are successive or simultaneous and confined to one image. 34. Perhaps the peculiarly grateful sensation which we experience in looking at the skilfully treated chiaroscuro of colorless pictures and similar works of art arises chiefly from the simultaneous impression of a whole, which by the organ itself is sought, rather than arrived at, in succession, and which, whatever may be the result, can never be arrested. End of Part 1, Section 2. Recording by Nathan Rosequist of the Art Monastery Project. artmonastery.org.
Section 5 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Deborah Wade, Cambridge, United Kingdom. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Part 1, Section 3. Grey Surfaces and Objects. 35. A moderate light is essential to many chromatic experiments. This can be presently obtained by surfaces more or less grey, and thus we have at once to make ourselves acquainted with this simplest kind of middle tint, with regard to which it is hardly necessary to observe that in many cases a white surface in shadow or in a low light may be considered equivalent to a grey. 36. Since a grey surface is intermediate between brightness and darkness, it admits of our illustrating a phenomenon before described 29 by an easy experiment. 37. Let a black object be held before a grey surface, and let the spectator, after looking steadfastly at it, keep his eyes unmoved while it is taken away. The space it occupied appears much lighter. Let a white object be held up in the same manner. On taking it away, the space it occupied will appear much darker than the rest of the surface. Let the spectator in both cases turn his eyes this way and that on the surface. The visionary images will move in like manner. 38. A grey object on a black ground appears much brighter than the same object on a white ground. If both comparisons are seen together, the spectator can hardly persuade himself that the two greys are identical. We believe this again to be a proof of the great excitability of the retina, and of the silent resistance which every vital principle is forced to exhibit when any definite or immutable state is presented to it. Thus, inspiration already presupposes expiration. Thus, every systole its diastole. It is the universal formula of life which manifests itself in this as in all other cases. When darkness is presented to the eye, it demands brightness, and vice versa. It shows its vital energy, its fitness to receive the impression of the object, precisely by spontaneously tending to an opposite state. End of Part 1, Section 3. Part 1, Section 4. Dazzling colourless objects. 39. If we look at a dazzling, altogether colourless object, it makes a strong, lasting impression, and its after-vision is accompanied by an appearance of colour. 40. Let a room be made as dark as possible. Let there be a circular opening in the window shutter about 3 inches in diameter, which may be closed or not at pleasure. The sun being suffered to shine through this on a white surface, let the spectator from some little distance fix his eyes on the bright circle thus admitted. The hole being then closed, let him look towards the darkest part of the room. A circular image will now be seen to float before him. The middle of this circle will appear bright, colourless, or somewhat yellow, but the border will at the same moment appear red. After a time, this red increasing towards the centre covers the whole circle, and at last the bright central point. No sooner, however, is the whole circle red than the edge begins to be blue, and the blue gradually encroaches inwards on the red. When the whole is blue, the edge becomes dark and colourless. This darker edge again slowly encroaches on the blue till the whole circle appears colourless. The image then becomes gradually fainter, and at the same time diminishes in size. Here again we see how the retina recovers itself by a succession of vibrations after the powerful external impression it received. 25-26. 41. By several repetitions similar in result, I found the comparative duration of these appearances in my own case to be as follows. I looked on the bright circle 5 seconds, and then, having closed the aperture, saw the coloured visionary circle floating before me. After 13 seconds it was altogether red. 29 seconds next elapsed till the whole was blue, and 48 seconds till it appeared colourless. By shutting and opening the eye, I constantly revived the image so that it did not quite disappear till 7 minutes had elapsed. Future observers may find these periods shorter or longer as their eyes may be stronger or weaker. 23. But it would be very remarkable if, notwithstanding such variations, a corresponding proportion as to relative duration should be found to exist. 42. But this remarkable phenomenon no sooner excites our attention than we observe a new modification of it. If we receive the impression of the bright circle as before, and then look on a light grey surface in a moderately lighted room, an image again floats before us, but in this instance a dark one. By degrees it is encircled by a green border that gradually spreads inwards over the whole circle, as the red did in the former instance. As soon as this has taken place, a dingy yellow appears, and filling the space as the blue did before, is finally lost in a negative shade. 43. These two experiments may be combined by placing a black and white plane surface next each other in a moderately lighted room, and then looking alternately on one and the other as long as the impression of the light circle lasts. The spectator will then perceive at first a red and green image alternately, and afterwards the other changes. After a little practice, the two opposite colours may be perceived at once, by causing the floating image to fall on the junction of the two planes. This can be more conveniently done if the planes are at some distance, for the spectrum then appears larger. 44. I happened to be in a forge towards evening, at the moment when a glowing mass of iron was placed on the anvil. I had fixed my eyes steadfastly on it, and, turning around, I looked accidentally into an open coal shed. A large red image now floated before my eyes, and as I turned them from the dark opening to the light boards of which the shed was constructed, the image appeared half green, half red, according as it had a lighter or darker ground behind it. I did not at that time take notice of the subsequent changes of this appearance. 45. The after vision occasioned by a total dazzling of the retina corresponds with that of a circumscribed bright object. The red colour seen by persons who are dazzled with snow belongs to this class of phenomena, as well as the singularly beautiful green colour which dark objects seem to wear after looking long on white paper in the sun. The details of such experiments may be investigated hereafter by those whose young eyes are capable of enduring such trials further for the sake of science. 46. With these examples we may also class the black letters which in the evening light appear red. Perhaps we might insert under the same category the story that drops of blood appeared on the table at which Henry IV of France had seated himself with the Duc de Guise to play at dice. End of section 5. Section 6 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Deborah Wade, Cambridge, United Kingdom. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Part 1, Section 5. Coloured Objects. 47. We have hitherto seen the physiological colours displayed in the after vision of colourless bright objects, and also in the after vision of general colourless brightness. We shall now find analogous appearances if a given colour be presented to the eye. In considering this, all that has been hitherto detailed must be present to our recollection. 48. The impression of coloured objects remains in the eye like that of colourless ones, but in this case the energy of the retina, stimulated as it is to produce the opposite colour, will be more apparent. 49. Let a small piece of bright coloured paper or silk stuff be held before a moderately lighted white surface. Let the observer look steadfastly on the small coloured object, and let it be taken away after a time while his eyes remain unmoved. The spectrum of another colour will then be visible on the white plane. The coloured paper may be also left in its place while the eye is directed to another part of the white plane. The same spectrum will be visible there too, for it arises from an image which now belongs to the eye. 50. In order at once to see what colour will be evoked by this contrast, the chromatic circle, Plate 1, Fig. 3, may be referred to. The colours are here arranged in a general way according to the natural order, and the arrangement will be found to be directly applicable in the present case, for the colours diametrically opposed to each other in this diagram are those which reciprocally evoke each other in the eye. Thus yellow demands purple, orange blue, red green, and vice versa. Thus again all intermediate graduations reciprocally evoke each other, the simpler colour demanding the compound, and vice versa. Note C. 51. The cases here under consideration occur oftener than we are aware in ordinary life. Indeed, an attentive observer sees these appearances everywhere, while, on the other hand, the uninstructed, like our predecessors, consider them as temporary visual defects, sometimes even as symptoms of disorders in the eye, thus exciting serious apprehensions. A few remarkable instances may here be inserted. 52. I had entered an inn towards evening, and as a well-favoured girl with a brilliantly fair complexion, black hair, and a scarlet bodice came into the room, I looked attentively at her as she stood before me at some distance in half shadow. As she presently afterwards turned away, I saw on the white wall which was now before me a black face surrounded with a bright light, while the dress of the perfectly distinct figure appeared of a beautiful sea green. 53. Among the materials for optical experiments there are portraits with colours and shadows exactly opposite to the appearance of nature. The spectator, after having looked at one of these for a time, will see the visionary figure tolerably true to nature. This is conformable to the same principles, and consistent with experience, for, in the former instance, a negress with a white headdress would have given me a white face surrounded with black. In the case of the painted figures, however, which are commonly small, the parts are not distinguishable by every one in the after image. 54. A phenomenon which has before excited attention among the observers of nature is to be attributed, I am persuaded, to the same cause. It has been stated that certain flowers towards evening in summer coruscate, become phosphorescent, or emit a momentary light. Some persons have described their observation of this minutely. I had often endeavoured to witness it myself, and had even resorted to artificial contrivances to produce it. On the 19th of June 1799, late in the evening, when the twilight was deepening into a clear night, as I was walking up and down the garden with a friend, we very distinctly observed a flame-like appearance near the oriental poppy, the flowers of which are remarkable for their powerful red colour. We approached the place and looked attentively at the flowers, but could perceive nothing further till at last, by passing and repassing repeatedly, while we looked sideways on them, we succeeded in renewing the appearance as often as we pleased. It proved to be a physiological phenomenon, such as others we have described, and the apparent coruscation was nothing but the spectrum of the flower in the compensatory blue-green colour. In looking directly at a flower, the image is not produced, but it appears immediately as the direction of the eye is altered. Again, by looking sideways on the object, a double image is seen for a moment for the spectrum, then appears near and on the real object. The twilight accounts for the eye being in a perfect state of repose, and thus very susceptible, and the colour of the poppy is sufficiently powerful in the summer twilight of the longest days to act with full effect and produce a compensatory image. I have no doubt these appearances might be reduced to experiment, and the same effect produced by pieces of coloured paper. Those who wish to take the most effectual means for observing the appearance in nature, suppose in a garden, should fix the eyes on the bright flowers selected for the purpose, and immediately after look on the gravel path. This will be seen studded with spots of the opposite colour. This experiment is practicable on a cloudy day and even in the brightest sunshine, for the sunlight, by enhancing the brilliancy of the flower, renders it fit to produce a compensatory colour sufficiently distinct to be perceptible even in a bright light. Thus peonies produce beautiful green, marigolds vivid blue spectra. 55. As the opposite colour is produced by a constant law in experiments with coloured objects on portions of the retina, so the same effect takes place when the whole retina is impressed with a single colour. We may convince ourselves of this by means of coloured glasses. If we look long through a blue pane of glass, everything will afterwards appear in sunshine to the naked eye, even if the sky is grey and the scene colourless. In like manner, in taking off green spectacles, we see all objects in a red light. Every decided colour does a certain violence to the eye, and forces the organ to opposition. 56. We have hitherto seen the opposite colours producing each other successively on the retina. It now remains to show by experiment that the same effects can exist simultaneously. If a coloured object impinges on one part of the retina, the remaining portion at the same moment has a tendency to produce a compensatory colour. To pursue a former experiment, if we look on a yellow piece of paper placed on a white surface, the remaining part of the organ has already a tendency to produce a purple hue on the colourless surface. In this case, the small portion of yellow is not powerful enough to produce this appearance distinctly, but if a white paper is placed on a yellow wall, we shall see the white tinged with a purple hue. 57. Although this experiment may be made with any colours, yet red and green are particularly recommended for it because these colours seem powerfully to evoke each other. Numerous instances occur in daily experience. If a green paper is seen through striped or flowered muslin, the stripes or flowers will appear reddish. A grey building seen through green palisades appears in like manner reddish. A modification of this tint in the agitated sea is also a compensatory colour. The light side of the waves appears green in its own colour, and the shadowed side is tinged with the opposite hue. The different direction of the waves with reference to the eye produces the same effect. Objects seen through an opening in the red or green curtain appear to wear the opposite hue. These appearances will present themselves to the attentive observer on all occasions, even to an unpleasant degree. 58. Having made ourselves acquainted with the simultaneous exhibition of these effects in direct cases, we shall find that we can also observe them by indirect means. If we place a piece of paper of a bright orange colour on the white surface, we shall, after looking intently at it, scarcely perceive the compensatory colour on the rest of the surface. But when we take the orange paper away, and when the blue spectrum appears in its place, immediately as this spectrum becomes fully apparent, the rest of the surface will overspread, as if by a flash, with a reddish-yellow light, thus exhibiting to the spectator in a lively manner the productive energy of the organ, in constant conformity with the same law. 59. As the compensatory colours easily appear where they do not exist in nature near and after the original opposite ones, so they are rendered more intense when they happen to mix with a similar real hue. In a court which was paved with grey limestone flags, between which grass had grown, the grass appeared of an extremely beautiful green when the evening clouds threw a scarcely perceptible reddish light on the pavement. In an opposite case, we find, in walking through meadows where we see scarcely anything but green, the stems of trees and the roads often gleam with a reddish hue. This tone is not uncommon in the works of landscape painters, especially those who practice in watercolours. They probably see it in nature, and thus unconsciously imitating it. Their colouring is criticised as unnatural. 60. These phenomena are of the greatest importance, since they direct our attention to the laws of vision, and are a necessary preparation for future observations on colours. They show that the eye especially demands completeness, and seeks to eke out the colorific circle in itself. The purple or violet colour suggested by yellow contains red and blue. Orange, which corresponds to blue, is composed of yellow and red. Green, uniting blue and yellow, demands red, and so through all graduations of the most complicated combinations. That we are compelled in this case to assume three leading colours has already been remarked by other observers. 61. When in this completeness the elements of which it is composed are still appreciable by the eye, the result is justly called harmony. We shall subsequently endeavour to show how the theory of the harmony of colours may be deduced from these phenomena, and how, simply through these qualities, colours may be capable of being applied to aesthetic purposes. This will be shown when we have gone through the whole circle of our observations, returning to the point from which we started.
6. Section 7 of Theory of Colours.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Deborah Wade, Cambridge, United Kingdom. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Part 1, Section 6, Coloured Shadows. 62. Before, however, we proceed further, we have yet to observe some very remarkable cases of the vivacity with which the suggested colours appear in the neighbourhood of others. We allude to coloured shadows. To arrive at these, we first turn our attention to shadows that are colourless or negative. 63. A shadow cast by the sun in its full brightness on a white surface gives us no impression of colour. It appears black, or, if a contrary light, here assumed to differ only in a degree, can act upon it, it is only weaker, half-lightened grey. 64. Two conditions are necessary for the existence of coloured shadows. First, that the principal light tinge the white surface with some hue. Secondly, that a contrary light illuminate to a certain extent the cast shadow. 65. Let a short lighted candle be placed at twilight on a sheet of white paper. Between it and the declining daylight, let a pencil be placed upright, so that its shadow thrown by the candle may be lighted, but not overcome by the weak daylight. The shadow will appear of the most beautiful blue. 66. That this shadow is blue is immediately evident, but we can only persuade ourselves by some attention that the white paper acts as a reddish yellow, by means of which the complemental blue is excited in the eye. 67. In all coloured shadows, therefore, we must presuppose a colour excited or suggested by the hue of the surface on which the shadow is thrown. This may easily be found to be the case by attentive consideration. but we may convince ourselves at once by the following experiment. 68. Place 2 candles at night opposite each other on a white surface. Hold a thin rod between them upright, so that 2 shadows be cast by it. Take a coloured glass and hold it before one of the lights, so that the white paper appear coloured. At the same moment, the shadow cast by the coloured light and slightly illumined by the colourless one will exhibit the complemental hue. 69. An important consideration suggests itself here, to which we shall frequently have occasion to return. Colour itself is a degree of darkness, skipov. Hence Kircher is perfectly right in calling it lumen opacatum. As it is allied to shadow, so it combines readily with it. It appears to us readily in and by means of shadow, the moment a suggesting cause presents itself. We could not refrain from adverting at once to a fact which we propose to trace and develop hereafter. 70. Select the moment in twilight when the light of the sky is still powerful enough to cast a shadow, which cannot be entirely effaced by the light of a candle. The candle may be so placed that a double shadow shall be visible, one from the candle towards the daylight, and another from the daylight towards the candle. If the former is blue, the latter will appear orange-yellow. This orange-yellow is in fact, however, only the yellow-red light of the candle diffused over the whole paper, and which becomes visible in shadow. 71. This is best exemplified by the former experiment with 2 candles and coloured glasses. The surprising readiness with which shadow assumes a colour will again invite our attention in the further consideration of reflections and elsewhere. 72. Thus the phenomena of coloured shadows may be traced to their cause without difficulty. Henceforth, let any one who sees an instance of the kind observe only with what hue the light surface on which they are thrown is tinged. Nay, the colour of the shadow may be considered as a chromatoscope of the illuminated surface, for the spectator may always assume the colour of the light to be the opposite of that of the shadow, and by an attentive examination may ascertain this to be the fact in every instance. 73. These appearances have been a source of great perplexity to former observers, for, as they were remarked chiefly in the open air, where they commonly appear blue, they were attributed to a certain inherent blue or blue colouring quality in the air. The inquirer can, however, convince himself by the experiment with the candle in a room that no kind of blue light or reflection is necessary to produce the effect in question. The experiment may be made on a cloudy day with white curtains drawn before the light, and in a room where no trace of blue exists, and the blue shadow will be only so much the more beautiful. 74. De Saussure, in the description of his ascent of Mont Blanc, says, "A second remark, which may not be uninteresting, relates to the colour of the shadows. These, notwithstanding the most attentive observation, we never found dark blue, although this had been frequently the case in the plain. On the contrary, in 59 instances we saw them once yellowish, 6 times pale bluish, 18 times colourless or black, and 34 times pale violet. Some natural philosophers suppose that these colours arise from accidental vapours diffused in the air, which communicate their own hues to the shadows. Not that the colours of the shadows are occasioned by the reflection of any given sky colour or interposition of any given air colour. The above observations seem to favour this opinion. The instances given by de Saussure may now be explained and classed with analogous examples without difficulty. At a great elevation the sky was generally free from vapours. The sun shone in full force on the snow, so that it appeared perfectly white to the eye. In this case they saw the shadows quite colourless. If the air was charged with a certain degree of vapour, in consequence of which the light snow would assume a yellowish tone, the shadows were violet-coloured, and this effect, it appears, occurred oftenest. They saw also bluish shadows, but this happened less frequently, and that the blue and violet were pale was owing to the surrounding brightness, by which the strength of the shadows was mitigated. Once only they saw the shadow yellowish. In this case, as we have already seen, the shadow is cast by a colourless light, and slightly illuminated by a coloured one. 75. In travelling over the Harz in winter, I happened to descend from the Brocken towards evening. The wide slopes extended above and below me from the heath, every insulated tree projecting rock, and all masses of both were covered with snow or hoarfrost. The sun was sinking towards the Oder ponds. During the day, owing to the yellowish hue of the snow, shadows tending to violet had already been observable. These might now be pronounced to be decidedly blue, as the illumined parts exhibited a yellow deepening to orange. But as the sun at last was about to set, and its rays, greatly mitigated by the thicker vapours, began to diffuse a most beautiful red colour over the whole scene around me, the shadow colour changed to a green, in lightness to be compared to a sea green, in beauty to the green of the emerald. The appearance became more and more vivid. One might have imagined oneself in a fairy world, for every object had clothed itself in the too vivid and so beautifully harmonizing colours, till at last, as the sun went down, the magnificent spectacle was lost in a grey twilight, and by degrees in a clear moon and starlight night. 76. One of the most beautiful instances of coloured shadows may be observed during the full moon. The candle light and moonlight may be contrived to be exactly equal in force. Both shadows may be exhibited with equal strength and clearness, so that both colours balance each other perfectly. A white surface being placed opposite the full moon, and the candle being placed a little on one side at a due distance, an opaque body is held before the white plane. A double shadow will then be seen. That cast by the moon and illumined by the candle light will be a powerful red-yellow, and contrariwise that cast by the candle and illumined by the moon will appear of the most beautiful blue. The shadow composed of the union of the two shadows where they cross each other is black. The yellow shadow cannot perhaps be exhibited in a more striking manner. The immediate vicinity of the blue and the interposing black shadow make the appearance more agreeable. It will even be found, if the eye dwells long on these colours, that they mutually evoke and enhance each other, the increasing red in the one still producing its contrast, viz. A kind of sea green. 77. We are here led to remark that in this, and in all cases, a moment or two may perhaps be necessary to produce the complemental colour. The retina must be first thoroughly impressed with the demanding hue before the responding one can be distinctly observable. 78. When divers are under water and the sunlight shines into the diving bell, everything is seen in a red light, the cause of which will be explained hereafter, while the shadows appear green. The very same phenomenon which I observed on a high mountain is presented to others in the depths of the sea, and thus nature throughout is in harmony with herself. 79. Some observations and experiments which equally illustrate what has been stated with regard to coloured objects and coloured shadows may be added here. Let a white paper blind be fastened inside the window on a winter evening. In this blind let there be an opening, through which the snow of some neighbouring roof can be seen. Towards dusk let a candle be brought into the room. The snow seen through the opening will then appear perfectly blue, because the paper is tinged with warm yellow by the candle light. The snow seen through the aperture is here equivalent to a shadow illumined by a contrary light, and may also represent a grey disk on a coloured surface. 80. Another very interesting experiment may conclude these examples. If we take a piece of green glass of some thickness and hold it so that the window bars be reflected in it, they will appear double owing to the thickness of the glass. The image which is reflected from under the surface of the glass will be green. The image which is reflected from the upper surface, and which should be colourless, will appear red. The experiment may be very satisfactorily made by pouring water into a vessel, the inner surface of which can act as a mirror, for both reflections may first be seen colourless while the water is pure, and then by tinging it they will exhibit two opposite hues. End of section 7. Recording by Deborah Wade.
Section 8 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kieran Metz. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 8. Faint Lights. 81. Light, in its full force, appears purely white, and it gives this impression also in its highest degree of dazzling splendor. Light, which is not so powerful, can also, under various conditions, remain colorless. Several naturalists and mathematicians have endeavored to measure its degrees: Lambert, Bouguer, and Rumford. 82. Yet an appearance of color presently manifests itself in fainter lights, for in their relation to absolute light they resemble the colored spectra of dazzling objects. 83. A light of any kind becomes weaker either when its own force from whatever cause is diminished, or when the eye is so circumstanced or placed that it cannot be sufficiently impressed by the action of the light. Those appearances, which may be called objective, come under the head of physical colors. We will only advert here to the transition from white to red heat in glowing iron. We may also observe that the flames of lights at night appear redder in proportion to their distance from the eye. 84. Candlelight at night acts as yellow when seen near. We can perceive this by the effect it produces on other colors. At night, a pale yellow is hardly to be distinguished from white. Blue approaches to green, and rose color to orange. 85. Candlelight at twilight acts powerfully as a yellow light. This is best proved by the purple-blue shadows which, under these circumstances, are evoked by the eye. 86. The retina may be so excited by a strong light that it cannot perceive fainter lights. If it perceive these, they appear colored. Hence, candlelight by day appears reddish, thus resembling, in its relation to fuller light, the spectrum of a dazzling object. Nay, if at night we look long and intently on the flame of a light, it appears to increase in redness. 87. There are faint lights which, notwithstanding their moderate luster, give an impression of a white, or, at the most, of a light yellow appearance on the retina, such as the moon in its full splendor. Rotten wood has even a kind of bluish light. All this will hereafter be the subject of further remarks. 88. If at night we place a light near a white or grayish wall, so that the surface be illumined from this central point to some extent, we find on observing the spreading light at some distance that the boundary of the illumined surface appears to be surrounded with a yellow circle, which on the outside tends to red-yellow. We thus observe that when light direct or reflected does not act in its full force, it gives an impression of yellow, of reddish, and lastly even of red. Here we find the transition to halos which we are accustomed to see in some mode or other round luminous points. Part 8. Subjective Halos. 89. Halos may be divided into subjective and objective. The latter will be considered under the physical colors. The first only belong here. These are distinguished from the objective halos by the circumstance of their vanishing when the point of light which produces them on the retina is covered. 90. We have before noticed the impression of a luminous object on the retina and seen that it appears larger, but the effect is not at an end here. It is not confined to the impression of the image. An expansive action also takes place, spreading from the center. 91. That a nimbus of this kind is produced round the luminous image in the eye may be best seen in a dark room, if we look towards a moderately large opening in the window shutter. In this case, the bright image is surrounded by a circular misty light. I saw such a halo bounded by a yellow and yellow-red circle on opening my eyes at dawn, on an occasion when I passed several nights in a bed carriage. 92. Halos appear most vivid when the eye is susceptible from having been in a state of repose. A dark background also heightens their appearance. Both causes account for our seeing them so strong if a light is presented to the eyes on waking at night. These conditions were combined when Descartes, after sleeping, as he sat in a ship, remarked such a vividly colored halo round the light. 93. A light must shine moderately, not dazzle, in order to produce the impression of a halo in the eye. At all events, the halos of dazzling lights cannot be observed. We see a splendor of this kind round the image of the sun reflected from the surface of water. 94. A halo of this description, attentively observed, is found to be encircled towards its edge with a yellow border. But even here, the expansive action, before alluded to, is not at an end, but appears still to extend in varied circles. 95. Several cases seem to indicate a circular action of the retina, whether owing to the round form of the eye itself and its different parts, or to some other cause. 96. If the eye is pressed only in a slight degree from the inner corner, darker or lighter circles appear. At night, even without pressure, we can sometimes perceive a succession of such circles emerging from or spreading over each other. 97. We have already seen that a yellow border is apparent round the white space illumined by a light placed near it. This may be a kind of objective halo. 98. Subjective halos may be considered as the result of a conflict between the light and a living surface. From the conflict between the exciting principle and the excited, an undulating motion arises, which may be illustrated by a comparison with the circles on water. The stone thrown in drives the water in all directions. The effect attains a maximum. It reacts, and, being opposed, continues under the surface. The effect goes on, culminates again, and thus the circles are repeated. If we have ever remarked the concentric rings which appear in a glass of water on trying to produce a tone by rubbing the edge, if we call to mind the intermitting pulsations in the reverberations of bells, we shall approach a conception of what may take place on the retina when the image of a luminous object impinges on it. Not to mention that as a living and elastic structure, it has already a circular principle in its organization. 99. The bright circular space which appears round the shining object is yellow, ending in red, then follows a greenish circle which is terminated by a red border. This appears to be the usual phenomenon where the luminous body is somewhat considerable in size. These halos become greater the more distant we are from the luminous object. 100. Halos may, however, appear extremely small and numerous when the impinging image is minute, yet powerful in its effect. The experiment is best made with a piece of gold leaf placed on the ground and illumined by the sun. In these cases, the halos appear in variegated rays. The iridescent appearance produced in the eye when the sun pierces through the leaves of trees seems also to belong to the same class of phenomena. End of Section 8. Recording by Kieran Metz. Section 9 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kieran Metz. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 9. Pathological Colors. Appendix 101. We are now sufficiently acquainted with the physiological colors to distinguish them from the pathological. We know what appearances belong to the eye in a healthy state and are necessary to enable the organ to exert its complete vitality and activity. 102. Morbid phenomena indicate in like manner the existence of organic and physical laws. For if a living being deviates from those rules with reference to which it is constructed, it still seeks to agree with the general vitality of nature in conformity with general laws, and throughout its whole course still proves the constancy of those principles on which the universe has existed, and by which it is held together. 103. We will here first advert to a very remarkable state in which the vision of many persons is found to be. As it presents a deviation from the ordinary mode of seeing colors, it might be fairly classed under morbid impressions. But as it is consistent in itself, as it often occurs, may extend to several members of a family, and probably does not admit of cure, we may consider it as bordering only on the nosological cases, and therefore place it first. 104. I was acquainted with 2 individuals not more than 20 years of age who were thus affected. Both had bluish-gray eyes, an acute sight for near and distant objects, by daylight and candlelight, and their mode of seeing colors was in the main quite similar. 105. They agreed with the rest of the world in denominating white, black, and gray in the usual manner. Both saw white untinged with any hue. One saw a somewhat brownish appearance in black, and in gray a somewhat reddish tinge. In general, they appeared to have a very delicate perception of the gradations of light and dark. 106. They appeared to see yellow, and yellow-red like others. In the last case, they said they saw the yellow passing as it were over the red as if glazed. Some thickly ground carmine which had dried in a saucer, they called red. 107. But now a striking difference presented itself. If the carmine was passed thinly over the white saucer, they would compare the light color thus produced to the color of the sky, and call it blue. If a rose was shown them beside it, they would, in like manner, call it blue. And in all the trials which were made, it appeared that they could not distinguish light blue from rose color. They confounded rose color, blue, and violet on all occasions. These colors only appeared to them to be distinguished from each other by delicate shades of lighter, darker, intenser, or fainter appearance. 108. Again, they could not distinguish green from dark orange, nor, more especially, from a red-brown. 109. If anyone, accidentally conversing with these individuals, happened to question them about surrounding objects, their answers occasioned the greatest perplexity, and the interrogator began to fancy his own wits were out of order. With some method we may, however, approach to a nearer knowledge of the law of this deviation from the general law. 110. These persons, as may be gathered from what has been stated, saw fewer colors than other people. Hence arose the confusion of different colors. They called the sky rose color and the rose blue, or vice versa. The question now is, did they see both blue or both rose color? Did they see green-orange or orange-green? 111. This singular enigma appears to solve itself if we assume that they saw no blue, but instead of it a light pure red, a rose color. We can comprehend what would be the result of this by means of the chromatic diagram. 112. If we take away blue from the chromatic circle, we shall miss violet and green as well. Pure red occupies the place of blue and violet, and in again mixing with yellow, the red produces orange where green should be. 113. Professing to be satisfied with this mode of explanation, we have named this remarkable deviation from ordinary vision acyanoblepsia. We have prepared some colored figures for its further elucidation, and in explaining these we shall add some further details. Among the examples will be found a landscape colored in the mode in which the individuals alluded to appear to see nature, the sky rose color, and all that should be green, varying from yellow to brown-red. nearly as foliage appears to us in autumn. 114. We now proceed to speak of morbid and other extraordinary affections of the retina, by which the eye may be susceptible of an appearance of light without external light, reserving for a future occasion the consideration of galvanic light. 115. If the eye receives a blow, sparks seem to spread from it. In some states of body, again, when the blood is heated and the system much excited, if the eye is pressed first gently and then more and more strongly, a dazzling and intolerable light may be excited. 116. If those who have been recently couched experience pain and heat in the eye, they frequently see fiery flashes and sparks. These symptoms last sometimes for a week or fortnight, or till the pain and heat diminish. 117. A person suffering from earache saw sparks and balls of light in the eye during each attack as long as the pain lasted. 118. Persons suffering from worms often experience extraordinary appearances in the eye, sometimes sparks of fire, sometimes specters of light, sometimes frightful figures, which they cannot by an effort of the will cease to see. Sometimes these appearances are double. 119. Hypochondriacs frequently see dark objects such as threads, hairs, spiders, flies, wasps. These appearances also exhibit themselves in the incipient hard cataract. Many see semi-transparent small tubes, forms like wings of insects, bubbles of water of various sizes which fall slowly down if the eye is raised. Sometimes these congregate together so as to resemble the spawn of frogs. Sometimes they appear as complete spheres, sometimes in the form of lenses. 120. As light appeared in the former instances without external light, so also these images appear without corresponding external objects. The images are sometimes transient, sometimes they last during the patient's life. Color, again, frequently accompanies these impressions. For hypochondriacs often see yellow-red stripes in the eye. These are generally more vivid and numerous in the morning or when lasting. 121. We have before seen that the impression of any object may remain for a time in the eye. This we have found to be a physiological phenomenon. The excessive duration of such an impression, on the other hand, may be considered as morbid. 122. The weaker the organ, the longer the impression of the image lasts. The retina does not so soon recover itself, and the effect may be considered as a kind of paralysis. 123. This is not to be wondered at in the case of dazzling lights. If anyone looks at the sun, he may retain the image in his eyes for several days. Boyle relates an instance of 10 years. 124. The same takes place in a certain degree with regard to objects that are not dazzling. Bush relates of himself that the image of an engraving, complete in all its parts, was impressed on his eye for 17 minutes. 125. A person inclined to fullness of blood retained the image of a bright red calico with white spots many minutes in the eye, and saw it float before everything like a veil. It only disappeared by rubbing the eye for some time. 126. Schurfer observes that the red color, which is the consequence of a powerful impression of light, may last for some hours. 127. As we can produce an appearance of light on the retina by pressure on the eyeball, so by a gentle pressure a red color appears, thus corresponding with the after-image of an impression of light. 128. Many sick persons, on awaking, see everything in the color of the morning sky, as if through a red veil. So, if in the evening they doze and wake again, the same appearance presents itself. It remains for some minutes and always disappears if the eye is rubbed a little. Red stars and balls sometimes accompany the impression. This state may last for a considerable time. 129. The aeronauts, particularly Zambacari and his companions, relate that they saw the moon blood red at the highest elevation. As they had ascended above the vapors of the earth, through which we see the moon and sun naturally of such a color, it may be suspected that this appearance may be classed with the pathological colors. The senses, namely, may be so influenced by an unusual state that the whole nervous system, and particularly the retina, may sink into a kind of inertness and inexcitability. Hence, it is not impossible that the moon might act as a very subdued light, and thus produce the impression of the red color. The sun even appeared blood red to the aeronauts of Hamburg. If those who are at some elevation in a balloon scarcely hear each other speak, may not this, too, be attributed to the inexcitable state of the nerves as well as to the thinness of the air? 130. Objects are often seen by sick persons in variegated colors. Boyle relates an instance of a lady who, after a fall by which an eye was bruised, saw all objects, but especially white objects, glittering in colors, even to an intolerable degree. 131. Physicians give the name of crypsia to an affection of the sight occurring in typhoid maladies. In these cases, the patients state that they see the boundaries of objects colored where light and dark meet. A change probably takes place in the humors of the eye, through which their achromatism is affected. 132. In cases of milky cataract, a very turbid crystalline lens causes the patient to see a red light. In a case of this kind, which was treated by the application of electricity, the red light changed by degrees to yellow and at last to white when the patient again began to distinguish objects. These changes of themselves warranted the conclusion that the turbid state of the lens was gradually approaching the transparent state. We shall be enabled easily to trace this effect to its source as soon as we become better acquainted with the physical colors. 133. If again it may be assumed that a jaundiced patient sees through an actually yellow-colored humor, we are at once referred to the department of chemical colors, and it is thus evident that we can only thoroughly investigate the chapter of pathological colors when we have made ourselves acquainted with the whole range of the remaining phenomena. What has been adduced may therefore suffice for the present, till we resume the further consideration of this portion of our subject. 134. In conclusion, we may, however, at once advert to some peculiar states or dispositions of the organ. There are painters who, instead of rendering the colors of nature, diffuse a general tone, a warm or cold hue, over the picture. In some, again, a predilection for certain colors displays itself, in others a want of feeling for harmony. 135. Lastly, it is also worthy of remark that savage nations, uneducated people, and children have a great predilection for vivid colors, that animals are excited to rage by certain colors, that people of refinement avoid vivid colors in their dress and the objects that are about them, and seem inclined to banish them altogether from their presence. End of Section 9. Recording by Kieran Metz.
Section 10 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Karen Almeida, Bern, Switzerland. Theory of Colors by Johann Wolfgang from Goethe. Translated by Charles Eastlake. Section 10. Part 2. Physical Colors. 136. We give this designation to colors which are produced by certain material mediums. These mediums, however, have no color themselves, and may be either transparent, semi-transparent, yet transmitting light, or altogether opaque. The colors in question are thus produced in the eye through such external given causes, or are merely reflected to the eye when by whatever means they are already produced without us. Although we thus ascribe to them a certain objective character, their distinctive quality still consists in their being transient and not to be arrested. 137. They are called by former investigators colores apparentes, fluxi, fugitivi, fantastici, falsi, variantes. They are also called speziosi and emfatici on account of their striking splendor. They are immediately connected with the physiological colors and appear to have but little more reality. For, while in a production of the physiological colors the eye itself was chiefly efficient, and we could only perceive the phenomena thus evoked within ourselves, but not without us, we have now to consider the fact that colors are produced in the eye by means of colorless objects, that we thus too have a colorless surface before us which is acted upon as the retina itself is, and that we can perceive the appearance produced upon it without us. In such a process, however, every observation will convince us that we have to do with colors in a progressive and mutable, but not in a final or complete state. 138. Hence, in directing our attention to these physical colors, we find it quite possible to place an objective phenomenon beside a subjective one, and often by means of the union of the two successfully to penetrate farther into the nature of the appearance. 139. Thus in the observations by which we become acquainted with the physical colors, the eye is not to be considered as acting alone, nor is the light ever to be considered in immediate relation with the eye, but we direct our attention especially to the various effects produced by mediums, those mediums being themselves colorless. 140. Light under these circumstances may be affected by three conditions. First, when it flashes back from the surface of a medium, in considering which catoptrical experiments invite our attention. Secondly, when it passes by the edge of a medium, the phenomena thus produced were formerly called perioptical. We prefer the term paroptical. Thirdly, when it passes through either a merely light-transmitting or an actually transparent body, thus constituting a class of appearances on which dioptrical experiments are founded. We have called a fourth class of physical colors epoptical, as the phenomena exhibit themselves on the colorless surface of bodies under various conditions, without previous or actual dye. 141. In examining these categories with reference to our three leading divisions, according to which we consider the phenomena of colors in a physiological, physical, or chemical view, we find that the catoptrical colors are closely connected with the physiological. The paroptical are already somewhat more distinct and independent. The dioptrical exhibit themselves as entirely and strictly physical. And as having a decidedly objective character, the epoptical, although still only apparent, may be considered as the transition to the chemical colors. 142. If we were desirous of prosecuting our investigation strictly in the order of nature, we ought to proceed according to the classification which has just been made. But in didactic treatises, it is not of so much consequence to connect as to duly distinguish the various divisions of a subject, in order that at last, when every single class and case has been presented to the mind, the whole may be embraced in one comprehensive view. We therefore turn our attention forthwith to the dioptrical class, in order at once to give the reader the full impression of the physical colors and to exhibit their characteristics the more strikingly. Section 9. Dioptrical colors. 143. Colors are called dioptrical when a colorless medium is necessary to produce them. The medium must be such that light and darkness can act through it either on the eye or on opposite surfaces. It is thus required that the medium should be transparent, or at least capable, to a certain degree, of transmitting light. 144. According to these conditions, we divide the dioptrical phenomena into two classes, placing in the first those which are produced by means of imperfectly transparent, yet light-transmitting mediums, and in the second, such as are exhibited when the medium is in the highest degree transparent. End of section 10. Section 11 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Karen Almeida, Bern, Switzerland. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 11. Section 10. Dioptrical colors of the first class. 145. Space, if we assume it to be empty, would have the quality of absolute transparency to our vision. If this space is filled so that the eye cannot perceive that it is so, there exists a more or less material transparent medium, which may be of the nature of air and gas, may be fluid or even solid. 146. The pure and light-transmitting semi-transparent medium is only in the accumulated form of the transparent medium. It may, therefore, be presented to us in three modes. 147. The extreme degree of this accumulation is white, the simplest, brightest, first opaque occupation of space. 148. Transparency itself, empirically considered, is already the first degree of the opposite state. The intermediate degrees from this point to opaque white are infinite. 149. At whatever point short of opacity we arrest the thickening medium, it exhibits simple and remarkable phenomena when placed in relation with light and darkness. 150. The highest degree of light, such as that of the sun, of phosphorus burning in oxygen, is dazzling and colorless. So the light of the fixed stars is for the most part colorless. The light, however, seen through a medium, but very slightly thickened, appears to us yellow. If the density of such a medium be increased, or if its volume become greater, we shall see the light gradually assume a yellow-red hue, which at last deepens to a ruby color. 151. If on the other hand darkness is seen through a semi-transparent medium, which is itself illumined by a light striking on it, a blue color appears. This becomes lighter and paler as the density of the medium is increased, but on the contrary appears darker and deeper the more transparent the medium becomes. In the least degree of dimness short of absolute transparence, always supposing a perfectly colorless medium, this deep blue approaches the most beautiful violet. 152. If this effect takes place in the eye as here described, and may thus be pronounced to be subjective, it remains further to convince ourselves of this by objective phenomena. For a light thus mitigated and subdued illumines all objects in like manner with a yellow, yellow-red, or red hue. And, although the effect of darkness through the non-transparent medium does not exhibit itself so powerfully, yet the blue sky displays itself in the camera obscura very distinctly on white paper, as well as every other material color. 153. In examining the cases in which this important leading phenomenon appears, we naturally mention the atmospheric colors first. Most of these may be here introduced in order. 154. The sun, seen through a certain degree of vapor, appears with a yellow disk. The center is often dazzlingly yellow when the edges are already red. The orb, seen through a thick yellow mist, appears ruby red, as was the case in 1794, even in the north. The same appearance is still more decided, owing to the state of the atmosphere when the scirocco prevails in southern climates. The clouds generally surrounding the sun in the latter case are of the same color, which is reflected again on all objects. The red hues of morning and evening are owing to the same cause. The sun is announced by a red light in shining through a greater mass of vapors. The higher he rises, the yellower and brighter the light becomes. 155. If the darkness of infinite space is seen through atmospheric vapors illumined by the daylight, the blue color appears. On high mountains the sky appears by day intensely blue, owing to the few thin vapors that float before the endless dark space. As soon as we descend in the valleys, the blue becomes lighter, till at last, in certain regions, and in consequence of increasing vapors, it altogether changes to a very pale blue. 156. The mountains, in like manner, appear to us blue, for as we see them at so great a distance that we no longer distinguish the local tints, and as no light reflected from their surface acts on our vision, they are equivalent to mere dark objects which, owing to the interposed vapors, appear blue. 157. So we find the shadowed parts of nearer objects are blue when the air is charged with thin vapors. 158. The snow mountains, on the other hand, at a great distance, still appear white, or approaching to a yellowish hue, because they act on our eyes as brightness seen through atmospheric vapor. 159. The blue appearance at the lower part of the flame of a candle belongs to the same class of phenomena. If the flame be held before a white ground, no blue will be seen, but this color will immediately appear if the flame is opposed to a black ground. This phenomena may be exhibited most strikingly with a spoonful of lighted spirits of wine. We may thus consider the lower part of the flame as equivalent to the vapor which, although infinitely thin, is still apparent before the dark surface. It is so thin that one may easily see to read through it. On the other hand, the point of the flame which conceals objects from our sight is to be considered a self-illuminating body. 160. Lastly, smoke is also to be considered as a semi-transparent medium, which appears to us yellow or reddish before a light ground, but blue before a dark one. 161. If we now turn our attention to fluid mediums, we find that water, deprived in a very slight degree of its transparency, produces the same effects. 162. The infusion of the lignum nephriticum, Guilandina lineae, which formerly excited so much attention, is only a semi-transparent liquor, which in dark wooden cups must appear blue, but held towards the sun in a transparent glass must exhibit a yellow appearance. 163. A drop of scented water, of spirit varnish, of several metallic solutions, may be employed to give various degrees of opacity to water for such experiments. Spirit of soap perhaps answers best. 164. The bottom of the sea appears to divers of a red color in bright sunshine. In this case the water, owing to its depth, acts as a semi-transparent medium. Under these circumstances, they find the shadows green, which is the complemental color. 165. Among solid mediums, the opal attracts our attention first. Its colors are at least partly to be explained by the circumstance that it is, in fact, a semi-transparent medium, through which sometimes light, sometimes dark, substrata are visible. 166. For these experiments, however, the opal glass, vitrum astroides girasol, is the most desirable material. It is prepared in various ways, and its semi-opacity is produced by metallic oxides. The same effect is produced also by melting pulverized and calcined bones together with the glass, on which account it is also known by the name of beinglas, but prepared in this mode, it easily becomes too opaque. 167. This glass may be adapted for experiments in various ways. It may either be made in a very slight degree non-transparent, in which case the light seen through various layers placed one upon the other may be deepened from the lightest yellow to the deepest red, or, if made originally more opaque, it may be employed in thinner or thicker laminae. The experiments may be successfully made in both ways. In order, however, to see the bright blue color, the glass should neither be too opaque nor too thick, for, as it is quite natural that darkness must act weakly through the semi-transparent medium, so this medium, if too thick, soon approaches whiteness. 168. Panes of glass throw a yellow light on objects through those parts where they happen to be semi-opaque, and these same parts appear blue if we look at a dark object through them. 169. Smoked glass may be also mentioned here, and is, in like manner, to be considered as a semi-opaque medium. It exhibits the sun more or less ruby-colored, and, although this appearance may be attributed to the black-brown color of the soot, we may still convince ourselves that a semi-transparent medium here acts as if we hold such a glass moderately smoked and lit by the sun on the unsmoked side before a dark object, for we shall then perceive a bluish appearance. 170. A striking experiment may be made in a dark room with sheets of parchment. If we fasten a piece of parchment before the opening in the window shutter when the sun shines, it will appear nearly white. By adding a second, a yellowish color appears, which still increases as more leaves are added, till at last it changes to red. 171. A similar effect, owing to the state of the crystalline lens in milky cataract, has been already adverted to. 172. Having now, in tracing these phenomena, arrived at the effect of a degree of opacity scarcely capable of transmitting light, we may here mention a singular appearance which was owing to a momentary state of this kind. A portrait of a celebrated theologian had been painted some years before the circumstance to which we allude, by an artist who was known to have considerable skill in the management of his materials. The very reverend individual was represented in a rich velvet dress, which was not a little admired, and which attracted the eye of the spectator almost more than the face. The picture, however, from the effect of the smoke of lamps and dust, had lost much of its original vivacity. It was therefore placed in the hands of a painter who was to clean it and give it a fresh coat of varnish. This person began his operations by carefully washing the picture with a sponge. No sooner, however, had he gone over the surface once or twice and wiped away the first dirt, than to his amazement the black velvet dress changed suddenly to a light blue plush, which gave the ecclesiastic a very secular, though somewhat old-fashioned, appearance. The painter did not venture to go on with his washing. He could not comprehend how a light blue should be the ground of the deepest black, still less how he could so suddenly have removed a glazing color capable of converting the one tint to the other. At all events, he was not a little disconcerted at having spoilt the picture to such an extent. Nothing to characterize the ecclesiastic remained but the richly curled round wig, which made the exchange of a faded plush for a handsome new velvet dress far from desirable. Meanwhile, the mischief appeared irreparable, and the good artist, having turned the picture to the wall, retired to rest with a mind ill at ease. But what was his joy the next morning, when, on examining the picture, he beheld the black velvet dress again in its full splendor. He could not refrain from again wetting a corner, upon which the blue color again appeared, and after a time vanished. On hearing of this phenomenon, I went at once to see the miraculous picture. A wet sponge was passed over it in my presence, and the change quickly took place. I saw a somewhat faded but decidedly light blue plush dress, the folds under the arm being indicated by some brown strokes. I explained this appearance to myself by the doctrine of the semi-opaque medium. The painter, in order to give additional depth to his black, may have passed some particular varnish over it. On being washed, this varnish imbibed some moisture and hence became semi-opaque, in consequence of which the black underneath immediately appeared blue. Perhaps those who are practically acquainted with the effect of varnishes may, through accident or contrivance, arrive at some means of exhibiting this singular appearance as an experiment to those who are fond of investigating natural phenomena. Notwithstanding many attempts, I could not myself succeed in reproducing it. 173. Having now traced the most splendid instances of atmospheric appearances, as well as other less striking yet sufficiently remarkable cases, to the leading examples of semi-transparent mediums, we have no doubt that attentive observers of nature will carry such researches further, and accustom themselves to trace and explain the various appearances which present themselves in everyday experience on the same principle. We may also hope that such investigators will provide themselves with an adequate apparatus in order to place remarkable facts before the eyes of others who may be desirous of information. 174. We venture, once for all, to call the leading appearance in question, as generally described in the foregoing pages, a primordial and elementary phenomenon, and we may here be permitted at once to state what we understand by the term. 175. The circumstances which come under our notice in ordinary observation are, for the most part, insulated cases, which, with some attention, admit of being classed under general leading facts. These again range themselves under theoretical rubrics which are more comprehensive and through which we become better acquainted with certain indispensable conditions of appearances in detail. From henceforth everything is gradually arranged under higher rules and laws, which, however, are not to be made intelligible by words and hypotheses to the understanding merely, but, at the same time, by real phenomena to the senses. We call these primordial phenomena because nothing appreciable by the senses lies beyond them. On the contrary, they are perfectly fit to be considered as a fixed point to which we first ascended, step by step, and from which we may, in like manner, descend to the commonest case of everyday experience. Such an original phenomena is that which has lately engaged our attention. We see on the one side light, brightness, on the other darkness, obscurity. We bring the semi-transparent medium between the two, and from these contrasts and this medium the colors develop themselves, contrasted, in like manner, but soon, through a reciprocal relation, directly tending again to a point of union. 176. With this conviction we look upon the mistake that has been committed in the investigation of this subject to be a very serious one, inasmuch as a secondary phenomenon has been thus placed higher in order. The primordial phenomenon has been degraded to an inferior place. Nay, the secondary phenomenon has been placed at the head. A compound effect has been treated as simple, a simple appearance as compound. Owing to this contradiction, the most capricious complication and perplexity have been introduced into physical inquiries, the effects of which are still apparent. 177. But when even such a primordial phenomenon is arrived at, the evil still is that we refuse to recognize it as such, that we still aim at something beyond, although it would become us to confess that we are arrived at the limits of experimental knowledge. Let the observer of nature suffer the primordial phenomena to remain undisturbed in its beauty. Let the philosopher admit it into his department, and he will find that important elementary facts are a worthier basis for further operations than insulated cases, opinions, and hypotheses. End of section 11.
Section 12 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 12. 11. Dioptrical colours of the second class. Refraction. 178. Dioptrical colours of both classes are closely connected, as will presently appear on a little examination. Those of the first class appeared through semi-transparent mediums. Those of the second class will now appear through transparent mediums. But since every substance, however transparent, may be already considered to partake of the opposite quality, as every accumulation of a medium called transparent proves, so the near affinity of the two classes is sufficiently manifest. 179. We will, however, first consider transparent mediums abstractly as such, as entirely free from any degree of opacity, and direct our whole attention to a phenomenon which here presents itself, and which is known by the name of refraction. 180. In treating of the physiological colours, we have already had occasion to vindicate what were formerly called illusions of sight, as the active energies of the healthy and duly efficient eye, and we are now again invited to consider similar instances confirming the constancy of the laws of vision. 181. Throughout nature, as presented to the senses, everything depends on the relation which things bear to each other, but especially on the relation which man, the most important of these, bears to the rest. Hence the world divides itself into two parts, and the human being as subject stands opposed to the object. Thus the practical man exhausts himself in the accumulation of facts, the thinker in speculation, each being called upon to sustain a conflict which admits of no peace and no decision. 182. But still the main point always is, whether the relations are truly seen. As our senses, if healthy, are the surest witnesses of external relations, so we may be convinced that in all instances where they appear to contradict reality, they lay the greater and surer stress on true relations. Thus a distant object appears to us smaller, and precisely by this means we are aware of distance. We produced coloured appearances on colourless objects, through colourless mediums, and at the same moment our attention was called to the degree of opacity in the medium. 183. Thus the different degrees of opacity in so-called transparent mediums, nay, even other physical and chemical properties belonging to them, are known to our vision by means of refraction, and invite us to make further trials in order to penetrate more completely by physical and chemical means into those secrets which are already opened to our view on one side. 184. Objects seen through mediums more or less transparent do not appear to us in the place which they should occupy according to the laws of perspective. On this fact the dioptrical colours of the second class depend. 185. Those laws of vision which admit of being expressed in mathematical formulae are based on the principle that, as light proceeds in straight lines, it must be possible to draw a straight line from the eye to any given object in order that it be seen. If, therefore, a case arises in which the light arrives to us in a bent or broken line, that we see the object by means of a bent or broken line, we are at once informed that the medium between the eye and the object is denser, or that it has assumed this or that foreign nature. 186. This deviation from the law of right-lined vision is known by the general term of refraction, and although we may take it for granted that our readers are sufficiently acquainted with its effects, yet we will here once more briefly exhibit it in its objective and subjective point of view. 187. Let the sun shine diagonally into an empty cubical vessel, so that the opposite side be illuminated, but not the bottom. Let water be then poured into this vessel, and the direction of the light will be immediately altered, for a part of the bottom is shone upon. At the point where the light enters the thicker medium, it deviates from its rectilinear direction, and appears broken. Hence the phenomenon is called the breaking, Brechung, or refraction. Thus much of the objective experiment. 188. We arrive at the subjective fact in the following mode. Let the eye be substituted for the sun. Let the sight be directed in like manner diagonally over one side, so that the opposite inner side be entirely seen, while no part of the bottom is visible. On pouring in water, the eye will perceive a part of the bottom, and this takes place without our being aware that we do not see in a straight line, for the bottom appears to us raised, and hence we give the term elevation, Hebung, to the subjective phenomenon. Some points which are particularly remarkable with reference to this will be adverted to hereafter. 189. Were we now to express this phenomenon generally, we might here repeat, in conformity with the view lately taken, that the relation of the objects is changed or deranged. 190. But as it is our intention at present to separate the objective from the subjective appearances, we first express the phenomenon in a subjective form and say a derangement or displacement of the object seen or to be seen takes place. 191. But that which is seen without a limiting outline may be thus affected without our perceiving the change. On the other hand, if what we look at has a visible termination, we have an evident indication that a displacement occurs. If, therefore, we wish to ascertain the relation or degree of such a displacement, we must chiefly confine ourselves to the alteration of surfaces with visible boundaries, in other words, to the displacement of circumscribed objects. 192. The general effect may take place through parallel mediums, for every parallel medium displaces the object by bringing it perpendicularly towards the eye. The apparent change of position is, however, more observable through mediums that are not parallel. 193. These latter may be perfectly spherical, or may be employed in the form of convex or concave lenses. We shall make use of all these as occasion may require in our experiments. But as they not only displace the object from its position, but alter it in various ways, we shall, in most cases, prefer employing mediums with surfaces not indeed parallel with reference to each other, but still altogether plane, namely prisms. These have a triangle for their base, and may, it is true, be considered as portions of a lens, but they are particularly available for our experiments, inasmuch as they very perceptibly displace the object from its position, without producing a remarkable distortion. 194. And now, in order to conduct our observations with as much exactness as possible, and to avoid all confusion and ambiguity, we confine ourselves at first to subjective experiments, in which, namely, the object is seen by the observer through a refracting medium. As soon as we have treated these in due series, the objective experiments will follow in similar order. End of section 12. Section 13 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 13. 12. Refraction without the appearance of colour. 195. Refraction can visibly take place without our perceiving an appearance of colour. To whatever extent a colourless or uniformly coloured surface may be altered as to its position by refraction, no colour consequent upon refraction appears within it, provided it has no outline or boundary. We may convince ourselves of this in various ways. 196. Place a glass cube on any larger surface and look through the glass perpendicularly or obliquely. The unbroken surface opposite the eye appears altogether raised, but no colour exhibits itself. If we look at a pure grey or blue sky, or a uniformly white or coloured wall through a prism, the portion of the surface which the eye thus embraces will be altogether changed as to its position, without our therefore observing the smallest appearance of colour. 13. Conditions of the appearance of colour. 197. Although in the foregoing experiments we have found all unbroken surfaces, large or small, colourless, yet at the outlines or boundaries, where the surface is relieved upon a darker or lighter object, we observe a coloured appearance. 198. Outline as well as surface is necessary to constitute a figure or circumscribed object. We therefore express the leading fact thus: circumscribed objects must be displaced by refraction in order to the exhibition of an appearance of colour. 199. We place before us the simplest object, a light disc on a dark ground. A. A displacement occurs with regard to this object if we apparently extend its outline from the centre by magnifying it. This may be done with any convex glass, and in this case we see a blue edge, B. 200. We can to appearance contract the circumference of the same light disc towards the centre by diminishing the object. The edge will then appear yellow, C. This may be done with a concave glass, which, however, should not be ground thin like common eyeglasses, but must have some substance. In order, however, to make this experiment at once with the convex glass, let a smaller black disc be inserted within the light disc on a black ground. If we magnify the black disc on a white ground with a convex glass, the same result takes place as if we diminished the white disc, for we extend the black outline upon the white, and we thus perceive the yellow edge together with the blue edge, D. 201. These two appearances, the blue and yellow, exhibit themselves in and upon the white. They both assume a reddish hue, in proportion as they mingle with the black. Plate 2. 202. In this short statement we have described the primordial phenomena of all appearance of colour occasioned by refraction. These undoubtedly may be repeated, varied, and rendered more striking, may be combined, complicated, confused, but after all may be still restored to their original simplicity. 203. In examining the process of the experiment just given, we find that in the one case we have to appearance extended the white edge upon the dark surface. In the other we have extended the dark edge upon the white surface, supplanting one by the other, pushing one over the other. We will now endeavour, step by step, to analyse these and similar cases. 204. If we cause the white disc to move in appearance entirely from its place, which can be done effectually by prisms, it will be coloured according to the direction in which it apparently moves, in conformity with the above laws. If we look at the disc A through a prism so that it appear moved to B, the outer edge will appear blue and blue-red, according to the law of the figure B, figure 1. The other edge being yellow and yellow-red, according to the law of the figure C, figure 1. For in the first case the white figure is, as it were, extended over the dark boundary, and in the other case the dark boundary is passed over the white figure. The same happens if the disc is to appearance moved from A to C, from A to D, and so throughout the circle. 205. As it is with the simple effect, so it is with more complicated appearances. If we look through a horizontal prism, AB, at a white disc placed at some distance behind it at E, the disc will be raised to F and coloured according to the above law. If we remove this prism and look through a vertical one, CD, at the same disc, it will appear at H and coloured according to the same law. If we place the two prisms one upon the other, the disc will appear displaced diagonally in conformity with a general law of nature, and will be coloured as before, that is, according to its movement in the direction. 206. If we attentively examine these opposite coloured edges, we find that they only appear in the direction of the apparent change of place. A round figure leaves us, in some degree, uncertain as to this. A quadrangular figure removes all doubt. 207. The quadrangular figure, A, moved in the direction AB or AD, exhibits no colour on the sides which are parallel with the direction in which it moves. On the other hand, if moved in the direction AC, parallel with its diagonal, all the edges of the figure appear coloured. 208. Thus a former position, 203, is here confirmed, namely, to produce colour, an object must be so displaced that the light edges be apparently carried over a dark surface, the dark edges over a light surface, the figure over its boundary, the boundary over the figure. But if the rectilinear boundaries of a figure could be indefinitely extended by refraction, so that figure and background might only pursue their course next, but not over each other, no colour would appear, not even if they were prolonged to infinity. End of section 13.
Section 14 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 14. Conditions under which the appearance of colours increases. 209. We have seen in the foregoing experiments that all appearance of colour occasioned by refraction depends on the condition that the boundary or edge be moved in upon the object itself, or the object itself over the ground, that the figure should be, as it were, carried over itself, or over the ground. And we shall now find that, by increased displacement of the object, the appearance of colour exhibits itself in a greater degree. This takes place in subjective experiments, to which, for the present, we confine ourselves under the following conditions. 210. First, if in looking through parallel mediums the eye is directed more obliquely. Secondly, if the surfaces of the medium are no longer parallel, but form a more or less acute angle. Thirdly, owing to the increased proportion of the medium, whether parallel mediums be increased in size, or whether the angle be increased, provided it does not attain a right angle. Fourthly, owing to the distance of the eye armed with a refracting medium for the object to be displaced. Fifthly, owing to a chemical property that may be communicated to the glass, and which may be afterwards increased in effect. 211. The greatest change of place, short of considerable distortion of the object, is produced by means of prisms, and this is the reason why the appearance of colour can be exhibited most powerfully through glasses of this form. Yet we will not, in employing them, suffer ourselves to be dazzled by the splendid appearances they exhibit, but keep the above well-established simple principles calmly in view. 212. The colour which is outside, or foremost, in the apparent change of an object by refraction, is always the broader, and we will henceforth call this a border. The colour that remains next the outline is the narrower, and this we will call an edge. 213. If we move a dark boundary towards a light surface, the yellow broader border is foremost, and the narrower yellow-red edge follows close to the outline. If we move a light boundary towards a dark surface, the broader violet border is foremost, and the narrower blue edge follows. 214. If the object is large, its centre remains uncoloured. Its inner surface is then to be considered as unlimited. It is displaced, but not otherwise altered. But if the object is so narrow that under the above conditions the yellow border can reach the blue edge, the space between the outlines will be entirely covered with colour. If we make this experiment with a white stripe on a black ground, the two extremes will presently meet, and thus produce green. We shall then see the following series of colours: yellow-red, yellow, green, blue, blue-red. 215. If we place a black band or stripe on white paper, the violet border will spread till it meets the yellow-red edge. In this case the intermediate black is effaced, as the intermediate white was in the last experiment, and in its stead a splendid pure red will appear. The series of colours will now be as follows: blue, blue-red, red, yellow-red, yellow. 216. The yellow and blue in the first case can by degrees meet so fully that the two colours blend entirely in green, and the order will then be yellow-red, green, blue-red. In the second case, under similar circumstances, we see only blue, red, yellow. This appearance is best exhibited by refracting the bars of a window when they are relieved on a grey sky. 217. In all this we are never to forget that this appearance is not to be considered as a complete or final state, but always as a progressive, increasing, and in many cases controllable appearance. Thus we find that, by the negation of the above 5 conditions, it gradually decreases and at last disappears altogether. End of section 14.
Section 15 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 15. Explanation of the foregoing phenomena. 218. Before we proceed further, it is incumbent on us to explain the first tolerably simple phenomenon, and to show its connection with the principles first laid down, in order that the observer of nature may be enabled clearly to comprehend the more complicated appearances that follow. 219. In the first place, it is necessary to remember that we have to do with circumscribed objects. In the act of seeing generally, it is the circumscribed visible which chiefly invites our observation. And in the present instance, in speaking of the appearance of colour, as occasioned by refraction, the circumscribed visible, the detached object solely occupies our attention. 220. For our chromatic exhibitions we can, however, divide objects generally into primary and secondary. The expressions of themselves denote what we understand by them, but our meaning will be rendered still more plain by what follows. 221. Primary objects may be considered firstly as original, as images which are impressed on the eye by things before it, and which assure us of their reality. To these the secondary images may be opposed as derived images, which remain in the organ when the object itself is taken away. Those apparent after images, which have been circumstantially treated of in the doctrine of physiological colours. 222. The primary images, again, may be considered as direct images which, like the original impressions, are conveyed immediately from the object to the eye. In contradistinction to these, the secondary images may be considered as indirect, being only conveyed to us as it were, at second hand from a reflecting surface. These are the mirrored or catoptrical images, which in certain cases can also become double images. 223. When, namely, the reflecting body is transparent, and has two parallel surfaces, one behind the other. In such a case, an image may be reflected to the eye from both surfaces, and thus arrive double images, inasmuch as the upper image does not quite cover the under one. This may take place in various ways. Let a playing card be held before a mirror. We shall at first see the distinct image of the card, but the edge of the whole card, as well as that of every spot upon it, will be bounded on one side with a border, which is the beginning of the second reflection. This effect varies in different mirrors according to the different thickness of the glass and the accidents of polishing. If a person wearing a white waistcoat with the remaining part of his dress dark stands before certain mirrors, the border appears very distinctly, and in like manner the metal buttons on dark cloth exhibit the double reflection very evidently. 224. The reader who has made himself acquainted with our former descriptions of experiments will the more readily follow the present statement. The window bars reflected by plates of glass appear double, and by increased thickness of the glass, and a due adaptation of the angle of reflection. The two reflections may be entirely separated from each other. So a vase full of water, with a plain mirror-like bottom, reflects any object twice, the two reflections being more or less separated under the same conditions. In these cases it is to be observed that, where the two reflections cover each other, the perfect vivid image is reflected, but where they are separated, they exhibit only weak, transparent, and shadowy images. 225. If we wish to know which is the under and which the upper image, we have only to take a coloured medium, for then a light object reflected from the under surface is of the colour of the medium, while that reflected from the upper surface presents the complemental colour. With dark objects it is the reverse, hence black and white surfaces may be here also conveniently employed. How easily the double images assume and evoke colours will here again be striking. 226. Thirdly, the primary images may be considered as principal images, while the secondary can be, as it were, annexed to those as accessory images. Such an accessory image produces a sort of double form, except that it does not separate itself from the principal object, although it may be said to be always endeavouring to do so. It is with secondary images of this last description that we have to do in prismatic appearances. 227. A surface without a boundary exhibits no appearance of colour when refracted. Whatever is seen must be circumscribed by an outline to produce this effect. In other words, a figure, an object, is required. This object undergoes an apparent change of place by refraction. The change is, however, not complete, not clean, not sharp, but incomplete inasmuch as an accessory image only is produced. 228. In examining every appearance of nature, but especially in examining an important and striking one, we should not remain in one spot. We should not confine ourselves to the insulated fact, nor dwell on it exclusively, but look round through all nature to see where something similar, something that has affinity to it, appears. For it is only by combining analogies that we gradually arrive at a whole which speaks for itself, and requires no further explanation. 229. Thus we here call to mind that in certain cases refraction unquestionably produces double images, as is the case in Iceland spar. Similar double images are also apparent in cases of refraction through large rock crystals, and in other instances, phenomena which have not hitherto been sufficiently observed. 230. But since in the case under consideration the question relates not to double but to accessory images, we refer to a phenomenon already adverted to but not yet thoroughly investigated. We allude to an earlier experiment in which it appeared that a sort of conflict took place in regard to the retina between a light object and its dark ground, and between a dark object and its light ground. The light object in this case appeared larger, the dark one smaller. 231. By a more exact observation of this phenomenon we may remark that the forms are not sharply distinguished from the ground, but that they appear with a kind of grey, in some degree coloured edge. In short, with an accessory image. If, then, objects seen only with the naked eye produce such effects, what may not take place when a dense medium is interposed? It is not that alone which presents itself to us in obvious operation which produces and suffers effects, but likewise all principles that have a mutual relation only of some sort are efficient accordingly, and indeed often in a very high degree. 232. Thus, when refraction produces its effect on an object that appears in accessory image next to the object itself, the real form thus refracted seems even to linger behind, as if resisting the change of place, but the accessory image seems to advance, and extends itself more or less in the mode already shown. 233. We also remark that in double images the fainter appear only half substantial, having a kind of transparent evanescent character, just as the fainter shades of double shadows must always appear as half shadows. These latter assume colours easily and produce them readily, the former also, and the same takes place in the instance of accessory images, which, it is true, do not altogether quit the real object, but still advance or extend from it as half substantial images, and hence can appear coloured so quickly and so powerfully. 234. That prismatic appearance is in fact an accessory image we may convince ourselves in more than one mode. It corresponds exactly with the form of the object itself, whether the object be bounded by a straight line or a curve, indented or waving. The form of the accessory image corresponds throughout exactly with the form of the object. 235. Again, not only the form but other qualities of the object are communicated to the accessory image. If the object is sharply relieved from its ground, like white on black, the coloured accessory image in like manner appears in its greatest force. It is vivid, distinct, and powerful, but it is most especially powerful when a luminous object is shown on a dark ground, which may be contrived in various ways. 236. But if the object is but faintly distinguished from the ground, like grey objects on black or white, or even on each other, the accessory image is also faint, and, when the original difference of tint or force is slight, becomes hardly discernible. 237. The appearances which are observable when coloured objects are relieved on light, dark, or coloured grounds are, moreover, well worthy of attention. In this case a union takes place between the apparent colour of the accessory image and the real colour of the object. A compound colour is the result, which is either assisted and enhanced by the accordance, or neutralized by the opposition of its ingredients. 238. But the common and general characteristics of both the double and accessory image is semi-transparence. The tendency of a transparent medium to become only half transparent or merely light transmitting has been before adverted to. Let the reader assume that he sees within or through such a medium a visionary image, and he will at once pronounce this latter to be a semi-transparent image. 239. Thus the colours produced by refraction may be fitly explained by the doctrine of the semi-transparent mediums. For where dark passes over light, as the border of the semi-transparent accessory image advances, yellow appears, and on the other hand, where a light outline passes over the dark background, blue appears. 240. The advancing foremost colour is always the broader. Thus the yellow spreads over the light with a broad border, but the yellow-red appears as a narrow stripe and is next the dark, according to the doctrine of augmentation, as an effect of shade. 241. On the opposite side, the condensed blue is next the edge, while the advancing border, spreading as a thinner veil over the black, produces the violet colour, precisely on the principles before explained in treating of semi-transparent mediums, principles which will hereafter be found equally efficient in many other cases. 242. Since an analysis like the present requires to be confirmed by ocular demonstration, we beg every reader to make himself acquainted with the experiments hitherto adduced, not in a superficial manner, but fairly and thoroughly. We have not placed arbitrary signs before him instead of the appearances themselves. No modes of expression are here proposed for his adoption, which may be repeated for ever without the exercise of thought and without leading any one to think. But we invite him to examine intelligible appearances which must be present to the eye and mind, in order to enable him clearly to trace these appearances to their origin, and to explain them to himself and to others. End of section 15.
Section 16 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 16. Decrease of the appearance of colour. 243. We need only take the 5 conditions under which the appearance of colour increases in the contrary order to produce the contrary or decreasing state. It may be as well, however, briefly to describe and review the corresponding modifications which are present to the eye. 244. At the highest point of complete junction of the opposite edges, the colours appear as follows: yellow-red, blue, green, red, blue-red, yellow. 245. Where the junction is less complete, the appearance is as follows: yellow-red, blue, yellow, blue-red, green, red, blue, yellow-red, blue-red, yellow. Here, therefore, the surface still appears completely coloured, but neither series is to be considered as an elementary series, always developing itself in the same manner and in the same degrees. On the contrary, they can and should be resolved into their elements, and in doing this we become better acquainted with their nature and character. 246. These elements then are yellow, red, blue, yellow, blue-red, white, black, blue, yellow-red, blue-red, yellow. Here the surface itself, the original object, which has been hitherto completely covered, and, as it were, lost, again appears in the centre of the colours, asserts its right, and enables us fully to recognise the secondary nature of the accessory images which exhibit themselves as edges and borders. 247. We can make these edges and borders as narrow as we please. Nay, we can still have refraction in reserve after having done away with all appearance of colour at the boundary of the object. Having now sufficiently investigated the exhibition of colour in this phenomenon, we repeat that we cannot admit it to be an elementary phenomenon. On the contrary, we have traced it to an antecedent and a simpler one. We have derived it, in connection with the theory of secondary images, from the primordial phenomenon of light and darkness, as affected or acted upon by semi-transparent mediums. Thus prepared, we proceed to describe the appearances which refraction produces on grey and coloured objects, and this will complete the section of subjective phenomena. Section 17. Grey objects displaced by refraction. 248. Hitherto we have confined our attention to black and white objects relieved on respectively opposite grounds, as seen through the prism, because the coloured edges and borders are most clearly displayed in such cases. We now repeat these experiments with grey objects, and again find similar results. 249. As we called black the equivalent of darkness and white the representative of light, so we now venture to say that grey represents half shadow, which partakes more or less of light and darkness, and thus stands between the two. We invite the reader to call to mind the following facts as bearing on our present view. 250. Grey objects appear lighter on a black than on a white ground. They appear as a light on a black ground, and larger, as a dark on a white ground, and smaller. 251. The darker the grey, the more it appears as a faint light on black, as a strong dark on white, and vice versa. Hence the accessory images of dark grey on black are faint, on white strong. So the accessory images of light grey on white are faint, on black strong. 252. Grey on black seen through the prism will exhibit the same appearances as white on black. The edges are coloured according to the same law, only the borders appear fainter. If we relieve grey on white, we have the same edges and borders which would be produced if we saw black on white through the prism. 253. Various shades of grey placed next each other in gradation will exhibit at their edges either blue and violet only, or red and yellow only, according as the darker grey is placed over or under. 254. A series of such shades of grey placed horizontally next each other will be coloured conformably to the same according as the whole series is relieved on a black or white ground above or below. 255. The observer may see the phenomena exhibited by the prism at one glance by enlarging the plate intending to illustrate this section. 256. It is of great importance duly to examine and consider another experiment in which a grey object is placed partly on a black and partly on a white surface, so that the line of division passes vertically through the object. 257. The colours will appear on this grey object in conformity with the usual law, but according to the opposite relation of the light to the dark, and will be contrasted in a line. For as the grey is as a light to the black, so it exhibits the red and yellow above the blue and violet below. Again, as the grey is as a dark to the white, the blue and violet appear above the red and yellow below. This experiment will be found of great importance with reference to the next chapter. End of section 16.
Section 17 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 17. 18. Coloured objects displaced by refraction. 258. An unlimited coloured surface exhibits no prismatic colour in addition to its own hue, thus not at all differing from a black, white, or grey surface. To produce the appearance of colour, light and dark boundaries must act on it, either accidentally or by contrivance. Hence experiments and observations on coloured surfaces, as seen through the prism, can only be made when such surfaces are separated by an outline from another differently tinted surface, in short, when circumscribed objects are coloured. 259. All colours, whatever they may be, correspond so far with grey that they appear darker than white and lighter than black. This shade-like quality of colour, skieron, has been already alluded to at 69, and will become more and more evident. If then we begin by placing coloured objects on black and white surfaces, and examine them through the prism, we shall again have all that we have seen exhibited with grey surfaces. 260. If we displace a coloured object by refraction, there appears, as in the case of colourless objects and according to the same laws, an accessory image. This accessory image retains, as far as colour is concerned, its usual nature, and acts on one side as a blue and blue-red, on the opposite side as a yellow and yellow-red. Hence the apparent colour of the edge and border will be either homogeneous with the real colour of the object, or not so. In the first case, the apparent image identifies itself with the real one, and appears to increase it, while in the second case the real image may be vitiated, rendered indistinct, and reduced in size by the apparent image. We proceed to review the cases in which these effects are most strikingly exhibited. 261. If we take a coloured drawing enlarged from the plate, which illustrates this experiment, and examine the red and blue squares placed next to each other on a black ground, through the prism as usual, we shall find that as both colours are lighter than the ground, similarly coloured edges and borders will appear above and below, at the outlines of both, only they will not appear equally distinct to the eye. 262. Red is proportionally much lighter on black than blue is. The colours of the edges will therefore appear stronger on the red than on the blue, which here acts as a dark grey, but little different from black. 263. The extreme red edge will identify itself with the vermilion colour of the square, which will thus appear a little elongated in this direction, while the yellow border immediately underneath it only gives the red surface a more brilliant appearance, and is not distinguished without attentive observation. 264. On the other hand, the red edge and yellow border are heterogeneous with the blue square. A dull red appears at the edge, and a dull green mingles with the figure, and thus the blue square seems, at a hasty glance, to be comparatively diminished on this side. 265. At the lower outline of the two squares a blue edge and a violet border will appear, and will produce the contrary effect, for the blue edge, which is heterogeneous with the warm red surface, will vitiate it, and produce a neutral colour, so that the red on this side appears comparatively reduced and driven upwards, and the violet border on the black is scarcely perceptible. 266. On the other hand, the blue apparent edge will identify itself with the blue square, and not only not reduce, but extend it. The blue edge and even the violet border next it have the apparent effect of increasing the surface and elongating it in that direction. 267. The effect of homogeneous and heterogeneous edges, as I have now minutely described it, is so powerful and singular that the two squares at the first glance seem pushed out of their relative horizontal position and moved in opposite directions, the red upwards, the blue downwards. But no one who is accustomed to observe experiments in a certain succession, and respectively to connect and trace them, will suffer himself to be deceived by such an unreal effect. 268. A just impression with regard to this important phenomenon will, however, much depend on some nice and even troublesome conditions, which are necessary to produce the illusion in question. Paper should be tinged with vermilion or the best minium for the red square, and with deep indigo for the blue square. The blue and red prismatic edges will then unite imperceptibly with the real surfaces, where they are respectively homogeneous. Where they are not, they vitiate the colours of the squares without producing a very distinct middle tint. The real red should not incline too much to yellow, otherwise the apparent deep red edge above will be too distinct. At the same time it should be somewhat yellow, otherwise the transition to the yellow border will be too observable. The blue must not be light, otherwise the red edge will be visible and the yellow border will produce a too decided green, while the violet border underneath would not give us the impression of being part of an elongated light blue square. 269. All this will be treated more circumstantially hereafter, when we speak of the apparatus intended to facilitate the experiments connected with this part of our subject. Every inquirer should prepare the figures himself in order fairly to exhibit this specimen of ocular deception, and at the same time to convince himself that the coloured edges, even in this case, cannot escape accurate examination. 270. Meanwhile, various other combinations, as exhibited in the plate, are fully calculated to remove all doubt on this point in the mind of every attentive observer. 271. If, for instance, we look at a white square next the blue one on a black ground, the prismatic hues of the opposite edges of the white, which here occupies the place of the red in the former experiment, will exhibit themselves in their utmost force. The red edge extends itself above the level of the blue almost in a greater degree than was the case with the red square itself in the former experiment. The lower blue edge again is visible in its full force next the white, while on the other hand it cannot be distinguished next the blue square. The violet border underneath is also much more apparent on the white than on the blue. 272. If the observer now compares these double squares, carefully prepared and arranged one above the other, the red with the white, the two blue squares together, the blue with the red, the blue with the white, he will clearly perceive the relations of these surfaces to their coloured edges and borders. 273. The edges and their relations to the coloured surfaces appear still more striking if we look at the coloured squares and a black square on a white ground, for in this case the illusion before mentioned ceases altogether, and the effect of the edges is as visible as in any case that has come under our observation. Let the blue and red squares be first examined through the prism. In both, the blue edge now appears above. This edge, homogeneous with the blue surface, unites with it and appears to extend it upwards, only the blue edge, owing to its lightness, is somewhat too distinct in its upper portion. The violet border underneath it is also sufficiently evident on the blue. The apparent blue edge is, on the other hand, heterogeneous with the red square. It is neutralized by contrast and is scarcely visible. Meanwhile, the violet border, uniting with the real red, produces a hue resembling that of the peach blossom. 274. If thus, owing to the above causes, the upper outlines of these squares do not appear level with each other, the correspondence of the under outlines is the more observable, for since both colours, the red and the blue, are darks compared with the white, as in the former case they were light compared with the black, the red edge with its yellow border appears very distinctly under both. It exhibits itself under the warm red surface in its full force, and under the dark blue nearly as it appears under the black, as may be seen if we compare the edges and borders of the figures placed one above the other on the white ground. 275. In order to present these experiments with the greatest variety and perspicuity, squares of various colours are so arranged that the boundary of the black and white passes through them vertically. According to the laws now known to us, especially in their application to coloured objects, we shall find the squares as usual doubly coloured at each edge. Each square will appear to be split in two, and to be elongated upwards or downwards. We may here call to mind the experiment with the grey figure, seen in like manner on the line of division between black and white. 257. 276. A phenomenon was before exhibited, even to illusion, in the instance of a red and blue square on a black ground. In the present experiment, the elongation upwards and downwards of two differently coloured figures is apparent in the two halves of one and the same figure of one and the same colour. Thus we are still referred to the coloured edges and borders, and to the effects of their homogeneous and heterogeneous relations with respect to the real colours of the objects. 277. I leave it to observers themselves to compare the various gradations of coloured squares, placed half on black, half on white, only inviting their attention to the apparent alteration which takes place in contrary directions. For red and yellow appear elongated upwards if on a black ground, downwards if on a white. Blue, downwards if on a black ground, upwards if on a white. All which, however, is quite in accordance with the diffusely detailed examples above given. 278. Let the observer now turn the figures so that the before-mentioned squares placed on the line of division between black and white may be in a horizontal series, the black above, the white underneath. On looking at these squares through the prism, he will observe that the red square gains by the addition of 2 red edges. On more accurate examination, he will observe the yellow border on the red figure, and the lower yellow border upon the white will be perfectly apparent. 279. The upper red edge on the blue square is on the other hand hardly visible. The yellow border next it produces a dull green by mingling with the figure. The lower red edge and the yellow border are displayed in lively colours. 280. After observing that the red figure in these cases appears to gain by an addition on both sides, while the dark blue on one side at least loses something, we shall see the contrary effect produced by turning the same figures upside down, so that the white ground be above, the black below. 281. For as the homogeneous edges and borders now appear above and below the blue square, this appears elongated, and a portion of the surface itself seems even more brilliantly coloured. It is only by attentive observation that we can distinguish the edges and borders from the colour of the figure itself. 282. The yellow and red squares, on the other hand, are comparatively reduced by the heterogeneous edges in this position of the figures, and their colours are, to a certain extent, vitiated. The blue edge in both is almost invisible. The violet border appears as a beautiful peach blossom hue on the red, as a very pale colour of the same kind on the yellow. Both the lower edges are green, dull on the red, vivid on the yellow. The violet border is but faintly perceptible under the red, but is more apparent under the yellow. 283. Every inquirer should make it a point to be thoroughly acquainted with all the appearances here adduced, and not consider it irksome to follow out a single phenomenon through so many modifying circumstances. These experiments, it is true, may be multiplied to infinity by differently coloured figures, upon and between differently coloured grounds. Under all such circumstances, however, it will be evident to every attentive observer that coloured squares only appear relatively altered, or elongated, or reduced by the prism, because an addition of homogeneous or heterogeneous edges produces an illusion. The inquirer will now be enabled to do away with this illusion if he has the patience to go through the experiments one after the other, always comparing the effects together, and satisfying himself of their correspondence. Experiments with coloured objects might have been contrived in various ways. Why they have been exhibited precisely in the above mode, and with so much minuteness, will be seen hereafter. The phenomena, although formerly not unknown, were much misunderstood, and it was necessary to investigate them thoroughly to render some portions of our intended historical view clearer. 284. In conclusion, we will mention a contrivance by means of which our scientific readers may be enabled to see these appearances distinctly at one view, and even in their greatest splendour. Cut in a piece of pasteboard 5 perfectly similar square openings of about an inch next each other, exactly in a horizontal line. Behind these openings place 5 coloured glasses in the natural order orange, yellow, green, blue, violet. Let the series thus adjusted be fastened in an opening of the camera obscura, so that the bright sky may be seen through the squares, or that the sun may shine on them. They will thus appear very powerfully coloured. Let the spectator now examine them through the prism, and observe the appearances, already familiar by the foregoing experiments, with coloured objects, namely, the partly assisting, partly neutralizing effects of the edges and borders, and the consequent apparent elongation or reduction of the coloured squares with reference to the horizontal line. The results witnessed by the observer in this case entirely correspond with those in the cases before analysed. We do not therefore go through them again in detail, especially as we shall find frequent occasions hereafter to return to the subject. Footnote: the earnestness and pertinacity with which Goethe insisted that the different colours are not subject to different degrees of refrangibility are at least calculated to prove that he was himself convinced on the subject, and however extraordinary it may seem, his conviction appears to have been the result of infinite experiments and the fullest ocular evidence. He returns to the question in the controversial division of his work, in the historical part, and again in the description of the plates. In the first he endeavours to show that Newton's experiment with the blue and red paper depends entirely on the colours being so contrived as to appear elongated or curtailed by the prismatic borders. If, he says, we take a light blue instead of a dark one, the illusion in the latter case is at once evident. According to the Newtonian theory, the yellow-red, red, is the least refrangible colour, the violet the most refrangible. Why then does Newton place a blue paper instead of a violet next the red? If the fact were as he states it, the difference in the refrangibility of the yellow-red and violet would be greater than in the case of the yellow-red and blue. But here comes in the circumstance that a violet paper conceals the prismatic borders less than a dark blue paper, as every observer may now easily convince himself, and so on. Polemischer Teil, paragraph 45. De Saguière, in repeating the experiment, confessed that if the ground of the colours was not black, the effect did not take place so well. Goethe adds, not only not so well, but not at all. Historischer Teil, page 459. Lucas of Lüttich, one of Newton's first opponents, denied that two differently coloured silks are different in distinctness when seen in the microscope. Another experiment proposed by him, to show the unsoundness of the doctrine of various refrangibility, was the following: that a tin plate painted with the prismatic colours in stripes be placed in an empty cubical vessel, so that from the spectator's point of view the colours may be just hidden by the rim. On pouring water into this vessel, all the colours become visible in the same degree, whereas, it was contended, if the Newtonian doctrine were true, some colours would be apparent before others. Historischer Teil, page 434. Such are the arguments and experiments adduced by Goethe on this subject. They have all probably been answered. In his analysis of Newton's celebrated Experimentum Crucis, he shows again that by reversing the prismatic colours, refracting a dark instead of a light object, the colours that are the most refrangible in Newton's experiment become the least so, and vice versa. Without reference to this objection, it is now admitted that the difference of colour is not a test of difference of refrangibility, and the conclusion deduced by Newton is no longer admissible as a general truth, that to the same degree of refrangibility ever belongs the same colour, and to the same colour ever belongs the same degree of refrangibility. Brewster's Optics, page 72. End of footnote. End of section 17.
Section 18 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 18. Part 19. Achromatism and Hyperchromatism. 285. Formerly, when much that is regular and constant in nature was considered as mere aberration and accident, the colours arising from refraction were but little attended to, and were looked upon as an appearance attributable to particular local circumstances. 286. But after it had been assumed that this appearance of colour accompanies refraction at all times, it was natural that it should be considered as intimately and exclusively connected with that phenomenon, the belief obtaining that the measure of the coloured appearance was in proportion to the measure of the refraction, and that they must advance pari passu with each other. 287. If, again, philosophers ascribe the phenomenon of a stronger or weaker refraction, not indeed wholly, but in some degree, to the different density of the medium, as pure atmospheric air, air charged with vapors, water, glass, according to their increasing density, increase the so-called refraction, or displacement of the object, so they could hardly doubt that the appearance of color must increase in the same proportion, and hence took it for granted, in combining different mediums which were to counteract refraction, that as long as refraction existed, the appearance of color must take place, and that as soon as the color disappeared, the refraction also must cease. 288. Afterwards it was, however, discovered that this relation which was assumed to correspond was in fact dissimilar, that two mediums can refract an object with equal power, and yet produce very dissimilar colored borders. 289. It was found that in addition to the physical principle to which refraction was ascribed, a chemical one was also to be taken into the account. We propose to pursue this subject hereafter in the chemical division of our inquiry, and we shall have to describe the particulars of this important discovery in our history of the doctrine of colors. What follows may suffice for the present. 290. In mediums of similar or nearly similar refracting power, we find the remarkable circumstance that a greater and lesser appearance of color can be produced by a chemical treatment. The greater effect is owing, namely, to acids, the lesser to alkalis. If metallic oxides are introduced into a common mass of glass, the colored appearance through such glasses becomes greatly increased without any perceptible change of refracting power. That the lesser effect, again, is produced by alkalis may be easily supposed. 291. Those kinds of glass which were first employed after the discovery are called flint and crown glass. The first produces the stronger, the second the fainter appearance of color. 292. We shall make use of both these denominations as technical terms in our present statement, and assume that the refractive power of both is the same, but that flint glass produces the colored appearance more strongly by 1/3 than the crown glass. The diagram, Plate 3, Fig. 2, may serve in illustration. 293. A black surface is here divided into compartments for more convenient demonstration. Let the spectator imagine 5 white squares between the parallel lines A, B, and C, D. The square number 1 is presented to the naked eye unmoved from its place. 294. But let the square number 2, seen through a crown glass prism, G, be supposed to be displaced by refraction 3 compartments, exhibiting the colored borders to a certain extent. Again, let the square number 3, seen through a flint glass prism, H, in like manner be moved downwards 3 compartments, when it will exhibit the colored borders by about 1/3 wider than number 2. 295. Again, let us suppose that the square number 4 has, like number 2, been moved downwards 3 compartments by a prism of crown glass, and that then, by an oppositely placed prism H of flint glass, it has been again raised to its former situation where it now stands. 296. Here, it is true, the refraction is done away with by the opposition of the two, but as the prism H, in displacing the square by refraction through 3 compartments, produces colored borders wider by 1/3 than those produced by the prism G, so, notwithstanding the refraction is neutralized, there must be an excess of colored border remaining. The position of this color, as usual, depends on the direction of the apparent motion, 204, communicated to the square by the prism H, and, consequently, it is the reverse of the appearance in the 2 squares 2 and 3, which have been moved in an opposite direction. This excess of color we have called hyperchromatism, and from this the achromatic state may be immediately arrived at. 297. For assuming that it was the square number 5 which was removed 3 compartments from its first supposed place, like number 2, by a prism of crown glass G, it would only be necessary to reduce the angle of a prism of flint glass H, and to connect it, reversed, to the prism G, in order to raise the square number 5 2 degrees, or compartments, by which means the hyperchromatism of the first case would cease, the figure would not quite return to its first position, and yet be already colorless. The prolonged lines of the united prisms under number 5 show that a single complete prism remains. Again, we have only to suppose the lines curved, and an object glass presents itself. Such is the principle of the achromatic telescopes. 298. For these experiments, a small prism, composed of 3 different prisms as prepared in England, is extremely well adapted. It is to be hoped our own opticians will in future enable every friend of science to provide himself with this necessary instrument. Part 20. Advantages of subjective experiments. Transition to the objective. 299. We have presented the appearances of color as exhibited by refraction, first by means of subjective experiments, and we have so far arrived at a definite result that we have been enabled to deduce the phenomena in question from the doctrine of semi-transparent mediums and double images. 300. In statements which have reference to nature, everything depends on ocular inspection, and these experiments are the more satisfactory as they may be easily and conveniently made. Every amateur can procure his apparatus without much trouble or cost, and if he is a tolerable adept in pasteboard contrivances, he may even prepare a great part of his machinery himself. A few plain surfaces on which black, white, gray, and colored objects may be exhibited alternately on a light and dark background, are all that is necessary. The spectator fixes them before him, examines the appearances at the edge of the figures conveniently, and as long as he pleases. He retires to a greater distance, again approaches, and accurately observes the progressive states of the phenomena. 301. Besides this, the appearances may be observed with sufficient exactness through small prisms, which need not be of the purest glass. The other desirable requisites in these glass instruments will, however, be pointed out in the section which treats of the apparatus. Footnote: this description of the apparatus was never given. End footnote. 302. A great advantage in these experiments again is that they can be made at any hour of the day in any room, whatever aspect it may have. We have no need to wait for sunshine, which in general is not very propitious to northern observers. Objective experiments. 303. The objective experiments, on the contrary, necessarily require the sunlight which, even when it is to be had, may not always have the most desirable relation with the apparatus placed opposite to it. Sometimes the sun is too high, sometimes too low, and withal only a short time in the meridian of the best situated room. It changes its direction during the observation. The observer is forced to alter his own position, and that of his apparatus, in consequence of which the experiments in many cases become uncertain. If the sun shines through the prism, it exhibits all inequalities, lines, and bubbles in the glass, and thus the appearance is rendered confused, dim, and discolored. 304. Yet both kinds of experiments must be investigated with equal accuracy. They appear to be opposed to each other, and yet are always parallel. What one order of experiments exhibits, the other exhibits likewise, and yet each has its peculiar capabilities, by means of which certain effects of nature are made known to us in more than one way. 305. In the next place, there are important phenomena which may be exhibited by the union of subjective and objective experiments. The latter experiments again have this advantage, that we can in most cases represent them by diagrams, and present to view the component relations of the phenomena. In proceeding, therefore, to describe the objective experiments, we shall so arrange them that they may always correspond with the analogous subjective examples. For this reason, too, we annex to the number of each paragraph the number of the former corresponding one. But we set out by observing generally that the reader must consult the plates, that the scientific investigator must be familiar with the apparatus, in order that the twin phenomena in one mode or the other may be placed before them. End of section 18. Recording by Philip Gould. Section 19 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 21. Refraction without the appearance of color. 306, 195, 196. That refraction may exhibit its effects without producing an appearance of color is not to be demonstrated so perfectly in objective as in subjective experiments. We have, it is true, unlimited spaces which we can look at through the prism, and thus convince ourselves that no color appears where there is no boundary. But we have no unlimited source of light which we can cause to act through the prism. Our light comes to us from circumscribed bodies, and the sun, which chiefly produces our prismatic appearances, is itself only a small circumscribed luminous object. 307. We may, however, consider every larger opening through which the sun shines, every larger medium through which the sunlight is transmitted and made to deviate from its course, as so far unlimited that we can confine our attention to the center of the surface without considering its boundaries. 308. 197. If we place a large water prism in the sun, a large bright space is refracted upwards by it on the plane intended to receive the image, and the middle of this illumined space will be colorless. The same effect may be produced if we make the experiment with glass prisms having angles of few degrees. The appearance may be produced even through glass prisms whose refracting angle is 60 degrees, provided we place the recipient surface near enough. Section 22. Conditions of the appearance of color. 309, 198. Although then the illumined space before mentioned appears indeed refracted and moved from its place, but not colored, yet on the horizontal edges of this space we observe a colored appearance. That here again the color is solely owing to the displacement of a circumscribed object may require to be more fully proved. The luminous body which here acts is circumscribed. The sun, while it shines and diffuses light, is still an insulated object. However small the opening in the lid of a camera obscura be made, still the whole image of the sun will penetrate it. The light which streams from all parts of the sun's disk will cross itself in the smallest opening, and form the angle which corresponds with the sun's apparent diameter. On the outside we have a cone narrowing to the orifice. Within, this apex spreads again, producing on an opposite surface a round image, which still increases in size in proportion to the distance of the recipient surface from the apex. This image, together with all other objects of the external landscape, appears reversed on the white surface in question in a dark room. 310. How little, therefore, we have here to do with single sun rays, bundles or fasces of rays, cylinders of rays, pencils, or whatever else of the kind may be imagined, is strikingly evident. For the convenience of certain diagrams, the sunlight may be assumed to arrive in parallel lines. But it is known that this is only a fiction quite allowable where the difference between the assumption and the true appearance is unimportant. But we should take care not to suffer such a postulate to be equivalent to a fact, and proceed to further operations on such a fictitious basis. 311. Let the aperture in the window shutter be now enlarged at pleasure. Let it be made round or square. Nay, let the whole shutter be opened, and let the sun shine into the room through the whole window. The space which the sun illumines will always be larger according to the angle which its diameter makes, and thus even the whole space illumined by the sun through the largest window is only the image of the sun plus the size of the opening. We shall hereafter have occasion to return to this. 312, 199. If we transmit the image of the sun through convex glasses, we contract it towards the focus. In this case, according to the laws before explained, a yellow border and a yellow-red edge must appear when the spectrum is thrown on white paper. But as this experiment is dazzling and inconvenient, it may be made more agreeably with the image of the full moon. On contracting this orb by means of a convex glass, the colored edge appears in the greatest splendor, for the moon transmits a mitigated light in the first instance, and can thus the more readily produce color which to a certain extent accompanies the subduing of light. At the same time, the eye of the observer is only gently and agreeably excited. 313 (200). If we transmit a luminous image through concave glasses, it is dilated. Here the image appears edged with blue. 314. The two opposite appearances may be produced by a convex glass simultaneously or in succession. Simultaneously by fastening an opaque disc in the center of the convex glass, and then transmitting the sun's image. In this case the luminous image and the black disc within it are both contracted, and, consequently, the opposite colors must appear. Again, we can present this contrast in succession by first contracting the luminous image towards the focus, and then suffering it to expand again beyond the focus, when it will immediately exhibit a blue edge. 315 (201). Here, too, what was observed in the subjective experiments is again to be remarked, namely, that blue and yellow appear in and upon the white, and that both assume a reddish appearance in proportion as they mingle with the black. 316 (202, 203). These elementary phenomena occur in all subsequent objective experiments, as they constituted the groundwork of the subjective ones. The process, too, which takes place is the same. A light boundary is carried over a dark surface. A dark surface is carried over a light boundary. The edges must advance, and, as it were, push over each other in these experiments as in the former ones. 317 (204). If we admit the sun's image through a larger or smaller opening into the dark room, if we transmit it through a prism so placed that its refracting angle as usual is underneath, the luminous image, instead of proceeding in a straight line to the floor, is refracted upwards on a vertical surface placed to receive it. This is the moment to take notice of the opposite modes in which the subjective and objective refractions of the object appear. 318. If we look through a prism held with its refracting angle underneath at an object above us, the object is moved downwards, whereas a luminous image refracted through the same prism is moved upwards. This, which we here merely mention as a matter of fact for the sake of brevity, is easily explained by the laws of refraction and elevation. 319. The luminous object being moved from its place in this manner, the colored borders appear in the order and according to the laws before explained. The violet border is always foremost, and thus in objective cases proceeds upwards, in subjective cases downwards. 320 (205). The observer may convince himself in like manner of the mode in which the appearance of color takes place in the diagonal direction when the displacement is effected by means of two prisms, as has been plainly enough shown in the subjective example. For this experiment, however, prisms should be procured of few degrees, say about 15. 321 (206, 207). That the coloring of the image takes place here too, according to the direction in which it moves, will be apparent if we make a square opening of moderate size in a shutter, and cause the luminous image to pass through a water prism. The spectrum being moved first in the horizontal and vertical directions, then diagonally, the colored edges will change their position accordingly. 322 (208). Whence it is again evident that to produce color the boundaries must be carried over each other, not merely moved side by side. End of section 19. Recording by Philip Gould. Section 20 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 23. Conditions of the increase of color. 323 (209). Here, too, an increased displacement of the object produces a greater appearance of color. 324 (210). This increased displacement occurs 1. By a more oblique direction of the impinging luminous object through mediums with parallel surfaces. 2. By changing the parallel form for one more or less acute angled. 3. By increased proportion of the medium, whether parallel or acute angled, partly because the object is by this means more powerfully displaced, partly because an effect depending on the mirror mass cooperates. 4. By the distance of the recipient surface from the refracting medium, so that the colored spectrum emerging from the prism may be said to have a longer way to travel. 5. When a chemical property produces its effects under all these circumstances. This we have already entered into more fully under the head of achromatism and hyperchromatism. 325 (211). The objective experiments have this advantage, that the progressive states of the phenomenon may be arrested and clearly represented by diagrams, which is not the case with the subjective experiments. 326. We can observe the luminous image after it has emerged from the prism step by step, and mark its increasing color by receiving it on a plane at different distances, thus exhibiting before our eyes various sections of this cone with an elliptical base. Again, the phenomenon may at once be rendered beautifully visible throughout its whole course in the following manner. Let a cloud of fine white dust be excited along the line in which the image passes through the dark space. The cloud is best produced by fine, perfectly dry hair powder. The more or less colored appearance will now be painted on the white atoms, and presented in its whole length and breadth to the eye of the spectator. 327. By this means we have prepared some diagrams which will be found among the plates. In these the appearance is exhibited from its first origin, and by these the spectator can clearly comprehend why the luminous image is so much more powerfully colored through prisms than through parallel mediums. 328 (212). At the two opposite outlines of the image an opposite appearance presents itself beginning from an acute angle. The appearance spreads as it proceeds further in space according to this angle. On one side, in the direction in which the luminous image is moved, a violet border advances on the dark, a narrower blue edge remains in the next outline of the image. On the opposite side a yellow border advances into the light of the image itself, and a yellow-red edge remains at the outline. 329 (213). Here, therefore, the movement of the dark against the light, of the light against the dark, may be clearly observed. 330 (214). The center of a large object remains long uncolored, especially with mediums of less density and smaller angles. But at last the opposite borders and edges touch each other, upon which a green appears in the center of the luminous image. 331 (215). Objective experiments have been usually made with the sun's image. An objective experiment with a dark object has hitherto scarcely been thought of. We have, however, prepared a convenient contrivance for this also. Let the large water prism before alluded to be placed in the sun, and let a round pasteboard disc be fastened either inside or outside. The colored appearance will again take place at the outline, beginning according to the usual law. The edges will appear, they will spread in the same proportion, and when they meet, red will appear in the center. An intercepting square may be added near the round disc, and placed in any direction ad libitum, and the spectator can again convince himself of what has been before so often described. 332 (216). If we take away these dark objects from the prism, in which case, however, the glass is to be carefully cleaned, and hold a rod or a large pencil before the center of the horizontal prism, we shall then accomplish the complete immixture of the violet border and the yellow-red edge, and see only the three colors, the external blue and yellow, and the central red. 333. If again we cut a long horizontal opening in the middle of a piece of pasteboard, fastened on the prism, and then cause the sunlight to pass through it, we shall accomplish the complete union of the yellow border with the blue edge upon the light, and only see yellow-red, green, and violet. The details of this are further entered into in the description of the plates. 334 (217). The prismatic appearance is thus by no means complete and final when the luminous image emerges from the prism. It is then only that we perceive its elements in contrast, for as it increases, these contrasting elements unite and are at last intimately joined. The section of this phenomenon arrested on a plane surface is different at every angle of distance from the prism, so that the notion of an immutable series of colors, or of a pervading similar proportion between them, cannot be a question for a moment. Section 24. Explanation of the foregoing phenomena. 335-218. As we have already entered into this analysis circumstantially while treating of the subjective experiments, as all that was of force there is equally valid here, it will require no long details in addition to show that the phenomena, which are entirely parallel in the two cases, may also be traced precisely to the same sources. 336-219. That in objective experiments also we have to do with circumscribed images has already been demonstrated at large. The sun may shine through the smallest opening, yet the image of the whole disk penetrates beyond. The largest prism may be placed in the open sunlight, yet it is still the sun's image that is bounded by the edges of the refracting surfaces, and produces the accessory images of this boundary. We may fasten pasteboard with many openings cut in it before the water prism, yet we still merely see multiplied images which, after having been moved from their place by refraction, exhibit colored edges and borders, and in these mere accessory images. 337-235. In subjective experiments we have seen that objects strongly relieved from each other produce a very lively appearance of color, and this will be the case in objective experiments in a much more vivid and splendid degree. The sun's image is the most powerful brightness we know. Hence its accessory image will be energetic in proportion, and notwithstanding its really secondary dimmed and darkened character, must still be very brilliant. The colors thrown by the sunlight through the prism on any object carry a powerful light with them, for they have the highest and most intense source of light, as it were, for their ground. 338. That we are warranted in calling even these accessory images semi-transparent, thus deducing the appearances from the doctrine of the semi-transparent mediums, we will be clear to everyone who has followed us thus far, but particularly to those who have supplied themselves with the necessary apparatus, so as to be enabled at all times to witness the precision and vivacity with which semi-transparent mediums act. End of section 20. Recording by Philip Gould.
Section 21 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Catherine. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 21, Part 25. Decrease of the appearance of color. 339. If we could afford to be concise in the description of the decreasing colored appearance in subjective cases, we may here be permitted to proceed with still greater brevity while we refer to the former distinct statement. One circumstance, only on account of its great importance, may be here recommended to the reader's special attention as a leading point of our whole thesis. 340. The decline of the prismatic appearance must be preceded by its separation, by its resolution into its elements. At the due distance from the prism, the image of the sun being entirely colored, the blue and yellow at length mix completely, and we see only yellow-red, green, and blue-red. If we bring the recipient surface nearer to the refracting medium, yellow and blue appear again, and we see the 5 colors with their gradations. At a still shorter distance, the yellow and blue separate from each other entirely. The green vanishes, and the image itself appears, colorless, between the colored edges and borders. The nearer we bring the recipient surface to the prism, the narrower the edges and borders become, till at last, when in contact with the prism, they are reduced to nothing. Part 26. Gray Objects. 341. We have exhibited gray objects as very important to our inquiry in the subjective experiments. They show, by the faintness of the accessory images, that these same images are in all cases derived from the principal object. We wish here, too, to carry on the objective experiments parallel with the others. We may conveniently do this by placing a more or less dull ground glass before the opening through which the sun's image enters. By this means a subdued image would be produced, which on being refracted would exhibit much duller colors on the recipient plane than those immediately derived from the sun's disk, and thus, even from the intense sun image, only a faint accessory image would appear, proportioned to the mitigation of the light by the glass. This experiment, it is true, will only again and again confirm what is already sufficiently familiar to us. Part 27. Colored Objects 342. There are various modes of producing colored images in objective experiments. In the first place, we can fix colored glass before the opening, by which means a colored image is at once produced. Secondly, we can fill the water prism with colored fluids. Thirdly, we can cause the colors already produced in their full vivacity by the prism to pass through proportionate small openings in a thin plate, and thus prepare small circumscribed colors for a second operation. This last mode is the most difficult, for owing to the continual progress of the sun, the image cannot be arrested in any direction at will. The second method has also its inconveniences, since not all colored liquids can be prepared perfectly bright and clear. On these accounts, the first is to be preferred, and deserves the more to be adopted, because natural philosophers have hitherto chosen to consider the colors produced from the sunlight through the prism, those produced through liquids and glasses, and those which are already fixed on paper or cloth, as exhibiting effects equally to be depended on, and equally available in demonstration. 343. As it is thus merely necessary that the image should be colored, so the large water prism before alluded to affords us the best means of effecting this. A pasteboard screen may be contrived to slide before the large surfaces of the prism, through which, in the first instance, the light passes uncolored. In this screen openings of various forms may be cut, in order to produce different images, and consequently different accessory images. This being done, we need only fix colored glasses before the openings, in order to observe what effect refraction produces on colored images in an objective sense. 344. A series of glasses may be prepared in a mode similar to that before described. These should be accurately contrived to slide in the grooves of the large water prism. Let the sun then shine through them, and the colored images refracted upwards will appear bordered and edged, and will vary accordingly. For these borders and edges will be exhibited quite distinctly on some images, and on others will be mixed with the specific color of the glass, which they will either enhance or neutralize. Every observer will be enabled to convince himself here again that we have only to do with the same simple phenomenon, so circumstantially described subjectively and objectively. Part 28. Achromatism and hyperchromatism 345. It is possible to make the hyperchromatic and achromatic experiments objectively as well as subjectively. After what has been already stated, a short description of the method will suffice, especially as we take it for granted that the compound prism before mentioned is in the hands of the observer. 346. Let the sun's image pass through an acute-angled prism of few degrees, prepared from crown glass, so that the spectrum be refracted upwards on an opposite surface. The edges will appear colored according to the constant law, namely the violet and blue above and outside, the yellow and yellow-red below and within the image. As the refracting angle of this prism is undermost, let another proportionate prism of flint glass be placed against it, with its refracting angle uppermost. The sun's image will by this means be again moved to its place, where, owing to the excess of the coloring power of the prism of flint glass, it will still appear a little colored, and, in consequence of the direction in which it has been moved, the blue and violet will now appear underneath and outside, the yellow and yellow-red above and inside. 347. If the whole image be now moved a little upwards by a proportionate prism of crown glass, the hypochromatism will disappear, the sun's image will be moved from its place and yet will appear colorless. 348. With an achromatic object glass composed of 3 glasses, this experiment may be made step by step, if we do not mind taking out the glasses from their setting. The 2 convex glasses of crown glass in contracting the sun's image towards the focus, the concave glass of flint glass in dilating the image beyond it, exhibit at the edges the usual colors. A convex glass united with a concave one exhibits the colors according to the law of the latter. If all 3 glasses are placed together, whether we contract the sun's image towards the focus or suffer it to dilate beyond the focus, colored edges never appear, and the achromatic effect intended by the optician is, in this case, again attained. 349. But as the crown glass has always a greenish tint, and as a tendency to this hue may be more decided in large and strong object glasses, and under certain circumstances produce the compensatory red, which, however, in repeated experiments with several instruments of this kind did not occur to us, philosophers have resorted to the most extraordinary modes of explaining such a result, and having been compelled, in support of their system, theoretically to prove the impossibility of achromatic telescopes, have felt a kind of satisfaction in having some apparent ground for denying so great an improvement. Of this, however, we can only treat circumstantially in our historical account of these discoveries. End of section 21. Recording by Catherine.
Section 22 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Simona Rusu. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 22. Combination of subjective and objective experiments. 350. Having shown above, 318, that refraction considered objectively and subjectively must act in opposite directions, it will follow that if we combine the experiments, the effects will reciprocally destroy each other. 351. Let the sun's image be thrown upwards on a vertical plane through a horizontally placed prism. If the prism is long enough to admit of the spectator also looking through it, he will see the image elevated by the objective refraction again depressed, and in the same place in which it appeared without refraction. 352. Here a remarkable case presents itself, but at the same time a natural result of a general law. For since, as often before stated, the objective sun's image thrown on the vertical plane is not an ultimate or unchangeable state of the phenomenon, so in the above operation the image is not only depressed when seen through the prism, but its edges and borders are entirely robbed of their hues, and the spectrum is reduced to a colorless circular form. 353. By employing two perfectly similar prisms placed next each other, for this experiment we can transmit the sun's image through one, and look through the other. 354. If the spectator advances nearer with the prism through which he looks, the image is again elevated, and by degrees becomes colored according to the law of the first prism. If he again retires till he has brought the image to the neutralized point, and then retires still further away, the image, which had become round and colorless, moves still more downwards and becomes colored in the opposite sense, so that if we look through the prism and upon the refracted spectrum at the same time, we see the same image colored according to subjective and objective laws. 355. The modes in which this experiment may be varied are obvious. If the refracting angle of the prism, through which the sun's image was objectively elevated, is greater than that of the prism through which the observer looks, he must retire to a much greater distance in order to depress the colored image so low on the vertical plane that it shall appear colorless, and vice versa. 356. It will be easily seen that we may exhibit achromatic and hyperchromatic effects in a similar manner, and we leave it to the amateur to follow out such researches more fully. Other complicated experiments in which prisms and lenses are employed together, others again in which objective and subjective experiments are variously intermixed, we reserve for a future occasion, when it will be our object to trace such effects to the simple phenomena with which you are now sufficiently familiar. Chapter 30. Transition. 357. In looking back on the description and analysis of dioptrical colors, we do not repent either that we have treated them so circumstantially, or that we have taken them into consideration before the other physical colors, out of the order we ourselves laid down. Yet before we quit this branch of our inquiry, it may be as well to state the reasons that we have weighed with us. 358. If some apology is necessary for having treated the theory of the dioptrical colors, particularly those of the second class, so diffusely, we should observe that the exposition of any branch of knowledge is to be considered, partly with reference to the intrinsic importance of the subject, and partly with reference to the particular necessities of the time in which the inquiry is undertaken. In our own case, we were forced to keep both these considerations constantly in view. In the first place, we had to state a mass of experiments with our consequent convictions. Next, it was our special aim to exhibit certain phenomena, known, it is true, but misunderstood, and above all exhibited in false connection, in that natural and progressive development which is strictly and truly conformable to observation, in order that hereafter, in our polemical or historical investigations, we might be enabled to bring a complete preparatory analysis to bear on, and elucidate our general view. The details we have entered into were on this account unavoidable. They may be considered as a reluctant consequence of the occasion. Hereafter, when philosophers will look upon a simple principle as simple, a combined effect as combined, when they will acknowledge the first elementary and the second complicated states for what they are, then indeed all this statement may be abridged to a narrower form, a labour which, should we ourselves not be able to accomplish it, we bequeath to the active interest of contemporaries and posterity. 359. With respect to the order of the chapters, it should be remembered that natural phenomena, which are even allied to each other, are not connected in any particular sequence or constant series. Their efficient causes act in a narrow circle, so that it is in some sort indifferent what phenomenon is first or last considered. The main point is that all should be as far as possible present to us, in order that we may embrace them at last from one point of view, partly according to their nature, partly according to generally received methods. 360. Yet in the present particular instance it may be asserted that the dioptrical colours are justly placed at the head of the physical colours, not only on account of their striking splendour and their importance in other respects, but because, in tracing these to their source, much was necessarily entered into which will assist our subsequent inquiries. 361. For hitherto light has been considered as a kind of abstract principle, existing and acting independently, to a certain extent self-modified, and on the slightest cause producing colours out of itself. To divert the votaries of physical science from this mode of viewing the subject, to make them attentive to the fact that in prismatic and other appearances we have not to do with light as an uncircumscribed and modifying principle, but as circumscribed and modified, that we have to do with a luminous image, with images or circumscribed objects generally, whether light or dark. This was the purpose we had in view, and such is the problem to be solved. 362. All that takes place in dioptrical cases, especially those of the second class, which are connected with the phenomena of refraction, is now sufficiently familiar to us, and will serve as an introduction to what follows. 363. Catoptrical appearances remind us of the physiological phenomena, but as we ascribe a more objective character to the former, we thought ourselves justified in classing them with the physical examples. It is of importance, however, to remember that here again it is not light in an abstract sense, but a luminous image that we have to consider. 364. In proceeding onwards to the paroptical class, the reader, if duly acquainted with the foregoing facts, will be pleased to find himself once more in the region of circumscribed forms. The shadows of bodies, especially as secondary images, so exactly accompanying the object, will serve greatly to elucidate analogous appearances. 365. We will not, however, anticipate these statements, but proceed as heretofore in what we consider the regular course. End of section 22. Section 23 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Simona Rusu. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 23. Chapter 31. Catoptrical Colors. 366. Catoptrical colors are such as appear in consequence of a mirror-like reflection. We assume in the first place that the light itself, as well as the surface from which it is reflected, is perfectly colorless. In this sense, the appearances in question come under the head of physical colors. They arise in consequence of reflection, as we found that the optical colors of the second class appear by means of refraction. Without further general definitions, we turn our attention at once to particular cases and to the conditions which are essential to the exhibition of these phenomena. 367. If we unroll a coil of bright steel wire, and after suffering it to spring confusedly together again, place it at a window in the light, we shall see the prominent parts of the circles and convolutions illuminated, but neither resplendent nor iridescent. But if the sun shines on the wire, this light will be condensed into a point, and we perceive a small resplendent image of the sun, which, when seen near, exhibits no color. On retiring a little, however, and fixing the eyes on this refulgent appearance, we discern several small mirrored suns, colored in the most varied manner. And although the impression is that green and red predominate, yet on a more accurate inspection we find that the other colors are also present. 368. If we take an eyeglass and examine the appearance through it, we find the colors have vanished, as well as the radiating splendor in which they were seen, and we perceive only the small luminous points, the repeated images of the sun. We thus find that the impression is subjective in its nature, and that the appearance is allied to those which we have averted under the name of radiating halos. 369. We can, however, exhibit this phenomenon objectively. Let a piece of white paper be fastened beneath a small aperture in the lid of a camera obscura, and when the sun shines through this aperture, let the confusedly rolled steel wire be held in the light so that it be opposite to the paper. The sunlight will impinge on and in the circles of the wire, and will not, as in the concentrating lens of the eye, display itself in a point, but as the paper can receive the reflection of the light, in every part of its surface will be seen in hair-like lines, which are also iridescent. 370. This experiment is purely catoptrical, for, as we cannot imagine that the light penetrates the surface of the steel and thus undergoes a change, we are soon convinced that we have here a mere reflection which, in its subjective character, is connected with the theory of faintly acting lights, and the after-image of dazzling lights, and as far as it can be considered objective, announces even in the minutest appearances a real effect independent of the action and reaction of the eye. 371. We have seen that to produce these effects not merely light but a powerful light is necessary, that this powerful light again is not an abstract and general quality, but a circumscribed light, a luminous image. We can convince ourselves still further of this by analogous cases. 372. A polished surface of silver placed in the sun reflects the dazzling light, but in this case no color is seen. If, however, we slightly scratch the surface, an iridescent appearance, in which green and red are conspicuous, will be exhibited at a certain angle. In chased and carved metals the effect is striking, yet it may be remarked throughout that, in order to its appearance, some form, some alternation of light and dark must cooperate with the reflection. Thus a window bar, the stem of a tree, an accidentally or purposely interposed object, produces a perceptible effect. This appearance, too, may be exhibited objectively in the camera obscura. 373. If we cause a polished plate surface to be so acted on by aqua fortis that the copper within it is touched, and the surface itself thus rendered rough, and if the sun's image be then reflected from it, the splendor will be reverberated from every minutest prominence, and the surface will appear iridescent. So if we hold a sheet of black unglazed paper in the sun and look at it attentively, it will be seen to glisten in its minutest points with the most vivid colors. 374. All these examples are referable to the same conditions. In the first case the luminous image is reflected from a thin line, in the second probably from sharp edges, in the third from very small points. In all a very powerful and circumscribed light is requisite. For all these appearances of colour again, it is necessary that the eye should be at a due distance from the reflecting points. 375. If these observations are made with the microscope, the appearance will be greatly increased in force and splendor, for we then see the smallest portion of the surfaces lit by the sun, glittering in these colours of reflection, which, allied to the hues of refraction, now attain their highest degree of brilliancy. In such cases we may observe a vermiform iridescence on the surface of organic bodies, the further description of which will be given hereafter. 376. Lastly, the colours which are chiefly exhibited in reflection are red and green, whence we may infer that the linear appearance especially consists of a thin line of red, bounded by blue on one side and yellow on the other. If these triple lines approach very near together, the intermediate space must appear green, a phenomenon which will often occur to us as we proceed. 377. We frequently meet with these colours in nature. The colours of the spider's web might be considered exactly of the same class with those reflected from the steel wire, except that the non-translucent quality of the former is not so certain as in the case of steel, on which account some have been inclined to class the colours of the spider's web with the phenomena of refraction. 378. In mother of pearl we perceive infinitely fine organic fibres and lamellae in juxtaposition, from which, as from the scratched silver before alluded to, varied colours, but especially red and green, may arise. 379. The changing colors of the plumage of birds may also be mentioned here, although in all organic instances a chemical principle and an adaptation of the color to the structure may be assumed, considerations to which we shall return in treating of chemical colors. 380. That the appearances of objective halos also approximate catoptrical phenomena will be readily admitted, while we again do not deny that refraction as well may here come into the account. For the present we restrict ourselves to one or two observations. Hereafter we may be enabled to make a fuller application of general principles to particular examples. 381. We first call to mind the yellow and red circles produced on a white or grey wall by a light placed near it. 88. Light, when reflected, appears subdued, and a subdued light excites the impression of yellow, and subsequently of red. 382. Let the wall be illuminated by a candle placed quite close to it. The further the light is diffused, the fainter it becomes, but it is still the effect of the flame, the continuation of its action, the dilated effect of its image. We might therefore very fairly call these circles reiterated images, because they constitute the successive boundaries of the action of the light, and yet at the same time only present an extended image of the flame. 383. If the sky is white and luminous round the sun, owing to the atmosphere being filled with light vapors, if mists or clouds pass before the moon, the reflection of the disk mirrors itself in them, the halos we then perceive are single or double, smaller or greater, sometimes very large, often colorless, sometimes colored. 384. I witnessed a very beautiful halo round the moon the 15th of November 1799, when the barometer stood high. The sky was cloudy and vapory. The halo was completely colored, and the circles were concentric round the light, as in subjective halos. That this halo was objective I was presently convinced by covering the moon's disk, when the same circles were nevertheless perfectly visible. 385. The different extent of the halos appears to have a relation with the proximity of distance of the vapor from the eye of the observer. 386. As window panes lightly breathed upon increase the brilliancy of subjective halos, and in some degree give them an objective character, so perhaps with a simple contrivance in winter, during a quickly freezing temperature, a more exact definition of this might be arrived at. 387. How much reason we have in considering these circles to insist on the image and its effects is apparent in the phenomenon of the so-called double suns. Similar double images always occur in certain points of halos and circles, and only present in a circumscribed form what takes place in a more general way in the whole circle. All this will be more conveniently treated in connection with the appearance of the rainbow. Note Q. 388. In conclusion, it is only necessary to point out the affinity between the catoptrical and paroptical colors. We call those paroptical colors which appear when the light passes by the edge of an opaque, colorless body. How nearly these are allied to dioptrical colors of the second class will be easily seen by those who are convinced with us that the colors of refraction take place only at the edges of objects. The affinity again between the catoptrical and paroptical colors will be evident in the following chapter. End of section 23. Section 24 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Simona Rusu. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 24. Chapter 32. Paroptical Colors. 389. The paroptical colors have been hitherto called perioptical because a peculiar effect of light was supposed to take place, as it were, round the object, and was ascribed to a certain flexibility of the light to and from the object. 390. These colors, again, may be divided into subjective and objective, because they appear partly without us, as it were, painted on surfaces, and partly within us, immediately on the retina. In this chapter we shall find it more to our purpose to take the objective cases first, since the subjective are so closely connected with other appearances already known to us that it is hardly possible to separate them. 391. The paroptical colors, then, are so called because the light must pass by an outline or edge to produce them. They do not, however, always appear in this case. To produce the effect very particular conditions are necessary besides. 392. It is also to be observed that in this instance again light does not act as an abstract diffusion. 361. The sun shines towards an edge. The volume of light poured from the sun image passes by the edge of a substance and occasions shadows. Within these shadows we shall presently find colors appear. 393. But, above all, we should make the experiments and observations that bear upon our present inquiry in the fullest light. We therefore place the observer in the open air before we conduct him to the limits of a dark room. 394. A person walking in sunshine in a garden, or on any level path, may observe that his shadow only appears sharply defined next the foot on which he rests. Farther from this point, especially round the head, it melts away into the bright ground. For as the sunlight proceeds not only from the middle of the sun, but also acts crosswise from the two extremes of every diameter, an objective parallax takes place which produces a half shadow on both sides of the object. 395. If the person walking raises and spreads his hands, he distinctly sees in the shadow of each finger the diverging separation of the two half shadows outwards, and the diminution of the principal shadow inwards, both being effects of the cross-action of the light. 396. This experiment may be repeated and varied before a smooth wall, with rods of different thickness, and again with balls. We shall always find that the further the object is removed from the surface of the wall, the more the weak double shadow spreads, and the more the forcible main shadow diminishes, till at last the main shadow appears quite effaced, and even the double shadows become so faint that they almost disappear. At a still greater distance they are, in fact, imperceptible. 397. That this is caused by the cross-action of the light we may easily convince ourselves, for the shadow of a pointed object plainly exhibits 2 points. We must thus never lose sight of the fact that, in this case, the whole sun image acts, produces shadows, changes them to double shadows, and finally obliterates them. 398. Instead of solid bodies, let us now take openings cut of various given sizes next each other, and let the sun shine through them on a plane surface at some little distance. We shall find that the bright image produced by the sun on the surface is larger than the opening. This is because one edge of the sun shines towards the opposite edge of the opening, while the other edge of the disk is excluded on that side. Hence, the bright image is more weakly lighted towards the edges. 399. If we take square openings of any size we please, we shall find that the bright image on a surface 9 feet from the opening is on every side about an inch larger than the opening, thus nearly corresponding with the angle of the apparent diameter of the sun. 400. That the brightness should gradually diminish towards the edges of the image is quite natural, for at last only a minimum of the light can act crosswise from the sun's circumference through the edge of the aperture. 401. Thus, we here again see how much reason we have in actual observation to guard against the assumption of parallel rays, bundles and faces of rays, and the like hypothetical notions. 402. We might rather consider the splendor of the sun, or of any light, as an infinite specular multiplication of the circumscribed luminous image, whence it may be explained that all square openings through which the sun shines at certain distances, according as the apertures are greater or smaller, must give a round image of light. 403. The above experiments may be repeated through openings of various shapes and sizes, and the same effect will always take place at proportionate distances. In all these cases, however, we may still observe that in a full light, and while the sun merely shines past an edge, no color is apparent. 404. We therefore proceed to experiments with a subdued light, which is essential to the appearance of color. Let a small opening be made in the window shutter of a dark room. Let the crossing sunlight which enters be received on a surface of white paper, and we shall find that the smaller the opening is, the dimmer the light image will be. This is quite obvious, because the paper does not receive light from the whole sun, but partially from single points of its disk. 405. If we look attentively at this dim image of the sun, we find it still dimmer towards the outlines, where a yellow border is perceptible. The color is still more apparent if a vapor or a transparent cloud passes before the sun, thus subduing and dimming its brightness. The halo on the wall, the effect of the decreasing brightness of a light placed near it, is here forced on our recollection. 88. 406. If we examine the image more accurately, we perceive that this yellow border is not the only appearance of color. We can see besides a bluish circle, if not even a halo-like repetition of the colored border. If the room is quite dark, we discern that the sky next the sun also has its effect. We see the blue sky, nay, even the whole landscape, on the paper, and are thus again convinced that, as far as regards the sun, we have here only to do with a luminous image. 407. If we take a somewhat larger square opening, so large that the image of the sun shining through it does not immediately become round, we may distinctly observe the half-shadows of every edge or side, the junction of these in the corners, and their colors, just as in the above-mentioned appearance with a round opening. 408. We have now subdued a parallactic light by causing it to shine through small apertures, but we have not taken from it its parallactic character, so that it can produce double shadows of bodies, although with diminished power. These double shadows, which we have hitherto been describing, follow each other in light and dark, colored and colorless circles, and produce repeated, nay, almost innumerable halos. These effects have been often represented in drawings and engravings. By placing needles, hairs, and other small bodies in the subdued light, the numerous halo-like double shadows may be increased. Thus observed, they have been ascribed to an alternating flexile action of the light, and the same assumption has been employed to explain the obliteration of the central shadow and the appearance of a light in the place of the dark. 409. For ourselves, we maintain that these again are parallactic double shadows, which appear edged with colored borders and halos. 410. After having seen and investigated the foregoing phenomena, we can proceed to the experiments with knife blades, exhibiting effects which may be referred to the contact and parallactic mutual intersection of the half-shadows and halos already familiar to us. 411. Lastly, the observer may follow out the experiments with hairs, needles, and wires in the half-light produced as before described by the sun, as well as in that derived from the blue sky, and indicated on the white paper. He will thus make himself still better acquainted with the true nature of this phenomenon. 412. But since in these experiments everything depends on our being persuaded of the parallactic action of the light, we can make this more evident by means of two sources of light, the two shadows from which intersect each other and may be altogether separated. By day this may be contrived with two small openings in a window shutter, by night with two candles. There are even accidental effects in interiors on opening and closing shutters, by means of which you can better observe these appearances than with the most careful apparatus. But still, all and each of these may be reduced to experiment by preparing a box which the observer can look into from above, and gradually diminishing the openings after having caused the double light to shine in. In this case, as might be expected, the colored shadow, considered under the physiological colors, appears very easily. 413. It is necessary to remember generally what has been before stated with regard to the nature of double shadows, half-lights, and the like. Experiments also should especially be made with different shades of gray placed next each other, where every stripe will appear light by a darker and dark by a lighter stripe next it. If at night, with 3 or more lights, we produce shadows which cross each other successively, we can observe this phenomenon very distinctly, and we shall be convinced that the physiological case before more fully treated here comes into the account. Section 38. 414. to what extent the appearances that accompany the paroptical colors may be derived from the doctrine of subdued lights, from half-shadows, and from the physiological disposition of the retina, or whether we shall be forced to take refuge in certain intrinsic qualities of light, as has hitherto been done, time may teach. Suffice it here to have pointed out the conditions under which the paroptical colors appear, and we may hope that our allusion to their connection with the facts before adduced by us will not remain unnoticed by the observers of nature. 415. The affinity of the paroptical colors with the dioptrical of the second class will also be readily seen and followed up by every reflecting investigator. Here, as in those instances, we have to do with edges or boundaries. Here, as in those instances, with a light which appears at the outline. How natural, therefore, it is to conclude that the paroptical effects may be heightened, strengthened, and enriched by the dioptrical. Since, however, the luminous image actually shines through the medium, we can here only have to do with objective cases of refraction. It is these which are strictly allied to the paroptical cases. The subjective cases of refraction, where we see objects through the medium, are quite distinct from the paroptical. We have already recommended them on account of their clearness and simplicity. 416. The connection between the paroptical colors and the catoptrical may be already inferred from what has been said. For as the catoptrical colors only appear on scratches, points, steel wire, and delicate threads, so it is nearly the same case as if the light shone past an edge. The light must always be reflected from an edge in order to produce color. Here again, as before pointed out, the partial action of the luminous image and the subduing of the light are both to be taken into account. 417. We add but few observations on the subjective paroptical colors, because these may be classed partly with the physiological colors, partly with the dioptrical of the second order. The greater part hardly seem to belong here, but when attentively considered, they still diffuse a satisfactory light over the whole doctrine and establish its connection. 418. If we hold a ruler before the eyes so that the flame of a light just appears above it, we see the ruler as it were intended and notched at the place where the light appears. This seems deducible from the expansive power of light acting on the retina. 18. 419. The same phenomenon on a large scale is exhibited at sunrise, for when the orb appears distinctly, but not too powerfully, so that we can still look at it, it always makes a sharp indentation in the horizon. 420. If when the sky is gray we approach a window, so that the dark cross of the window bars be relieved on the sky, if after fixing the eyes on the horizontal bar we bend the head a little forward, on half closing the eyes as we look up, we shall presently perceive a bright yellow-red border under the bar, and a bright light blue one above it. The duller and more monotonous the gray of the sky, the more dusky the room, and consequently the more previously unexcited the eye, the livelier the appearance will be, but it may be seen by an attentive observer even in bright daylight. 421. If we move the head backwards while half closing the eyes, so that the horizontal bar be seen below, the phenomenon will appear reversed. The upper edge will appear yellow, the under edge blue. 422. Such observations are best made in a dark room. If white paper is spread before the opening where the solar microscope is commonly fastened, the lower edge of the circle will appear blue, the upper yellow, even while the eyes are quite open, or only by half closing them so far that a halo no longer appears round the white. If the head is moved backwards, the colors are reversed. 423. These phenomena seem to prove that the humours of the eye are in fact only really achromatic in the center where vision takes place, but that towards the circumference and in unusual motions of the eyes, as in looking horizontally when the head is bent backwards or forwards, a chromatic tendency remains, especially when distinctly relieved objects are thus looked at. Hence such phenomena may be considered as allied to the dioptrical colors of the second class. 424. Similar colors appear if we look on black and white objects through a pinhole in a card. Instead of a white object, we may take the minute light aperture in the tin plate of a camera obscura as prepared for paroptical experiments. 425. If we look through a tube, the farther end of which is contracted or variously indented, the same colors appear. 426. The following phenomena appear to me to be more nearly allied to the paroptical appearances. If we hold up a needle near the eye, the point appears double. A particularly remarkable effect again is produced if we look towards a grey sky through the blades of knives prepared for paroptical experiments. We seem to look through a gauze. A multitude of threads appear to the eye. These are in fact only the reiterated images of the sharp edges, each of which is successively modified by the next, or perhaps modified in a parallactic sense by the oppositely acting one, the whole mass being thus changed to a thread-like appearance. 427. Lastly, it is to be remarked that if we look through the blades towards a minute light in the window shutter, colored stripes and halos appear on the retina as on the paper. 428. The present chapter may be here terminated, the less reluctantly as a friend has undertaken to investigate this subject by further experiments. In our recapitulation, in the description of the plates and apparatus, we hope hereafter to give an account of his observations. End of section 24. Section 25 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Simona Rusu. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 25. Chapter 33. Optical Colors. 429. We have hitherto had to do with colors which appear with vivacity, but which immediately vanish again when certain conditions cease. We have now to become acquainted with others, which, it is true, are still to be considered as transient, but which under certain circumstances become so fixed that, even after the conditions which first occasioned their appearance cease, they still remain, and thus constitute the link between the physical and the chemical colors. 430. They appear from various causes on the surface of a colorless body, originally without communication, dye, or immersion, va-fi, and we now proceed to trace them from their faintest indication to their most permanent state, through the different conditions of their appearance, which for easier survey we here at once summarily state. 431. First condition: the contact of two smooth surfaces of hard transparent bodies. First case, if masses or plates of glass, or if lenses are pressed against each other. Second case, if a crack takes place in a solid mass of glass, crystal, or ice. Third case, if lamellae of transparent stones become separated. Second condition, if a surface of glass or a polished stone is breathed upon. Third condition, the combination of the two last, first breathing on the glass, then placing another plate of glass upon it, thus exciting the colors by pressure, then removing the upper glass, upon which the colors begin to fade and vanish with the breath. Fourth condition, bubbles of various liquids, soap, chocolate, beer, wine, fine glass bubbles. Fifth condition, very fine pellicles and lamellae produced by the decomposition of minerals and metals. The pellicles of lime, the surface of stagnant water, especially if impregnated with iron, and again pellicles of oil on water, especially of varnish on aqua fortis. Sixth condition, if metals are heated, the operation of imparting tints to steel and other metals. Seventh condition, if the surface of glass is beginning to decompose. 432. First condition, first case, if two convex glasses, or a convex and plane glass, or best of all a convex and concave glass, come in contact, concentric colored circles appear. The phenomenon exhibits itself immediately on the slightest pressure, and may then be gradually carried through various successive states. We will describe the complete appearance at once, and we shall then be better enabled to follow the different states through which it passes. 433. The center is colorless, where the glasses are, so to speak, united in one by the strongest pressure. A dark gray point appears with a silver white space round it. Then follow, in decreasing distances, various insulated rings, all consisting of 3 colors, which are in immediate contact with each other. Each of these rings, of which perhaps 3 or 4 might be counted, is yellow on the inner side, blue on the outer, and red in the center. Between 2 rings there appears a silver-white interval. The rings which are furthest from the center are always nearer together. They are composed of red and green, without a perceptible white space between them. 434. We will now observe the appearances in their gradual formation, beginning from the slightest pressure. 435. On the slightest pressure the center itself appears of a green color. Then follow, as far as the concentric circles extend, red and green rings. They are wide, accordingly, and no trace of a silver-white space is to be seen between them. The green is produced by the blue of an imperfectly developed circle, mixing with the yellow of the first circle. All the remaining circles are, in this slight contact, broad, their yellow and blue edges mixed together, thus producing a beautiful green. The red, however, of each circle remains pure and untouched. Hence the whole series is composed of these 2 colors. 436. A somewhat stronger pressure separates the first circle by a slight interval from the imperfectly developed one. It is thus detached and may be said to appear in a complete state. The center is now a blue point, for the yellow of the first circle is now separated from this central point by a silver-white space. From the center of the blue a red appears, which is thus in all cases bounded on the outside by its blue edge. The second and third rings from the center are quite detached. Where deviations from this order present themselves, the observer will be enabled to account for them from what has been or remains to be stated. 437. On a stronger pressure the center becomes yellow. This yellow is surrounded by a red and blue edge. At last the yellow also retires from the center. The innermost circle is formed and is bounded with yellow. The whole center itself now appears silver-white, till at last, on the strongest pressure, the dark point appears, and the phenomenon as described at first is complete. 438. The relative size of the concentric circles and their intervals depends on the form of the glasses which are pressed together. 439. We remarked above that the colored center is, in fact, an undeveloped circle. It is, however, often found on the slightest pressure that several undeveloped circles exist there, as it were, in the germ. These can be successively developed before the eye of the observer. 440. The regularity of these rings is owing to the form of the convex glasses, and the diameter of the colored appearance depends on the greater or lesser section of a circle on which a lens is polished. We easily conclude from this that, by pressing plain glasses together, irregular appearances only will be produced. The colors, in fact, undulate like watered silks, and spread from the point of pressure in all directions. Yet the phenomenon, as thus exhibited, is much more splendid than in the former instance, and cannot fail to strike every spectator. If we make the experiment in this mode, we shall distinctly see, as in the other case, that on a slight pressure the green and red waves appear; on a stronger, stripes of blue, red, and yellow become detached. At first the outer sides of these stripes touch. On increased pressure they are separated by a silver-white space. 441. Before we proceed to a further description of this phenomenon, we may point out the most convenient mode of exhibiting it. Place a large convex glass on a table near the window. Upon this glass lay a plate of well-polished mirror glass, about the size of a playing card, and the mere weight of the plate will press sufficiently to produce one or other of the phenomena above described. So also by the different weight of plates of glass, by other accidental circumstances, for instance, by slipping the plate on the side of the convex glass, where the pressure cannot be so strong as in the center, all the gradations above described can be produced in succession. 442. In order to observe the phenomenon, it is necessary to look obliquely on the surface where it appears, but above all, it is to be remarked that by stooping still more, and looking at the appearance under a more acute angle, the circles not only grow larger, but other circles are developed from the centre, of which no trace is to be discovered when we look perpendicularly, even through the strongest magnifiers. 443. In order to exhibit a phenomenon in its greatest beauty, the utmost attention should be paid to the cleanness of the glasses. If the experiment is made with plate glass adapted for mirrors, the glass should be handled with gloves. The inner surfaces, which must come in contact with the utmost nicety, may be most conveniently cleaned before the experiment, and the outer surfaces should be kept clean while the pressure is increased. 444. From what has been said, it will be seen that an exact contact of two smooth surfaces is necessary. Polished glasses are best adapted for the purpose. Plates of glass exhibit the most brilliant colors when they fit closely together, and for this reason the phenomenon will increase in beauty if exhibited under an air pump by exhausting the air. 445. The appearance of the colored rings may be produced in the greatest perfection by placing a convex and concave glass together, which have been ground on similar segments of circles. I have never seen the effect more brilliant than with the object glass of an achromatic telescope, in which the crown glass and flint glass were necessarily in the closest contact. 446. A remarkable appearance takes place when dissimilar surfaces are pressed together. For example, a polished crystal and a plate of glass. The appearance does not at all exhibit itself in large flowing waves, as in the combination of glass with glass, but it is small and angular, and, as it were, disjointed. Thus it appears that the surface of the polished crystal, which consists of infinitely small sections of lamellae, does not come so uninterruptedly in contact with the glass as another glass plate would. 447. The appearance of color vanishes on the strongest pressure, which so intimately unites the two surfaces that they appear to make but one substance. It is this which occasions the dark centre, because the pressed lens no longer reflects any light from this point, for the very same point, when seen against the light, is perfectly clear and transparent. On relaxing the pressure, the colours in like manner gradually diminish and disappear entirely when the surfaces are separated. 448. These same appearances occur in two similar cases. If entirely transparent masses become partially separated, the surfaces of their parts being still sufficiently in contact, we see the same circles and waves more or less. They may be produced in great beauty by plunging a hot mass of glass in water, the different fissures and cracks enabling us to observe the colors in various forms. Nature often exhibits the same phenomena in split rock crystals. 449. This appearance again frequently displays itself in the mineral world in those kinds of stone which by nature have a tendency to exfoliate. These original lamellae are, it is true, so intimately united that stones of this kind appear altogether transparent and colourless, yet the internal layers become separated from various accidental causes, without altogether destroying the contact. Thus the appearance which is now familiar to us by the foregoing description often occurs in nature, particularly in calcareous spars, the specularis, adularia, and other minerals of similar structure. Hence it shows an ignorance of the proximate causes of an appearance so often accidentally produced, to consider it so important in mineralogy, and to attach especial value to the specimens exhibiting it. 450. We have yet to speak of the very remarkable inversion of this appearance, as related by men of science. If, namely, instead of looking at the colours by a reflected light, we examine them by a transmitted light, the opposite colours are said to appear, and in a mode corresponding with that which we have before described as physiological, the colours evoking each other. Instead of blue, we should thus see red-yellow, instead of red, green, etc., and vice versa. We reserve experiments in detail, the rather as we have ourselves still some doubts on this point. 451. If we were now called upon to give some general explanation of these optical colors as they appear under the first condition, and to show their connection with the previously detailed physical phenomena, we might proceed to do so as follows. 452. The glasses employed for the experiments are to be regarded as the utmost possible practical approach to transparence. By the intimate contact, however, occasioned by the pressure applied to them, their surfaces, we are persuaded, immediately become in a very slight degree dimmed. Within this semi-transparence, the colours immediately appear, and every circle comprehends the whole scale. For when the two opposites, yellow and blue, are united by their red extremities, pure red appears. The green, on the other hand, as in prismatic experiments, when yellow and blue touch. 453. We have already repeatedly found that where colour exists at all, the whole scale is soon called into existence. A similar principle may be said to lurk in the nature of every physical phenomenon. It already follows from the idea of polar opposition, from which an elementary unity or completeness results. 454. The fact that a colour exhibited by transmitted light is different from that displayed by reflected light reminds us of those dioptrical colours of the first class which we found were produced precisely in the same way through semi-opacity. That here, too, a diminution of transparency exists, there can scarcely be a doubt, for the adhesion of the perfectly smooth plates of glass, an adhesion so strong that they remain hanging to each other, produces a degree of union which deprives each of the two surfaces in some degree of its smoothness and transparency. The fullest proof may, however, be found in the fact that in the centre, where the lens is most strongly pressed on the other glass, and where a perfect union is accomplished, a complete transparency takes place, in which we no longer perceive any colour. All this may be hereafter confirmed by a recapitulation of the whole. 455. Second condition. If after breathing on a plate of glass the breath is merely wiped away with the finger, and if we then again immediately breathe on the glass, we see very vivid colours gliding through each other. These, as the moisture evaporates, change their place, and at last vanish altogether. If this operation is repeated, the colours are more vivid and beautiful, and remain longer than they did the first time. 456. Quickly as this appearance passes, and confused as it appears to be, I have yet remarked the following effects. At first all the principal colours appear with their combinations. On breathing more strongly, the appearance may be perceived in some order. In this succession it may be remarked that when the breath in evaporating becomes contracted from all sides towards the centre, the blue colour vanishes last. 457. The phenomenon appears more readily between the minute lines which the action of passing the fingers leaves on the clear surface. A somewhat rough state of the surface of the glass is otherwise requisite. On some glass the appearance may be produced by merely breathing. In other cases, the wiping with the fingers is necessary. I have even met with polished mirror glasses, one side of which immediately showed the colours vividly, the other not. To judge from some remaining pieces, the former was originally the front of the glass, the latter the side which was covered with quicksilver. 458. These experiments may be best made in cold weather, because the glass may be more quickly and distinctly breathed upon, and the breath evaporates more suddenly. In severe frost the phenomenon may be observed on a large scale, while travelling in a carriage, the glasses being well cleaned and all closed. The breath of the person within is very gently diffused over the glass, and immediately produces the most vivid play of colours. How far they may present a regular succession I have not been able to remark, but they appear particularly vivid when they have a dark object as a background. This alternation of colours does not, however, last long, for as soon as the breath gathers in drops or freezes to points of ice, the appearance is at once at an end. 459. Third condition. The two foregoing experiments of the pressure and breathing may be united, namely, by breathing on a plate of glass, and immediately after pressing the other upon it. The colours then appear as in the case of two glasses unbreathed upon, with this difference that the moisture occasions here and there an interruption of the undulations. On pushing one glass away from the other, the moisture appears iridescent as it evaporates. 460. It might, however, be asserted that this combined experiment exhibits no more than each single experiment, for it appears the colours excited by pressure disappear in proportion as the glasses are less in contact, and the moisture then evaporates with its own colours. 461. Fourth condition. Iridescent appearances are observable in almost all bubbles. Soap bubbles are the most commonly known, and the effect in question is thus exhibited in the easiest mode, but it may be observed in wine, beer, in pure spirit, and again especially in the froth of chocolate. 462. As in the above cases, we require an infinitely narrow space between two surfaces which are in contact, so we can consider the pellicle of the soap bubble as an infinitely thin lamina between two elastic bodies. For the appearance in fact takes place between the air within, which distends the bubble, and the atmospheric air. 463. The bubble when first produced is colourless, then coloured stripes like those in marble paper begin to appear. These at length spread over the whole surface, or rather are driven round it as it is distended. 464. In a single bubble, suffered to hang from the straw or a tube, the appearance of colour is difficult to observe, for the quick rotation prevents any accurate observation, and all the colours seem to mix together, yet we can perceive that the colours begin at the orifice of the tube. The solution itself may, however, be blown into carefully, so that only one bubble shall appear. This remains white, colourless, if not much agitated, but if the solution is not too watery, circles appear round the perpendicular axis of the bubble. These, being near each other, are commonly composed alternately of green and red. Lastly, several bubbles may be produced together by the same means. In this case the colours appear on the sides where two bubbles have pressed each other flat. 465. The bubbles of chocolate froth may perhaps be even more conveniently observed than those of soap. Though smaller, they remain longer. In these, owing to the heat, an impulse, a movement, is produced and sustained, which appears necessary to the development and succession of the appearances. 466. If the bubble is small or shut in between others, coloured lines chase each other over the surface, resembling marbled paper. All the colours of the scale are seen to pass through each other, the pure, the augmented, the combined, all distinctly clear and beautiful. In small bubbles the appearance lasts for a considerable time. 467. If the bubble is larger, or if it becomes by degrees detached, owing to the bursting of others near, we perceive that this impulsion and attraction of the colours has, as it were, an end in view. For on the highest point of the bubble we see a small circle appear, which is yellow in the centre. The other remaining coloured lines move constantly round this with a vermicular action. 468. In a short time the circle enlarges and sinks downwards on all sides. In the centre the yellow remains, below and on the outside it becomes red, and soon blue. Below this again appears a new circle of the same series of colours. If they approximate sufficiently, a green is produced by the union of the border colours. 469. When I could count 3 such leading circles, the centre was colourless, and this space became by degrees larger as the circles sank lower, till at last the bubble burst. 470. Fifth condition. Very delicate pellicles may be formed in various ways. On these films we discover a very lively play of colours, either in the usual order, or more confusedly passing through each other. The water in which lime has been slaked soon skims over with a coloured pellicle. The same happens on the surface of stagnant water, especially if impregnated with iron. The lamellae of the fine tartar which adheres to bottles, especially in red French wine, exhibit the most brilliant colours on being exposed to the light if carefully detached. Drops of oil on water, brandy, and other fluids produce also similar circles and brilliant effects. But the most beautiful experiment that can be made is the following. Let aqua fortis, not too strong, be poured into a flat saucer, and then with a brush drop on it some of the varnish used by engravers to cover certain portions during the process of biting their plates. After quick commotion, there presently appears a film which spreads itself out in circles and immediately produces the most vivid appearances of color. 471. Sixth condition. When metals are heated, colors rapidly succeeding each other appear on the surface. These colors can, however, be arrested at will. 472. If a piece of polished steel is heated, it will, at a certain degree of warmth, be overspread with yellow. If taken suddenly away from the fire, this yellow remains. 473. As the steel becomes hotter, the yellow appears darker, intenser, and presently passes into red. This is difficult to arrest, for it hastens very quickly to bright blue. 474. This beautiful blue is to be arrested if the steel is suddenly taken out of the heat and buried in ashes. The blue steel works are produced in this way. If again the steel is held longer over the fire, it soon becomes a light blue, and so it remains. 475. These colors pass like a breath over the plate of steel. Each seems to fly before the other, but in reality each successive hue is constantly developed from the preceding one. 476. If we hold a penknife in the flame of a light, a colored stripe will appear across the blade. The portion of the stripe which was nearest to the flame is light blue. This melts into blue-red, the red is in the center. Then follow yellow-red and yellow. 477. This phenomenon is deducible from the preceding ones, for the portion of the blade next to the handle is less heated than the end which is in the flame, and thus all the colors which in other cases exhibited themselves in succession must here appear at once, and may thus be permanently preserved. 478. Robert Boyle gives this succession of colors as follows: A florido flavo ad flavum saturum et rubescentem, quem artifices sanguineum vocant, inde ad languidum postea ad saturiorem cyaneum. This would be quite correct if the words languidus and saturior were to change places. How far the observation is correct, that the different colors have a relation to the degree of temper which the metal afterwards acquires, we leave to others to decide. The colors are here only indications of the different degrees of heat. Note R. 479. When lead is calcined, the surface is first grayish. This grayish powder, with greater heat, becomes yellow and then orange. Silver, too, exhibits colors when heated. The fracture of silver in the process of refining belongs to the same class of examples. When metallic glasses melt, colors in like manner appear on the surface. 480. Seventh condition. When the surface of glass becomes decomposed, the accidental opacity, blindwerden, of glass has been already noticed. The term blindwerden is employed to denote that the surface of the glass is also affected as to appear dim to us. 481. White glass becomes blind soonest. Cast and afterwards polished glass is also liable to be so affected. The bluish less, the green least. 482. Of the two sides of a plate of glass, one is called the mirror side. It is that which in the oven lies uppermost, on which one may observe roundish elevations. It is smoother than the other, which is undermost in the oven, and on which scratches may be sometimes observed. On this account the mirror side is placed facing the interior of rooms, because it is less affected by the moisture adhering to it from within than the other would be, and the glass is thus less liable to become blind. 483. This half opacity or dimness of the glass assumes by degrees an appearance of colour, which may become very vivid, and in which perhaps a certain succession or otherwise regular order might be discovered. 484. Having thus traced the physical colors from their simplest effects to the present instances, where these fleeting appearances are found to be fixed in bodies, we are in fact arrived at the point where the chemical colors begin. Nay, we have in some sort already passed those limits, a circumstance which may excite a favourable prejudice for the consistency of our statement. By way of conclusion to this part of our inquiry, we subjoin a general observation which may not be without its bearing on the common connecting principle of the phenomena that have been adduced. 485. The colouring of steel and the appearances analogous to it might perhaps be easily deduced from the doctrine of the semi-opaque mediums. Polished steel reflects light powerfully. We may consider the colour produced by the heat as a slight degree of dimness. Hence a bright yellow must immediately appear. This, as the dimness increases, must still appear deeper, more condensed, and redder, and at last pure and ruby red. The colour has now reached the extreme point of depth, and if we suppose the same degree of semi-opacity still to continue, the dimness would now spread itself over a dark ground, first producing a violet, then a dark blue, and at last a light blue, and thus complete the series of the appearances. We will not assert that this mode of explanation will suffice in all cases. Our object is rather to point out the road by which the all-comprehensive formula, the very key of the enigma, may be at last discovered. End of section 25.
Section 26 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Joanne Crosby. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 26. Part 3. Chemical Colors. 486. We give this denomination to colors which we can produce and more or less fix in certain bodies, which we can render more intense, which we can again take away and communicate to other bodies, and to which, therefore, we ascribe a certain permanency. Duration is their prevailing characteristic. 487. In this view, the chemical colors were formerly distinguished with various epithets. They were called color proprietary, corporei, materiale, vari, permanente, fixi. 488. In the preceding chapter, we observed how the fluctuating and transient nature of the physical colors becomes gradually fixed, thus forming the natural transition to our present subject. 489. Color becomes fixed in bodies more or less permanently, superficially or thoroughly. 490. All bodies are susceptible of color. It can either be excited, rendered intense, and gradually fixed in them, or at least communicated to them. 34. Chemical contrast. 491. In the examination of colored appearances, we had occasion everywhere to take notice of a principle of contrast. So again, in approaching the precincts of chemistry, we find a chemical contrast of a remarkable nature. We speak here, with reference to our present purpose, only of that which is comprehended under the general names of acid and alkali. 492. We characterize the chromatic contrast in conformity with all other physical contrasts as a more or less, subscribing the plus to the yellow side, the minus to the blue, and we now find that these two divisions correspond with the chemical contrasts. The yellow and the yellow-red affect the acids, the blue and the blue-red, the alkali. Thus the phenomena of chemical colors, although still necessarily mixed up with other considerations, admit of being traced with sufficient simplicity. 493. The principal phenomena in chemical colors are produced by the oxidation of metals, and it will be seen how important this consideration is at the onset. Other facts which come into the account, and which are worthy of attention, will be examined under separate heads. In doing this, we, however, expressly state that we only propose to offer some preparatory suggestions to the chemist in a very general way, without entering into the nicer chemical problems and questions or presuming to decide on them. Our object is only to give a sketch of the mode in which, according to our convictions, the chemical theory of colors may be connected with general physics. End of section 26. Section 27 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Johann Crosby. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 27. 35. White. 494. In treating of the diatropic colors of the first class, we have already in some degree anticipated this subject. Transparent substances may be said to be in the highest class of inorganic matter. With these, colorless semi-transparence is closely connected, and white may be considered the last opaque degree of this. 495. Pure water crystallized to snow appears white, for the transparence of the separate parts makes no transparent whole. Various crystallized salts, when deprived to a certain extent of moisture, appear as white powder. The accidentally opaque state of a pure transparent substance might be called white. Thus pounded glass appears as a white powder. The cessation of a combining power and the exhibition of the atomic quality of the substance might at the same time be taken into account. 496. The known undecomposed earths are in their pure state all white. They pass to a state of transparence by natural crystallization. Silex becomes rock crystal, argile, mica, magnesia, talc, calcareous earth, and barite appear transparent in various spars. 497. As in the coloring of mineral bodies, the metallic oxides will often invite our attention. We observe, in conclusion, that metals, when slightly oxidated, at first appear white, as lead is converted to white lead by vegetable acid. 36. Black. 498. Black is not exhibited in so elementary a state as white. We met with it in the vegetable kingdom in semi-combustion, and charcoal, a substance especially worthy of attention on other accounts, exhibits a black color. Again, if woods, for example boards, owing to the action of light, air, and moisture, are deprived in part of their combustibility, there appears first the gray, then the black color. So again we can convert even portions of animal substance to charcoal by semi-combustion. 499. In the same manner, we often find that a suboxidation takes place in metals, when the black color is to be produced. Various metals, particularly iron, become black by slight oxidation, by vinegar, by mild acid fermentations, for example, a decoction of rice, and c. 500. Again, it may be inferred that deoxidation may produce black. This occurs in the preparation of ink, which becomes yellow by the solution of iron in strong sulfuric acid, but when partly deoxidized by the infusion of gallnuts, appears black. 37. First excitation of color. 501. In the division of physical colors, where semi-transparent mediums were considered, we saw colors antecedently to white and black. In the present case, we assume a white and black already produced and fixed, and the question is, how color may be excited in them. 502. Here, too, we can say, white that becomes darkened or dimmed inclines to yellow. Black, as it becomes lighter, inclines to blue. 503. Yellow appears on the active plus side, immediately in the light, the bright, the white. All white surfaces easily assume a yellow tinge. Paper, linen, wool, silk, wax, transparent fluids again, which have a tendency to combustion, easily become yellow. In other words, they easily pass into a very slight state of semi-transparence. 504. So again, the excitement on the passive side, the tendency to obscure, dark black, is immediately accompanied with blue, or rather with a reddish blue, iron dissolved in sulfuric acid and much diluted with water, if held to the light in a glass, exhibits a beautiful violet color as soon as a few drops only of the infusion of gallnuts are added. This color presents the peculiar hues of the dark topaz, the orphinion of a burnt red, as the ancients expressed it. 505. Whether any color can be excited in the pure earths by the chemical operations of nature and art, without the admixture of metal oxides, is an important question generally, indeed answered in the negative. It is perhaps connected with the question, to what extent changes may be produced in the earths through oxidation. 506. Undoubtedly, the negation of the above question is confirmed by the circumstances that whenever mineral colors are found, some trace of metal, especially of iron, shows itself. We are thus naturally led to consider how easily iron becomes oxidized, how easily the oxidate of iron assumes different colors, how infinitely divisible it is, and how quickly it communicates its color. It were to be wished, notwithstanding, that new experiments could be made in regard to the above point, so as to either confirm or remove any doubt. 507. However this may be, the susceptibility of the earths with regard to colors already existing is very great. A luminous earth is thus particularly distinguished. 508. In proceeding to consider the metals, which in the inorganic world have the almost exclusive prerogative of appearing colored, we find that, in their pure independent natural state, they are already distinguished from the pure earths by a tendency to some one color or other. 509. While silver approximates most to pure white, nay, really represents pure white, heightened by metallic splendor, steel, tin, lead, and so forth incline towards pale blue-gray. Gold, on the other hand, deepens to pure yellow. Copper approaches a red hue, which, under certain circumstances, increases almost to bright red, but which again returns to a yellow-golden color when combined with zinc. 510. But if metals in their pure state have so specific a determination towards this or that exhibition of color, they are, through the effect of oxidation, in some degree reduced to a common character. For the elementary colors now come forth in their purity, and although this or that metal appears to have a particular tendency to this or that color, we find some that can go through the whole circle of hues, others that are capable of exhibiting more than one color. Tin, however, is distinguished by its comparative inaptitude to becoming colored. We propose to give a table hereafter, showing how far the different metals can be more or less made to exhibit the different colors. 511. When the clean, smooth surface of a pure metal, on being heated, becomes overspread with a mantling color, which passes through a series of appearances as the heat increases, this, we are persuaded, indicates the aptitude of the metal to pass through the whole range of colors. We find this phenomenon most beautifully exhibited in polished steel, but silver, copper, brass, lead, and tin easily present similar appearances. A superficial oxidation is probably here taking place, as may be inferred from the effects of the operation when continued, especially in the more easily oxidizable metals. 512. The same conclusion may be drawn from the fact that iron is more easily oxidizable by acid liquids when it's red hot, for in this case the two effects concur with each other. We observe again that steel, accordingly as it is hardened in different stages of its colorification, may exhibit a difference of elasticity. This is quite natural, for the various appearances of color indicates various degrees of heat. 513. If we look beyond this superficial mantling, this pellicle of color, we observe that as metals are oxidized throughout their masses, white or black appears with the first degree of heat, as may be seen in white lead, iron, and quicksilver. 514. If we examine further, and look for the actual exhibition of color, we find it most frequently on the plus side. The mantling so often mentioned of smooth metallic surfaces begins with yellow. Iron passes presently into yellow ochre, lead from white lead to massiacate, quicksilver from Ethiops to yellow turbith. The solutions of gold and platinum in acids are yellow. 515. The exhibition on the minus side are less frequent. Copper slightly oxidized appears blue, In the preparation of Prussian blue, alkalis are employed. 516. Generally, however, these appearances of color are of so mutable a nature that chemists look upon them as deceptive tests, at least in the nicer gradations. For ourselves, as we can only treat of these matters in a general way, we merely observe that the appearances of color in metals may be classed according to their origin, manifold appearances, and cessation as various results of oxidation, hyperoxidation, aboxidation, and deoxidation. End of section 27.
Section 28 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 28. 38. Augmentation of color. 517. The augmentation of color exhibits itself as a condensation, a fullness, a darkening of the hue. We have before seen, in treating of colorless mediums, that by increasing the degree of opacity in the medium, we can deepen a bright object from the lightest yellow to the intensest ruby red. Blue, on the other hand, increases to the most beautiful violet if we rarefy and diminish a semi-opaque medium, itself lighted, but through which we see darkness. 150, 151. 518. If the color is positive, a similar color appears in the intenser state. Thus, if we fill a white porcelain cup with a pure yellow liquor, the fluid will appear to become gradually redder toward the bottom, and at last appears orange. If we pour a pure blue solution into another cup, the upper portion will exhibit a sky blue, that towards the bottom a beautiful violet. If the cup is placed in the sun, the shadowed side, even of the upper portion, is already violet. If we throw a shadow with the hand, or any other substance, over the illuminated portion, the shadow, in like manner, appears reddish. 519. This is one of the most important appearances connected with the doctrine of colors, for we here manifestly find that a difference of quantity produces a corresponding qualified impression on our senses. In speaking of the last class of optical colors, 452, 485, we stated our conjecture that the coloring of steel might perhaps be traced to the doctrine of the semi-transparent mediums, and we would here again recall this to the reader's recollection. 520. All chemical augmentation of color, again, is the immediate consequence of continued excitation. The augmentation advances constantly and unremittingly, and it is to be observed that the increase of intenseness is most common on the plus side. Yellow iron ochre increases, as well by fire as by other operations, to a very strong red. Massicot is increased to red lead, turbith to vermilion, which last obtains a very high degree of the yellow red. An intimate saturation of the metal by the acid, and its separation to infinity, take place together with the above effects. 521. The augmentation on the minus side is less frequent, but we observe that the more pure and condensed the Prussian blue or cobalt glass is prepared, the more readily it assumes a reddish hue and inclines to the violet. 522. The French have a happy expression for the less perceptible tendency of yellow and blue towards red. They say the color has un île de rouge, which we might perhaps express by a reddish glance, einen rötlichen Blick. 39. Culmination. 523. This is the consequence of still progressing augmentation. Red, in which neither yellow nor blue is to be detected, here constitutes the acme. 524. If we wish to select a striking example of a culmination on the plus side, we again find it in the colored steel, which attains the bright red acme, and can be arrested at this point. 525. Were we here to employ the terminology before proposed, we should say that the first oxidation produces yellow, the hyperoxidation yellow-red, that here a kind of maximum exists, and that then an aboxidation, and lastly a deoxidation takes place. 526. High degrees of oxidation produce a bright red. Gold in solution, precipitated by a solution of tin, appears bright red. Oxide of arsenic, in combination with sulphur, produces a ruby color. 527. How far, however, a kind of sub-oxidation may cooperate in some culminations is matter for inquiry, for an influence of alkalis on yellow-red also appears to produce the culmination, the color reaching the acme by being forced towards the minus side. 528. The Dutch prepare a color known by the name of vermilion from the best Hungarian cinnabar, which exhibits the brightest yellow-red. This vermilion is still only a cinnabar, which, however, approximates the pure red, and it may be conjectured that alkalis are used to bring it nearer to the culminating point. 529. Vegetable juices, treated in this way, offer very striking examples of the above effects. The coloring matter of turmeric, annatto, dyer's saffron, and other vegetables, being extracted with spirits of wine, exhibit tints of yellow, yellow-red, and hyacinth red. These, by the admixture of alkalis, pass to the culminating point, and even beyond it to blue-red. 530. No instance of a culmination on the minus side has come to my knowledge in the mineral and vegetable kingdoms. In the animal kingdom the juice of the murex is remarkable. Of its augmentation and culmination on the minus side we shall hereafter have occasion to speak. 40. Fluxation. 531. The mutability of colours is so great that even those pigments, which may have been considered to be defined and arrested, still admit of slight variations on one side or the other. This mutability is most remarkable near the culminating point, and is effected in a very striking manner by the alternate employment of acids and alkalis. 532. To express this appearance in dyeing, the French make use of the word virer, to turn from one side to the other. They thus very adroitly convey an idea which others attempt to express by terms indicating the component use. 533. The effect produced with litmus is one of the most known and striking of this kind. This coloring substance is tendered red-blue by means of alkalis. The red-blue is very readily changed to red-yellow by means of acid, and again returns to its first state by again employing alkalis. The question whether a culminating point is to be discovered and arrested by nice experiments is left to those who are practised in these operations. Dyeing, especially scarlet dyeing, might afford a variety of examples of this fluctuation. 41. Passage through the whole scale. 534. The first excitation and gradual increase of colour take place more on the plus than on the minus side. So, also, in passing through the whole scale, colour exhibits itself most on the plus side. 535. A passage of this kind, regular and evident to the senses, from yellow through red to blue, is apparent in the colouring of steel. 536. The metals may be arrested at various points of the colorific circle by various degrees and kinds of oxidation. 537. As they also appear green, a question arises whether chemists know any instance in the mineral kingdom of a constant transition from yellow through green to blue, and vice versa. Oxide of iron melted with glass produces first a green, and with a more powerful heat a blue color. 538. We may here observe of green generally that it appears, especially in an atomic sense, and certainly in a pure sense, when we mix blue and yellow. But again an impure and dirty yellow soon gives us the impression of green. Yellow and black already produce green. This, however, is owing to the affinity between black and blue. An imperfect yellow, such as that of sulphur, gives us the impression of a greenish hue. Thus, again, an imperfect blue appears green. The green of wine bottles arises, it appears, from an imperfect union of the oxide of iron with the glass. If we produce a more complete union by greater heat, a beautiful blue glass is the result. 539. From all this it appears that a certain chasm exists in nature between yellow and blue, the opposite character of which, it is true, may be done away atomically by due immixture, and thus combined to green. But the true reconciliation between yellow and blue, it appears, only takes place by means of red. 540. The process, however, which appears unattainable in inorganic substances, we shall find to be possible when we turn our attention to organic productions, for in these the passage through the whole circle from yellow through green and blue to red really takes place. End of section 28. Recording by Todd. Section 29 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 29. 42. Inversion. 541. Again, an immediate inversion, or change to the totally opposite hue, is a very remarkable appearance which sometimes occurs. At present we are merely enabled to adduce what follows. 452. The mineral chameleon, a name which has been given to an oxide of manganese, may be considered, in its perfectly dry state, as a green powder. If we strew it in water, the green color displays itself very beautifully in the first moment of solution, but it changes presently to the bright red opposite to green, without any apparent intermediate state. 543. The same occurs with the sympathetic ink, which may be considered a reddish liquid, but which, when dried by warmth, appears as a green color on paper. 544. In fact, this phenomena appears to be owing to the conflict between a dry and moist state, as has already been observed, if we are not mistaken, by the chemists. We may look to the improvements of time to point out what may further be deduced from these phenomena, and to show what other facts they may be connected with. 43. Fixation. 545. Mutable as we have hitherto found colour to be, even as a substance, yet under certain circumstances it may at last be fixed. 546. There are bodies capable of being entirely converted into colouring matter. Here it may be said that the colour fixes itself in its own substance, stops at a certain point, and is there defined. Such colouring substances are found throughout nature. The vegetable world affords a great quantity of examples, among which some are particularly distinguished, and may be considered as the representatives of the rest, such as, on the active side, madder; on the passive side, indigo. 547. In order to make these materials available in use, it is necessary that the colouring quality in them should be intimately condensed, and the tinging substance refined, practically speaking, to an infinite divisibility. This is accomplished in various ways, and particularly by the well-known means of fermentation and decomposition. 548. These colouring substances now attach themselves again to other bodies. Thus, in the mineral kingdom, they adhere to earths and metallic oxides. They unite in melting with the glasses, and in this case, as the light is transmitted through them, they appear in the greatest beauty, while an eternal duration may be ascribed to them. 549. They fasten on vegetable and animal bodies with more or less power, and retain more or less permanently, partly owing to their nature, as yellow, for example, is more effervescent than blue, or owing to the nature of the substance on which they appear. They last less in vegetable than in animal substances, and even within this latter kingdom there are again varieties. Hemp or cotton threads, silk or wool, exhibit very different relations to colouring substances. 550. Here comes into the account the important operation of employing mordants, which may be considered as the intermediate agents between the colour and the recipient substance. Various works on dyeing speak of this circumstantially. Suffice it to have been alluded to processes by means of which the colour retains a permanency only to be destroyed with the substance, and which may even increase in brightness and beauty by use. 44. Intermixture, real. 551. Every intermixture presupposes a specific state of colour, and thus when we speak of intermixture, we here understand it in an atomic sense. We must first have before us certain bodies arrested at any given point of the colorific circle, before we can produce gradations by their union. 552. Yellow, blue, and red may be assumed as pure elementary colours, already existing. From these, violet, orange, and green are the simplest combined results. 553. Some persons have taken much pains to define these intermixtures more accurately, by relations of number, measure, and weight, but nothing very profitable has been thus accomplished. 554. Painting consists, strictly speaking, in the intermixture of such specific colouring bodies and their infinite possible combinations, combinations which can only be appreciated by the nicest, most practised eye, and only accomplished under its influence. 555. The intimate combination of these ingredients is effected, in the first instance, through the most perfect comminution of the material by means of grinding, washing, etc., as well as by vehicles or liquid mediums which hold together the pulverized substance, and combined organically, as it were, the inorganic. Such are the oils, resins, etc. 556. If all the colours are mixed together they retain their general character as scaron, and as they are no longer seen next to each other, no completeness, no harmony is experienced. The result is grey, which, like apparent colour, always appears somewhat darker than white, and somewhat lighter than black. 557. This grey may be produced in various ways: by mixing yellow and blue to an emerald green, and then adding pure red, till all three neutralize each other; or by placing the primitive and intermediate colours next each other in certain proportion, and afterwards mixing them. 558. That all the colours mixed together produce white is an absurdity which people have credulously been accustomed to repeat for a century, in opposition to the evidence of their senses. 559. Colours, when mixed together, retain their original darkness. The darker the colours, the darker will be the grey resulting from their union, till at last this grey approaches black. The lighter the colours, the lighter will be the grey, which at last approaches white. 45. Intermixture, apparent. 560. The intermixture, which is only apparent, naturally invites our attention in connection with the foregoing. It is in many respects important, and indeed the intermixture which we have distinguished as real might be considered as merely apparent, for the elements of which the combined colour consists are only too small to be considered as distinct parts. Yellow and blue powders mingled together appear green to the naked eye, but through a magnifying glass we can still perceive yellow and blue distinct from each other. Thus yellow and blue stripes seen at a distance present a green mass. The same observation is applicable with regard to the intermixture of other specific colours. 561. In the description of our apparatus we shall have occasion to mention the wheel, by means of which the apparent intermixture is produced by rapid movement. Various colours are arranged near each other round the edge of a disc, which is made to revolve with velocity, and thus by having several such discs ready, every possible intermixture can be presented to the eye, as well as the mixture of all colours to grey, darker or lighter according to the depth of the tints as above explained. 562. Physiological colours admit, in like manner, of being mixed with others. If, for example, we produce the blue shadow 65 on a light yellow paper, the surface will appear green. The same happens with regard to the other colours if the necessary preparations are attended to. 563. If, when the eye is impressed with visionary images that last for a while, we look on coloured surfaces, an intermixture also takes place. The spectrum is determined to a new colour which is composed of the two. 564. Physical colours also admit of combination. Here might be adduced the experiments in which many coloured images are seen through the prism, as we have before shown in detail. 258, 284. 565. Those who have prosecuted these inquiries have, however, paid most attention to the appearances which take place when the prismatic colours are thrown on coloured surfaces. 566. What is seen under these circumstances is quite simple. In the first place, it must be remembered that the prismatic colours are much more vivid than the colours of the surfaces on which they are thrown. Second, we have to consider that the prismatic colours may be either homogeneous or heterogeneous with the recipient surface. In the former case the surface deepens and enhances them, and it is itself enhanced in return as a coloured stone is displayed by a similarly coloured foil. In the opposite case each vitiates, disturbs, and destroys the other. 567. These experiments may be repeated with coloured glasses, by causing the sunlight to shine through them on coloured surfaces. In every instance similar results will appear. 568. The same effect takes place when we look on coloured objects through coloured glasses. the colors being thus according to the same conditions enhanced, subdued, or neutralized. 569. If the prismatic colors are suffered to pass through colored glasses, the appearances that take place are perfectly analogous. In these cases more or less force, more or less light and dark, the clearness and cleanness of the glass are all to be allowed for they produce many delicate varieties of effect. These will not escape the notice of every accurate observer who takes sufficient interest in the inquiry to go through the experiments. 570. It is scarcely necessary to mention that several colored glasses, as well as oiled or transparent papers, placed over each other, may be made to produce and exhibit every kind of intermixture at pleasure. 571. Lastly, the operation of glazing in painting belongs to this kind of intermixture. By this means a much more refined union may be produced than that arising from the mechanical atomic mixture which is commonly employed. End of section 29. Recording by Todd. Section 30 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 30. 46. Communication, actual. 572. Having now provided the coloring materials, as before shown, a further question arises how to communicate these to colorless substances. The answer is of the greatest importance from the connection of the object with the ordinary wants of men, with useful purposes, and with commercial and technical interests. 573. Here, again, the dark quality of every color again comes into the account. From a yellow that is very near to white, through orange, and the hue of minimum to pure red and carmine, through all gradations of violet to the deepest blue which is almost identified with black, color still increases in darkness. Blue, once defined, admits of being diluted, made light, united with yellow, and then, as green, it approaches the light side of the scale, but this is by no means according to its own nature. 574. In the physiological colors, we have already seen that they are less than the light, inasmuch as they are a repetition of an impression of light. Nay, at last they leave this impression quite as a dark. In physical experiments, the employment of semi-transparent mediums, the effect of semi-transparent accessory images, taught us that in such cases we have to do with a subdued light, with a transition to darkness. 575. In treating of the chemical origin of pigments, we found that the same effect was produced on the very first excitement. The yellow tinge which mantles over the steel already darkens the shining surface. In changing white lead to massicot, it is evident that the yellow is darker than the white. 576. This process is in the highest degree delicate. The growing intenseness, as it still increases, tinges the substance more and more intimately and powerfully, and thus indicates the extreme fineness and the infinite divisibility of the colored atoms. 577. The colors which approach the dark side, and consequently blue in particular, can be made to approximate to black. In fact, a very perfect Prussian blue or an indigo, acted on by vitriolic acid, appears almost as a black. 578. A remarkable appearance may here be adverted to. Pigments, in their deepest and most condensed state, especially those produced from the vegetable kingdom, such as the indigo just mentioned, or madder carried to its intensest hue, no longer show their own color. On the contrary, a decided metallic shine is seen on their surface, in which the physiological compensatory color appears. 579. All good indigo exhibits a copper color in its fracture, a circumstance attended to, as a known characteristic, in trade. Again, the indigo which has been acted on by sulphuric acid, if thickly laid on, or suffered to dry so that neither white paper nor the porcelain can appear through, exhibits a color approaching to orange. 580. The bright red Spanish rouge, probably prepared from madder, exhibits on its surface a perfectly green metallic shine. If this color, or the blue before mentioned, is washed with a pencil on porcelain or paper, it is seen in its real state owing to the bright ground shining through. 581. Colored liquids appear black when no light is transmitted through them. as we may easily see in cubic tin vessels with glass bottoms. In these, every transparent colored infusion will appear black and colorless if we place a black surface under them. 582. If we contrive that the image of a flame be reflected from the bottom, the image will appear colored. If we lift up the vessel and suffer the transmitted light to fall on white paper under it, the color of the liquid appears on the paper. Every light ground seen through such a colored medium exhibits the color of the medium. 583. Thus every color, in order to be seen, must have a light within or behind it. Hence the lighter and brighter the grounds are, the more brilliant the colors appear. If we pass lac varnish over a shining white metal surface, as the so-called foils are prepared, the splendor of the color is displayed by this internally reflected light as powerfully as in any prismatic experiment. Nay, the force of the physical colors is owing principally to the circumstance that light is always acting within and behind them. 584. Lichtenberg, who of necessity followed the received theory, owing to the time and circumstances in which he lived, was yet too good an observer and too acute not to explain and classify, after his fashion, what was evident to his senses. He says, in the preface to De Laval, "It appears to me also, on other grounds, probable, that our organ, in order to be impressed by a color, must at the same time be impressed by all light, white." 585. To procure white as a ground is the chief business of the dyer. Every color may be easily communicated to colorless earths, especially to alum, but the dyer has especially to do with animal and vegetable products as the ground of his operations. 586. Everything living tends to color, to local, specific color, to effect, to opacity, pervading the minutest atoms. Everything in which life is extinct approximates to white. 494. To the abstract, the general state, to cleanness, to transparence. 587. How this is put in practice in technical operations remains to be adverted to in the chapter on the privation of color. With regard to the communication of color, we have especially to bear in mind that animals and vegetables, in a living state, produce colors, and hence their substances, if deprived of colors, can the more readily reassume them. 47. Communication apparent. 588. The communication of colors, real as well as apparent, corresponds, as may easily be seen, with their intermixture. We need not, therefore, repeat what has already been sufficiently entered into. 589. Yet we may here point out more circumstantially the importance of an apparent communication which takes place by means of reflection. This phenomena is well known, but still it is pregnant with inferences, and is of the greatest importance both to the investigator of nature and to the painter. 590. Let a surface colored with any one of the positive colors be placed in the sun, and let its reflection be thrown on other colorless objects. This reflection is a kind of subdued light, a half shadow, which, in a subdued state, reflects the colors in question. 591. If this reflection acts on light surfaces, it is so far overpowered that we can scarcely perceive the color which accompanies it; but if it acts on shadowed portions, a sort of magical union takes place with the sciera. Shadow is the proper element of color, and in this case a subdued color approaches it, lighting up, tinging, and enlivening it, and thus arises an appearance, as powerful as agreeable, which may render the most pleasing service to the painter who knows how to make use of it. These are the types of the so-called reflexes, which were only noticed late in the history of art, and which have been too seldom employed in their full variety. 592. The schoolmen call these colors colores notionales and intentionales, and the history of the doctrine of colors will generally show that the old inquirers already observed the phenomena well enough, and knew how to distinguish them properly, although the whole method of treating such subjects is very different from ours. End of Section 30. Recording by Todd.
Section 31 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Susie. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Sections 48 and 49. Section 48. Extraction. 593. Color may be extracted from substances, whether they possess it naturally or by communication, in various ways. We have thus the power to remove it intentionally for a useful purpose, but, on the other hand, it often flies contrary to our wish. 594. Not only are the elementary earths in their natural state white, but vegetable and animal substances can be reduced to a white state without disturbing their texture. A pure white is very desirable for various uses, as in the instance of our preferring to use linen and cotton stuffs uncolored. In like manner, some silk stuffs, paper, and other substances are the more agreeable the whiter they can be. Again, the chief basis of all dyeing consists in white grounds. For these reasons, manufacturers, aided by accident and contrivance, have devoted themselves assiduously to discover means of extracting color. Infinite experiments have been made in connection with this object, and many important facts have been arrived at. 595. It is in accomplishing this entire extraction of color that the operation of bleaching consists, which is very generally practiced empirically or methodically. We will here shortly state the leading principles. 596. Light is considered as one of the first means of extracting color from substances, and not only the sunlight, but the mere powerless daylight. For as both lights, the direct light of the sun, as well as the derived light of the sky, kindle Bologna phosphorus, so both act on colored surfaces. Whether the light attacks the color allied to it, and, as it were, kindles and consumes it, thus reducing the definite quality to a general state, or whether some other operation unknown to us takes place, it is clear that light exercises a great power on colored surfaces, and bleaches them more or less. Here, however, the different colors exhibit a different degree of durability. Yellow, especially if prepared from certain materials, is, in this case, the first to fly. 597. Not only light, but air, and especially water, act strongly in destroying color. It has been even asserted that thread, well soaked and spread on the grass at night, bleaches better than that which is exposed, after soaking, to the sunlight. Thus, in this case, water proves to be a solving and conducting agent, removing the accidental quality, and restoring the substance to a general or colorless state. 598. The extraction of color is also affected by reagents. Spirits of wine has a peculiar tendency to attract the juice which tinges plants, and becomes colored with it often in a very permanent manner. Sulfuric acid is very efficient in removing color, especially from wool and silk, and everyone is acquainted with the use of sulfur vapors in bleaching. 599. The strongest acids have been recommended more recently as more expeditious agents in bleaching. 600. The alkaline reagents produce the same effects by contrary means. Lixiviums alone, oils and fat combined with lixiviums to soap, and so forth. 601. Before we dismiss this subject, we observe that it may be well worth while to make certain delicate experiments as to how far light and air exhibit their action in the removal of color. It might be possible to expose colored substances to the light under glass bells, without air or filled with common or particular kinds of air. The colors might be those of known fugacity, and it might be observed whether any of the volatilized color attached itself to the glass or was otherwise perceptible as a deposit or precipitate. Whether, again, in such a case, this appearance would be perfectly like that which had gradually ceased to be visible, or whether it had suffered any change. Skillful experimentalists might devise various contrivances with a view to such researches. 602. Having thus first considered the operations of nature as subservient to our proposes, we add a few observations on the modes in which they act against us. 603. The art of painting is so circumstanced that the most beautiful results of mind and labor are altered and destroyed in various ways by time. Hence, great pains have been always taken to find durable pigments, and so to unite them with each other and with their ground, that their permanency might be further ensured. The technical history of the schools of painting affords sufficient information on this point. 604. We may here too mention a minor art to which, in relation to dyeing, we are much indebted, namely the weaving of tapestry. As the manufacturers were enabled to imitate the most delicate shades of pictures, and hence often brought the most variously colored materials together, it was soon observed that the colors were not all equally durable, but that some faded from the tapestry more quickly than others. Hence the most diligent efforts were made to ensure an equal permanency to all the colors and their gradations. This object was especially promoted in France under Colbert, whose regulations to this effect constitute an epoch in the history of dyeing. The gay dye, which only aimed at a transient beauty, was practiced by a particular guild. On the other hand, great pains were taken to define the technical processes which promised durability. And thus, after considering the artificial extraction, the evanescence, and the perishable nature of brilliant appearances of color, we are again returned to the desideratum of permanency. Section 49. Nomenclature. 605. After what has been adduced respecting the origin, the increase, and the affinity of colors, we may be better enabled to judge what nomenclature would be desirable in future, and what might be retained of that hitherto in use. 606. The nomenclature of colors, like all other modes of designation, but especially those employed to distinguish the objects of sense, proceeded in the first instance from particular to general, and from general back again to particular terms. The name of the species became a generic name to which the individual was again referred. 607. This method might have been followed in consequence of the mutability and uncertainty of ancient modes of expression, especially since, in the early ages, more reliance may be supposed to have been placed on the vivid impressions of sense. The qualities of objects were described indistinctly because they were impressed clearly on every imagination. 608. The pure chromatic circle was limited, it is true, but specific as it was, it appears to have been applied to innumerable objects, while it was circumscribed by qualifying characteristics. If we take a glance at the copiousness of the Greek and Roman terms, we shall perceive how mutable the words were, and how easily each was adapted to almost every point in the colorific circle. Note W. 609. In modern ages, terms for many new gradations were introduced in consequence of the various operations of dyeing. Even the colors of fashion and their designations represented an endless series of specific hues. We shall, on occasion, employ the chromatic terminology of modern languages, whence it will appear that the aim has gradually been to introduce more exact definitions, and to individualize and arrest a fixed and specific state by language equally distinct. 610. With regard to the German terminology, it has the advantage of possessing 4 monosyllabic names, no longer to be traced to their origin, viz. Yellow, gelb, blue, red, green. They represent the most general idea of color to the imagination, without reference to any very specific modification. 611. If we were to add 2 other qualifying terms to each of these 4, as thus red-yellow and yellow-red, red-blue and blue-red, yellow-green and green-yellow, blue-green and green-blue, we should express the gradations of the chromatic circle with sufficient distinctness. And if we were to add the designations of light and dark, and again define in some measure the degree of purity or its opposite by the monosyllables black, white, gray, brown, we should have a tolerably sufficient range of expressions to describe the ordinary appearances presented to us, without troubling ourselves whether they were produced dynamically or atomically. 612. The specific and proper terms in use might, however, still be conveniently employed, and we have thus made use of the words orange and violet. We have in like manner employed the word purpur to designate a pure central red, because the secretion of the murex or purpura is to be carried to the highest point of culmination by the action of the sunlight on fine linen saturated with the juice. End of section 31.
Section 32 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Recording by Chris Gray. Part L. Minerals. 613. The colours of minerals are all of a chemical nature, and thus the modes in which they are produced may be explained in a general way by what has been said on the subject of chemical colours. 614. Among the external characteristics of minerals, the description of their colours occupies the first place, and great pains have been taken, in the spirit of modern times, to define and arrest every such appearance exactly. By this means, however, new difficulties, it appears to us, have been created, which occasion no little inconvenience in practice. 615. It is true, this precision, when we reflect how it arose, carries with it its own excuse. The painter has at all times been privileged in the use of colours, the few specific hues, in themselves, admitted of no change, but from these innumerable gradations were artificially produced, which imitated the surface of natural objects. It was, therefore, not to be wondered at that these gradations should also be adopted as criterions, and that the artist should be invited to produce tinted patterns with which the objects of nature might be compared, and according to which they were to receive their designations. 616. But, after all, the terminology of colours which has been introduced in mineralogy is open to many objections. The terms, for instance, have not been borrowed from the mineral kingdom, as was possible enough in most cases, but from all kinds of visible objects. Too many specific terms have been adopted, and in seeking to establish new definitions by combining these, the nomenclators have not reflected that they thus altogether efface the image from the imagination, and the idea from the understanding. Lastly, these individual designations of colours, employed to a certain extent as elementary definitions, are not arranged in the best manner as regards their respective derivation from each other, Hence, the scholar must learn every single designation and impress an almost lifeless but positive language on his memory. The further consideration of this will be too foreign to our present subject. Footnote 1. These remarks have reference to the German mineralogical terminology -T. Part L.I. Plants 617. The colours of organic bodies in general may be considered as a higher kind of chemical operation, for which reason the ancients employed the word concoction to designate the process. All the elementary colours, as well as the combined and secondary hues, appear on the surface of organic productions, while on the other hand, the interior, if not colourless, appears, strictly speaking, negative when brought to the light. As we propose to communicate our views respecting organic nature, to a certain extent, in another place, we only insert here what has been before connected with the doctrine of colours, while it may serve as an introduction to the further consideration of the views alluded to, and first, of plants. 618. Seeds, bulbs, roots, and what is generally shut out from the light, or immediately surrounded by the earth, appear, for the most part, white. 619. Plants reared from seed, in darkness, are white or approaching to yellow. Light, on the other hand, in acting on their colours, acts at the same time on their form. 620. Plants which grow in darkness make, it is true, long shoots from joint to joint, but the stems between two joints are thus longer than they should be, no side stems are produced, and the metamorphosis of the plant does not take place. 621. Light, on the other hand, places it at once in an active state. The plant appears green, and the course of the metamorphosis proceeds uninterruptedly to the period of reproduction. 622. We know that the leaves of the stem are only preparations and pre-significations of the instruments of florification and fructification, and accordingly we can already see colours in the leaves of the stem which, as it were, announce the flower from afar, as in the case of the amaranthus. 623. There are white flowers whose petals have wrought or refined themselves to the greatest purity. There are coloured ones, in which the elementary hues may be said to fluctuate to and fro. There are some which, in tending to the higher state, have only partially emancipated themselves from the green of the plant. 624. Flowers of the same genus, and even of the same kind, are found of all colours. Roses, and particularly mallows, for example, vary through a great portion of the calorific circle from white to yellow, then through red-yellow to bright red, and from thence to the darkest hue it can exhibit as it approaches blue. 625. Others already begin from a higher degree in the scale, as, for example, the poppy, which is yellow-red in the first instance, and which afterwards approaches a violet hue. 626. Yet the same colours in species, varieties, and even in families and classes, if not constant, are still predominant, especially the yellow colour. Blue is throughout rarer. 627. A process somewhat similar takes place in the juicy capsule of the fruit, for it increases in colour from the green through the yellowish and yellow up to the highest red, the colour of the rind thus indicating the degree of ripeness. Some are coloured all round, some are only on the sunny side, in which last case the augmentation of the yellow into red, the gradations crowding in and upon each other, may be very well observed. 628. Many fruits, too, are coloured internally. Pure red juices, especially, are common. 629. The colour which is found superficially in the flower and penetratingly in the fruit spreads itself through all the remaining parts, colouring the roots and the juices of the stem, and this with a very rich and powerful hue. 630. So, again, the colour of the wood passes from yellow through the different degrees of red up to pure red and on to brown. Blue woods are unknown to me, and in this degree of organisation the active side exhibits itself powerfully, although both principles appear balanced in the general green of the plant. 631. We have seen above that the germ pushing from the earth is generally white and yellowish, but that by means of the action of light and air it acquires a green colour. The same happens with young leaves of trees, as may be seen, for example, in the birch, the young leaves of which are yellowish, and if boiled yield a beautiful yellow juice. Afterwards they become greener, while the leaves of other trees become gradually blue-green. 632. Thus a yellow ingredient appears to belong more essentially to leaves than a blue one, for this last vanishes in the autumn, and the yellow of the leaf appears changed to a brown colour. Still more remarkable, however, are the particular cases where leaves in autumn again become pure yellow, and others increase to the brightest red. 633. Other plants, again, may, by artificial treatment, be entirely converted to a colouring matter, which is as fine, active, and infinitely divisible as any other. Indigo and madder, with which so much is effected, are examples. Lichens are also used for dyes. 634. To this fact another stands immediately opposed. We can, namely, extract the colouring parts of plants, and, as it were, exhibit it apart, while the organisation does not on this account appear to suffer at all. The colours of flowers may be extracted by spirits of wine, and tinge it, the petals meanwhile becoming white. 635. There are various modes of acting on flowers and their juices by reagents. This has been done by Boyle and in many experiments. Roses are bleached by sulphur, and may be restored to their first state by other acids. Roses are turned green by the smoke of tobacco. End of section 32. Recording by Chris Gray, CG Systems and Gadgets, and Plants for Pussycats.
Section 33 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Gillian Hendry. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 33. 52. Worms, insects, fishes. 636. With regard to creatures belonging to the lower degrees of organisation, we may first observe that worms, which live in the earth and remain in darkness and cold moisture, are imperfectly negatively coloured. Worms bred in warm moisture and darkness are colourless. Light seems expressly necessary to the definite exhibition of colour. 637. Creatures which live in water, which, although a very dense medium, suffers sufficient light to pass through it, appear more or less coloured. Zoophytes, which appear to animate the purest calcareous earth, are mostly white, yet we find corals deepened into the most beautiful yellow-red. In other cells of worms this colour increases nearly to bright red. 638. The shells of the crustaceous tribe are beautifully designed and coloured, yet it is to be remarked that neither land snails nor the shells of crustacea of fresh water are adorned with such bright colours as those of the sea. 639. In examining shells, particularly such as are spiral, we find that a series of animal organs, similar to each other, must have moved increasingly forward, and in turning on an axis produced the shell in a series of chambers, divisions, tubes, and prominences, according to a plan for ever growing larger. We remark, however, that a tinging juice must have accompanied the development of these organs, a juice which marked the surface of the shell, probably through the immediate cooperation of the sea water, with coloured lines, points, spots, and shadings. This must have taken place at regular intervals, and thus left the indications of increasing growth lastingly on the exterior. Meanwhile the interior is generally found white or only faintly coloured. 640. That such a juice is to be found in shellfish is besides sufficiently proved by experience, for the creatures furnish it in its liquid and colouring state. The juice of the inkfish is an example, but a much stronger is exhibited in the red juice found in many shellfish, which was so famous in ancient times, and has been employed with advantage by the moderns. There is, it appears, in the entrails of many of the crustaceous tribe a certain vessel which is filled with a red juice. This contains a very strong and durable colouring substance, so much so that the entire creature may be crushed and boiled, and yet out of this broth a sufficiently strong tinging liquid may be extracted. But the little vessel filled with colour may be separated from the animal, by which means, of course, a concentrated juice is gained. 641. This juice has the property that when exposed to light and air it appears first yellowish, then greenish. It then passes to blue, then to a violet, gradually growing redder, and lastly, by the action of the sun, and especially if transferred to cambric, it assumes a pure bright red colour. 642. Thus we should here have an augmentation, even to culmination, on the minus side, which we cannot easily meet with in inorganic cases. Indeed, we might almost call this example a passage through the whole scale, and we are persuaded that by due experiments the entire revolution of the circle might really be effected, for there is no doubt that by acids duly employed the pure red may be pushed beyond the culminating point towards scarlet. 643. This juice appears on the one hand to be connected with the phenomena of reproduction, eggs being found, the embryos of future shellfish, which contain a similar colouring principle. On the other hand, in animals ranking higher in the scale of being, the secretion appears to bear some relation to the development of the blood. The blood exhibits similar properties in regard to colour. In its thinnest state it appears yellow, thickened, as it is found in the veins, it appears red, while the arterial blood exhibits a brighter red, probably owing to the oxidation which takes place by means of breathing. The venous blood approaches more to violet, and by this mutability denotes the tendency to that augmentation and progression which are now familiar to us. 644. Before we quit the element whence we derived the foregoing examples, we may add a few observations on fishes, whose scaly surface is coloured either altogether in stripes or in spots, and still oftener exhibits a certain iridescent appearance, indicating the affinity of the scales with the coats of shellfish, mother of pearl, and even the pearl itself. At the same time, it should not be forgotten that warmer climates, the influence of which extends to the watery regions, produce, embellish, and enhance these colours in fishes in a still greater degree. 645. In Otaheite, Forster observed fishes with beautifully iridescent surfaces, and this effect was especially apparent at the moment when the fish died. We may here call to mind the hues of the chameleon and other similar appearances, for when similar facts are presented together, we are better enabled to trace them. 646. Lastly, although not strictly in the same class, the iridescent appearance of certain molluscae may be mentioned, as well as the phosphorescence which in some marine creatures, it is said, becomes iridescent just before it vanishes. 647. We now turn our attention to those creatures which belong to light, air, and dry warmth, and it is here that we first find ourselves in the living region of colours. Here, in exquisitely organised parts, the elementary colours present themselves in their greatest purity and beauty. They indicate, however, that the creatures they adorn are still low in the scale of organisation, precisely because these colours can thus appear, as it were, unwrought. Here, too, heat seems to contribute much to their development. 648. We find insects which may be considered altogether as concentrated colouring matter. Among these, the cochineals especially are celebrated. With regard to these, we observe that their mode of settling on vegetables, and even nestling in them, at the same time produces these excrescences which are so useful as mordants in fixing colours. 649. But the power of colour, accompanied by regular organisation, exhibits itself in the most striking manner in those insects which require a perfect metamorphosis for their development, in Scarabaei, and especially in butterflies. 650. These last, which might be called true productions of light and air, often exhibit the most beautiful colours. even in their chrysalis state, indicating the future colours of the butterfly, a consideration which, if pursued further hereafter, must undoubtedly afford a satisfactory insight into many a secret of organised being. 651. If again we examine the wings of the butterfly more accurately, and in its net-like web discover the rudiments of an arm, and observe further the mode in which this, as it were, flattened arm is covered with tender plumage and constituted an organ of flying, we believe we recognise a law according to which the great variety of tints is regulated. This will be a subject for further investigation hereafter. 652. That again heat generally has an influence on the size of the creature, on the accomplishment of the form, and on the greater beauty of the colours, hardly needs to be remarked. 53. Birds. 653. The more we approach the higher organisations, the more it becomes necessary to limit ourselves to a few passing observations, for all the natural conditions of such organised beings are the result of so many premises, that, without having at least hinted at these, our remarks would only appear daring, and at the same time insufficient. 654. We find in plants that the consummate flower and fruit are, as it were, rooted in the stem, and that they are nourished by more perfect juices than the original roots first afforded. We remark too that parasitical plants, which derive their support from organised structures, exhibit themselves especially endowed as to their energies and qualities. We might in some sense compare the feathers of birds with plants of this description. The feathers spring up as a last structural result from the surface of a body which has yet much in reserve for the completion of the external economy, and thus are very richly endowed organs. 655. The quills not only grow proportionally to a considerable size, but are throughout branched, by which means they properly become feathers, and many of these feathered branches are again subdivided, thus again recalling the structure of plants. 656. The feathers are very different in shape and size, but each still remains the same organ, forming and transforming itself according to the constitution of the part of the body from which it springs. 657. With the form, the colour also becomes changed, and a certain law regulates the general order of hues, as well as that particular distribution by which a single feather becomes partly coloured. It is from this that all combination of variegated plumage arises, and whence at last the eyes in the peacock's tail are produced. It is a result similar to that which we have already unfolded in treating of the metamorphosis of plants, and which we shall take an early opportunity to prove. 658. Although time and circumstances compel us here to pass by this organic law, yet we are bound to refer to the chemical operations which commonly exhibit themselves in the tinting of feathers in a mode now sufficiently known to us. 659. Plumage is of all colours, yet on the whole yellow deepening to red is commoner than blue. 660. The operation of light on the feathers and their colours is to be remarked in all cases. Thus, for example, the feathers on the breast of certain parrots are strictly yellow. The scale-like anterior portion, which is acted on by the light, is deepened from yellow to red. The breast of such a bird appears bright red, but if we blow into the feathers, the yellow appears. 661. The exposed portion of the feathers is in all cases very different from that which, in a quiet state, is covered. It is only the exposed portion, for instance in ravens, which exhibits the iridescent appearance. The covered portion does not, from which indication the feathers of the tail, when ruffled together, may be at once placed in the natural order again. End of section 33.
Section 34 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jennifer Painter. Theory of Colours by Johann Wolfgang von Goethe, translated by Charles Eastlake. Section 34. Mammalia and Human Beings. Paragraph 662. Here the elementary colours begin to leave us altogether. We are arrived at the highest degree of the scale, and shall not dwell on its characteristics long. Paragraph 663. An animal of this class is distinguished among the examples of organised being. Everything that exhibits itself about him is living. Of the internal structure we do not speak, but confine ourselves briefly to the surface. The hairs are already distinguished from feathers, inasmuch as they belong more to the skin, inasmuch as they are simple, thread-like, not branched. They are, however, like feathers, shorter, longer, softer, and firmer, colourless or coloured, and all this in conformity to laws which might be defined. Paragraph 664. White and black, yellow, yellow-red, and brown alternate in various modifications, but they never appear in such a state as to remind us of the elementary hues. On the contrary, they are all broken colours subdued by organic concoction, and thus denote, more or less, the perfection of life in the being they belong to. Paragraph 665. One of the most important considerations connected with morphology, so far as it relates to surfaces, is this, that even in quadrupeds the spots of the skin have a relation with the parts underneath them. Capriciously as nature here appears, on a hasty examination, to operate, she nevertheless consistently observes a secret law. The development and application of this, it is true, are reserved only for accurate and careful investigation and sincere co-operation. Paragraph 666. If in some animals portions appear variegated with positive colours, this of itself shows how far such creatures are removed from a perfect organisation, for, it may be said, the nobler a creature is, the more all the mere material of which he is composed is disguised by being wrought together, the more essentially his surface corresponds with the internal organisation, the less can it exhibit the elementary colours. Where all tends to make up a perfect whole, any detached specific developments cannot take place. Paragraph 667. Of man we have little to say, for he is entirely distinct from the general physiological results of which we now treat. So much in this case is in affinity with the internal structure, that the surface can only be sparingly endowed. Paragraph 668. When we consider that brutes are rather encumbered than advantageously provided with intercutaneous muscles, when we see that much that is superfluous tends to the surface, as, for instance, large ears and tails, as well as hair, manes, tufts, we see that nature, in such cases, has much to give away and to lavish. Paragraph 669. On the contrary, the general surface of the human form is smooth and clean, and thus in the most perfect examples the beautiful forms are apparent. For it may be remarked in passing, that a superfluity of hair on the chest, arms, and lower limbs rather indicates weakness than strength. Poets only have sometimes been induced, probably by the example of the ferine nature, so strong in other respects, to extol similar attributes in their rough heroes. Paragraph 670. But we have here chiefly to speak of colour, and observe that the colour of the human skin, in all its varieties, is never an elementary colour, but presents, by means of organic concoction, a highly complicated result. Footnote. This agrees with the general recommendation so often given by high authorities in art to avoid a tinted look in the colour of flesh. The great example of Rubens, whose practice was sometimes an exception to this, may however show that no rule of art is to be blindly or exclusively adhered to. Reynolds, nevertheless, in the midst of his admiration for this great painter, considered the example dangerous, and more than once expresses himself to this effect, observing on one occasion that Rubens, like Baroccio, is sometimes open to the criticism made on an ancient painter, namely, that his figures look as if they fed on roses. Lodovico Dolce, who is supposed to have given the viva voce precepts of Titian in his dialogue, makes Aretino say, "I would generally banish from my pictures those vermilion cheeks with coral lips, for faces thus treated look like masks." Propertius, reproving his Cynthia for using cosmetics, desires that her complexion might exhibit the simplicity and purity of colour which is seen in the works of Apelles. Those who have written on the practice of painting have always recommended the use of few colours for flesh. Reynolds and others quote even ancient authorities as recorded by Pliny, and Boschini gives several descriptions of the method of the Venetians, and particularly of Titian, to the same effect. They used, he says, earths more than any other colour, and at the utmost only added a little vermilion, minium, and lake, abhorring as a pestilence biadetti, gialli santi, smaltini, verdi azzurri, giallolini. Elsewhere, he says, earth should be used rather than other colours. After repeating the above prohibited list, he adds, "I speak of the imitation of flesh, for in other things every colour is good." Again, our great Titian used to say that he who wishes to be a painter should be acquainted with 3 colours, white, black, and red. Assuming this account to be a little exaggerated, it is still to be observed that the monotony to which the use of few colours would seem to tend is prevented by the nature of the Venetian process, which was sufficiently conformable to Goethe's doctrine, the gradations being multiplied, and the effect of the colours heightened by using them as semi-opaque mediums. Immediately after the passage last quoted, we read, "He also gave this true precept, that to produce a lively colouring in flesh it is not possible to finish at once." As these particulars may not be known to all, we add some further abridged extracts, explaining the order and methods of these different operations. The Venetian painters, says this writer, after having drawn in their subject, go in the masses with very solid colour, without making use of nature or statues. Their great object in this stage of their work was to distinguish the advancing and retiring portions, that the figures might be relieved by means of chiaroscuro, one of the most important departments of colour and form, and indeed of invention. Having decided on their scheme of effect, when this preparation was dry, they consulted nature and the antique, not servilely, but with the aid of a few lines on paper, quattro segni in carta. They corrected their figures without any other model. Then returning to their brushes, they began to paint smartly on this preparation, producing the colour of flesh. The passage before quoted follows, stating that they used earths chiefly, that they carefully avoided certain colours, and likewise varnishes and whatever produces a shining surface. When this second painting was dry, they proceeded to scumble over this or that figure with a low tint, to make the one next to it come forward, giving another at the same time additional light, for example, on a head, a hand, or a foot, thus detaching them, so to speak, from the canvas. Tintoret's Prigione di Santa Rocco is here quoted. By thus still multiplying these well understood retouchings where required, on the dry surface, a secco, they reduced the whole to harmony. In this operation they took care not to cover entire figures, but rather went on gemming them, giolilandole, with vigorous touches. In the shadows, too, they infused vigour frequently by glazing with asphaltum, always leaving great masses in middle tint, with many darks, in addition to the partial glazings and few lights. The introduction to the subject of Venetian colouring, in the poem by the same author, is also worth transcribing, but as the style is quaint and very concise, a translation is necessarily a paraphrase. The art of colouring has the imitation of qualities for its object. Not all qualities, but those secondary ones which are appreciable by the sense of sight. The eye especially sees colours. The imitation of nature in painting is therefore justly called colouring, but the painter arrives at his end by indirect means. He gives the varieties of tone in masses, he smartly impinges lights, he clothes his preparation with more delicate local hues. He unites, he glazes. Thus everything depends on the method, on the process. For if we look at colour abstractedly, the most positive may be called the most beautiful. But if we keep the end of imitation in view, this shallow conclusion falls to the ground. The refined Venetian manner is very different from mere direct, sedulous imitation. Every one who has a good eye may arrive at such results, but to attain the manner of Paolo, of Bassan, of Palma, Tintoret, or Titian, is a very different undertaking. The effects of semi-transparent mediums in some natural productions seem alluded to in the following passage. Nature sometimes accidentally imitates figures in stones and other substances, and although they are necessarily incomplete in form, yet the principle of effect, or depth, resembles the Venetian practice. In a passage that follows, there appears to be an allusion to the production of the atmospheric colours by semi-transparent mediums. End of footnote. Paragraph 671. That the colour of the skin and hair has relation with the differences of character is beyond question, and we are led to conjecture that the circumstance of one or other organic system predominating produces the varieties we see. A similar hypothesis may be applied to nations, in which case it might perhaps be observed that certain colours correspond with certain conformations, which has always been observed of the negro physiognomy. Paragraph 672. Lastly, we might here consider the problematical question whether all human forms and hues are not equally beautiful, and whether custom and self-conceit are not the causes why one is preferred to another. We venture, however, after what has been adduced, to assert that the white man, that is, he whose surface varies from white to reddish, yellowish, brownish, in short, whose surface appears most neutral in hue and least inclines to any particular or positive colour, is the most beautiful. On the same principle, a similar point of perfection in human conformation may be defined hereafter, when the question relates to form. We do not imagine that this long disputed question is to be thus once for all settled, for there are persons enough who have reason to leave this significancy of the exterior in doubt. But we thus express a conclusion, derived from observation and reflection, such as might suggest itself to a mind aiming at a satisfactory decision. We subjoin a few observations connected with the elementary chemical doctrine of colours. Footnote. The author's conclusion here is unsatisfactory, for the colour of the black races may be considered at least quite as negative as that of Europeans. It would be safer to say that the white skin is more beautiful than the black, because it is more capable of indications of life and indications of emotion. A degree of light which would fail to exhibit the finer varieties of form on a dark surface would be sufficient to display them on a light one, and the delicate mantlings of colour, whether the result of action or emotion, are more perceptible for the same reason. End of footnote. End of section 34.
Section 35 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Part LV. Physical and chemical effects of the transmission of light through coloured mediums. 673. The physical and chemical effects of colourless light are known, so that it is unnecessary here to describe them at length. Colourless light exhibits itself under various conditions as exciting warmth, as imparting a luminous quality to certain bodies, as promoting oxidation and deoxidation. In the modes and degrees of these effects, many varieties take place, but no difference is found indicating a principle of contrast such as we find in the transmission of coloured light. We proceed briefly to advert to this. 674. Let the temperature of a dark room be observed by means of a very sensible air thermometer. If the bulb is then brought to the direct sunlight, as it shines into the room, nothing is more natural than that the fluid should indicate a much higher degree of warmth. If upon this we interpose coloured glasses, it follows again quite naturally that the degree of warmth must be lowered. First, because the operation of the direct light is already somewhat impeded by the glass, and again, more especially, because a coloured glass, as a dark medium, admits less light through it. 675. But here a difference in the excitation of warmth exhibits itself to the attentive observer, according to the colour of the glass. The yellow and the yellow-red glasses produce a higher temperature than the blue and blue-red, the difference being considerable. 676. This experiment may be made with the prismatic spectrum. The temperature of the room being first remarked on the thermometer, the blue coloured light is made to fall on the bulb, when a somewhat higher degree of warmth is exhibited, which still increases as the other colours are gradually brought to act on the mercury. If the experiment is made with the water prism, so that the white light can be retained in the centre, this, refracted indeed, but not yet coloured light, is the warmest, and the other colours stand in relation to each other as before. 677. As we here merely describe, without undertaking to deduce or explain this phenomenon, we only remark in passing that the pure light is by no means abruptly and entirely at an end with the red division in the spectrum, but that a refracted light is still to be observed deviating from its course and, as it were, insinuating itself beyond the prismatic image, so that on closer examination it will hardly be found necessary to take refuge in invisible rays and their refraction. 678. The communication of light by means of coloured mediums exhibits the same difference. The light communicates itself to Bologna phosphorus through blue and violet glasses, but by no means through yellow and yellow-red glasses. It has been even remarked that the phosphori which have been rendered luminous under violet and blue glasses become sooner extinguished when afterwards placed under yellow and yellow-red glasses than those which have been suffered to remain in a dark room without any further influence. 679. These experiments, like the foregoing, may also be made by means of the prismatic spectrum when the same results take place. 680. To ascertain the effect of coloured light on oxidation and deoxidation, the following means may be employed. Let moist, perfectly white muriate of silver be spread on a strip of paper. Place it in the light so that it may become to a certain degree grey, and then cut it in 3 portions. Of these, one may be preserved in a book, as a specimen of this state. Let another be placed under a yellow-red, and the third under a blue-red glass. The last will become a darker grey, and exhibit a deoxidation. The other, under the yellow-red glass, will, on the contrary, become a lighter grey, and thus approach nearer to the original state of more perfect oxidation. The change in both may be ascertained by a comparison with the unaltered specimen. 681. An excellent apparatus has been contrived to perform these experiments with the prismatic image. The results are analogous to those already mentioned, and we shall hereafter give the particulars, making use of the labours of an accurate observer, who has been for some time carefully prosecuting these experiments. Translator's footnote, see back. Part LVI. Chemical effect in dioptrical achromatism. 682. We first invite our readers to turn to what has been before observed on this subject, to avoid unnecessary repetition here. 683. We can thus give a glass the property of producing much wider coloured edges without refracting more strongly than before, that is, without displacing the object much more perceptibly. 684. This property is communicated to the glass by means of metallic oxides. Minium, melted and thoroughly united with a pure glass, produces this effect, and thus flint glass is prepared with oxide of lead. Experiments of this kind have been carried farther, and the so-called butter of antimony, which, according to a new preparation, may be exhibited as a pure fluid, has been made use of in hollow lenses and prisms, producing a very strong appearance of colour with a very moderate refraction, and presenting the effect which we have called hyperchromatism in a very vivid manner. 685. In common glass, the alkaline nature obviously preponderates, since it is chiefly composed of sand and alkaline salts. Hence a series of experiments exhibiting the relation of perfectly alkaline fluids to perfect acids might lead to useful results. 686. For, could the maximum and minimum be found, it would be a question whether a refracting medium could not be discovered, in which the increasing and diminishing appearance of colour, an effect almost independent of refraction, could not be done away with altogether, while the displacement of the object would be unaltered. 687. How desirable, therefore, it would be with regard to this last point, as well as for the elucidation of the whole of this third division of our work, and, indeed, for the elucidation of the doctrine of colours generally, that those who are occupied in chemical researches, with new views ever opening to them, should take this subject in hand, pursuing into more delicate combinations what we have only roughly hinted at, and prosecuting their inquiries with reference to science as a whole. End of section 35. Recording by Chris Gray, CG Systems and Gadgets, and Plants for Pussycats.
Section 36 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Brianna. Theory of Colors by Johann Wolfgang van Goethe. Translated by Charles Eastlake, 1810. General Characteristics 688. We have hitherto, in a manner forcibly, kept phenomena asunder, which partly from their nature, partly in accordance with our mental habits, have, as it were, constantly sought to be reunited. We have exhibited them in three divisions. We have considered colours, first as transient, the result of an action and reaction in the eye itself; next as passing effects of colourless, light-transmitting, transparent and opaque mediums on light, especially on the luminous image. Lastly, we arrived at the point where we could securely pronounce them as permanent and actually inherent in bodies. 689. In following this order, we have as far as possible endeavored to define, to separate, and to class the appearances. But now that we need no longer be apprehensive of mixing and confounding them, we may proceed, first, to state the general nature of these appearances considered abstractedly, as an independent circle of facts, and in the next place to show how this particular circle is connected with other classes of analogous phenomena in nature. The facility with which colour appears. We have observed that colour, under many conditions, appears very easily. The susceptibility of this eye with regard to light, the constant reaction of the retina against it, produce instantaneously a slight iridescence. Every subdued light may be considered as coloured, nay, we ought to call any light coloured, inasmuch as it is seen. Colourless light, colourless surfaces are in some sort abstract ideas. In actual experience we can hardly be said to be aware of them. 691. If light impinges on a colourless body, is reflected from it, or passes through it, colour immediately appears. But it is necessary here to remember what has been so often urged by us, namely that the leading conditions of refraction, reflection, and so on, are not of themselves sufficient to produce the appearance. Sometimes, it is true, light acts as these merely as light, but oftener as a defined, circumscribed appearance, as a luminous image. The semi-opacity of the medium is often a necessary condition, while half the double shadows are required for many coloured appearances. In all cases, however, colour appears instantaneously. We find, again, that by means of pressure, breathing heat, by various kinds of motion and alteration on smooth clean surfaces, as well as on colourless fluids, colour is immediately produced. 692. The slightest change has only to take place to component parts of bodies, whether by immixture with other particles or to such effects, and colour either makes its appearance or becomes changed. The force of colour. 693. The physical colours, and especially those of the prism, were formerly called colores infatici, on account of their extraordinary beauty and force. Strictly speaking, however, a high degree of effect may be ascribed to all appearances of colour, assuming that they are exhibited under the purest and most perfect conditions. 694. The dark nature of colour, its full rich quality, and what produces the grave and at the same time fascinating impression we sometimes experience, and as colour is to be considered a condition of light, so it cannot dispense with light as the co-operating cause of its appearance, as its basis or ground, as a power thus displaying and manifesting colour. The definite nature of colour. 695. The existence and the relatively definite character of colour are one and the same thing. Light displays itself in the face of nature, and it were with a general indifference, informing us to surrounding objects, perhaps devoid of interest or importance. But colour is at all times specific, characteristic, and significant. 696. Considered in a general point of view, colour is determined towards one of the two sides,
It thus presents a contrast which we call polarity, and which we may fitly designate by the expressions plus and minus. Plus yellow, minus blue. Plus action, minus negation. Plus light, minus shadow. Plus brightness, minus darkness. Plus force, minus weakness. Plus warmth, minus coldness. Plus proximity, minus distance. Plus repulsion, minus attraction. Plus affinity with acids, minus affinity with alkalis. Combination of the two principles, 697. If these specific contrasted principles are combined, the respective qualities do not therefore destroy each other. For if in this intermixture the ingredients are so perfectly balanced that neither is to be distinctly recognized, the union again acquires a specific character. It appears as a quality by itself in which we no longer think of a combination. The union we call green. 698. Thus, if two opposite phenomena springing from the same source do not destroy each other when combined, but in their union present a third appreciable and pleasing appearance, this result at once indicates their harmonious relation. The more perfect result yet remains to be adverted to. Augmentation to red. 699. Blue and yellow do not admit of increased intensity without presently exhibiting a new appearance in addition to their own. Each color, in its lightest state, is a dark. If condensed, it must become darker, but this effect no sooner takes place than the hue assumes an appearance which we designated by the word reddish. 700. This appearance still increases, so that when the highest degree of intensity is attained, it predominates over the original hue. A powerful impression of light leaves the sensation of red on the retina. In the prismatic yellow-red which springs directly from the yellow, we hardly recognize the yellow. 701. This deepening takes place again by means of colorless semi-transparent mediums, and here we see the effect in its utmost purity and extent. Transparent fluids, colored with any given hues in a series of glass vessels, exhibit it very strikingly. The augmentation is unremittingly repaid and constant. It is universal and obtains in physiological as well as physical and chemical colors. Junction of two augmented extremes. 702. As the extremes of the simple contrasts produce a beautiful and agreeable appearance by their union, so the deepened extremes on being united will present a still more fascinating color. Indeed, it might naturally be expected that we should here find the acme of the whole phenomenon. Completeness the result of variety. 703. And such is the fact, for pure red appears a color to which, from its excellence, we have appropriated the term purple. 704. There are various modes in which pure red may appear,
by bringing together the violet edge and the yellow-red border in prismatic experiments, by continued augmentation and chemical operations, and by the organic contrast in physiological effects. 705. As a pigment, it cannot be produced by intermixture or union, but only by arresting the hue in substances chemically acted on, at a high culminating point. Hence, the painter is justified in assuming that there are three primitive colours from which he combines all the others. The natural philosopher, on the other hand, assumes only two elementary colours from which he, in like manner, develops and combines the rest. Completeness the result of variety in colour. 706. The various appearances of colour, arrested in their different degrees, and seen in juxtaposition, produce a whole. This totally is harmony to eye. 707. The chromatic circle has been gradually presented to us. The various relations of its progression are apparent to us. Two pure original principles in contrast are the foundation of the whole. An augmentation manifests itself by means of which both approach a third state. Hence, there exists on both sides a lowest and highest, a simplest and most qualified state. Again, two combinations present themselves. First, that of the simple primitive contrasts, then that of the deepened contrasts. Harmony of the complete state. 708. The whole ingredients of the chromatic scale, seen in juxtaposition, produce an harmonious impression on the eye. The difference between the physical contrast and the harmonious opposition in all its extent should not be overlooked. The first resides in the pure restricted original dualism, considered in its antagonizing elements. The other results from the fully developed effects of the complete state. 709. Every single opposition, in order to be harmonious, must comprehend the whole. The physiological experiments are sufficiently convincing on this point. A development of all the possible contrasts of the chromatic scale will be shortly given. Facility with which colour may be made to tend either to the plus or minus side. 710. We have already had occasion to take notice of the mutability of colour in considering its so-called augmentation and progressive variations round the whole circle. But the hues even pass and repass from one side to the other, rapidly and of necessity. 711. Physiological colours are different in appearance as they happen to fall on a dark or on a light ground. In physical colours, the combination of the objective and subjective experiments is very remarkable. The optical colours, it appears, are contrasted according to the light shines through or upon them. To what extent the chemical colours may be changed by fire and alkalis has been sufficiently shown in its proper place. Evanescence of colour. 712. All that has been adverted to as subsequent to the rapid excitation and definition of colour, in mixture, augmentation, combination, separation, not forgetting the law of compensatory harmony, all takes place with the greatest rapidity and facility, but with equal quickness color again altogether disappears. 713. The physiological appearances are in no wise to be arrested. The physical lasts only as long as the external condition lasts. Even the chemical colours have great mutability. They may be made to pass and repass from one side to the other by means of opposite reagents, and may even be annihilated altogether. Permanence of colour. The chemical colours afford evidence of very great duration. Colours fixed in a glass by fusion and by nature in gems defy all time and reaction. 715. The art of dyeing again fixes colour very powerfully. The hues of pigments which might otherwise be easily rendered mutable by reagents may be communicated to substances in the greatest permanency by means of mordants. End of section 4. Recording by Brianna.
Section 37 of Theory of Colours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 37. Part 5. Relation to other pursuits. Relation to philosophy. 716. The investigator of nature cannot be required to be a philosopher, but it is expected that he should so far have attained the habit of philosophizing as to distinguish himself essentially from the world, in order to associate himself with it again in a higher sense. He should form to himself a method in accordance with observation, but he should take heed not to reduce observation to mere notion, to substitute words for this notion, and to use and deal with these words as if they were things. He should be acquainted with the labours of philosophers in order to follow up the phenomena which have been the subject of his observation into the philosophic region. 717. It cannot be required that the philosopher should be a naturalist, and yet his cooperation in physical researches is as necessary as it is desirable. He needs not an acquaintance with details for this, but only a clear view of those conclusions where insulated facts meet. 718. We have before, number 175, alluded to this important consideration, and repeat it here where it is in its place. The worst that can happen to physical science, as well as to many other kinds of knowledge, is that men should treat a secondary phenomenon as a primordial one, and, since it is impossible to derive the original fact from the secondary state, seek to explain what is in reality the cause by an effect made to usurp its place. Hence arises an endless confusion, a mere verbiage, a constant endeavour to seek and to find subterfuges whenever truth presents itself and threatens to be overpowering. 719. While the observer, the investigator of nature, is thus dissatisfied in finding that the appearances he sees still contradict a received theory, the philosopher can calmly continue to operate in his abstract department on a false result, for no result is so false but that it can be made to appear valid, as form without substance by some means or other. 720. If, on the other hand, the investigator of nature can attain to the knowledge of that which we have called a primordial phenomenon, he is safe, and the philosopher with him. The investigator of nature is safe, since he is persuaded that he has here arrived at the limits of his science, that he finds himself at the height of experimental research. a height whence he can look back upon the details of observation in all its steps, and forwards into, if he cannot enter, the regions of theory. The philosopher is safe, for he receives from the experimentalist an ultimate fact, which in his hands now becomes an elementary one. He now justly pays little attention to appearances which are understood to be secondary, whether he already finds them scientifically arranged, or whether they present themselves to his causal observation scattered and confused. Should he even be inclined to go over this experimental ground himself, and not be averse to examination in detail, he does this conveniently, instead of lingering too long in the consideration of secondary and intermediate circumstances, or hastily passing them over without becoming accurately acquainted with them. 721. To place the doctrine of colours nearer, in this sense, within the philosopher's reach, was the author's wish, and although the execution of his purpose, from various causes, does not correspond with his intention, he will still keep this object in view in an intended recapitulation, as well as in the polemical and historical portions of his work, for he will have to return to the consideration of this point hereafter, on an occasion where it will be necessary to speak with less reserve. Relation to mathematics. 722. It may be expected that the investigator of nature, who proposes to treat the science of natural philosophy in its entire range, should be a mathematician. In the Middle Ages, mathematics was the chief organ by means of which men hoped to master the secrets of nature, and even now, geometry in certain departments of physics is justly considered of first importance. The author can boast of no attainments of this kind, and on this account confines himself to departments of science which are independent of geometry, departments which in modern times have been opened up far and wide. 724. It will be universally allowed that mathematics, one of the noblest auxiliaries which can be employed by man, has, in one point of view, been of the greatest use to the physical sciences, but that, by a false application of its methods, it has in many respects been prejudicial to them, is also not to be denied. We find it here and there reluctantly admitted. 725. The theory of colours, in particular, has suffered much, and its progress has been incalculably retarded by having been mixed up with optics generally, a science which cannot dispense with mathematics, whereas the theory of colours, in strictness, may be investigated quite independently of optics. 726. But besides this, there was an additional evil. A great mathematician was possessed with an entirely false notion on the physical origin of colours, yet, owing to his great authority as a geometer, the mistakes which he committed as an experimentalist long became sanctioned in the eyes of a world ever fettered in prejudices. 727. The author of the present inquiry has endeavoured throughout to keep the theory of colours distinct from the mathematics, although there are evidently certain points where the assistance of geometry would be desirable. Had not the unprejudiced mathematicians with whom he has had, or still has, the good fortune to be acquainted, been prevented by other occupations from making common cause with him, his work would not have wanted some merit in this respect. But this very want may be in the end advantageous, since it may now become the object of the enlightened mathematician to ascertain where the doctrine of colours is in need of his aid, and how he can contribute the means at his command with a view to the complete elucidation of this branch of physics. 728. In general, it were to be wished that the Germans, who render such good service to science, while they adopt all that is good from other nations, could by degrees accustom themselves to work in concert. We live, it must be confessed, in an age the habits of which are directly opposed to such a wish. Every one seeks not only to be original in his views, but to be independent of the labours of others, or at least to persuade himself that he is so, even in the course of his life and occupation. It is very often remarked that men who undoubtedly have accomplished much quote themselves only, their own writings, journals, and compendiums, whereas it would be far more advantageous for the individual and for the world if many were devoted to a common pursuit. The conduct of our neighbours, the French, is, in this respect, worthy of imitation. We have a pleasing instance in Cuvier's preface to his Tableau élémentaire de l'histoire naturelle des animaux. 729. He who has observed science and its progress with an unprejudiced eye might even ask whether it is desirable that so many occupations and aims, though allied to each other, should be united in one person, and whether it would not be more suitable for the limited powers of the human mind to distinguish, for example, the investigator and inventor from him who employs and applies the result of experiment? Astronomers, who devote themselves to the observation of the heavens and the discovery or enumeration of stars, have in modern times formed, to a certain extent, a distinct class from those who calculate the orbits, consider the universe in its connection, and more accurately define its laws. The history of the doctrine of colours will often lead us back to these considerations. Relation to the technical operations of the dyer. 730. If in our labours we have gone out of the province of the mathematician, we have, on the other hand, endeavoured to meet the practical views of the dyer, and although the chapter which treats of colour in a chemical point of view is not the most complete and circumstantial, yet in that portion, as well as in our general observations respecting colour, the dyer will find his views assisted far more than by the theory hitherto in vogue, which failed to afford him any assistance. 731. It is curious, in this view, to take a glance at the works containing directions on the art of dyeing. As the Catholic, on entering his temple, sprinkles himself with holy water, and after bending the knee, proceeds perhaps to converse with his friends on his affairs, without any especial devotion, so all the treatises on dyeing begin with a respectful allusion to the accredited theory, without afterwards exhibiting a single trace of any principle deduced from this theory, or showing that it has thrown light on any part of the art, or that it offers any useful hints in furtherance of practical methods. 732. On the other hand, there are men who, after having become thoroughly and experimentally acquainted with the nature of dyes, have not been able to reconcile their observations with the received theory, who have, in short, discovered its weak points, and sought for a general view more consonant to nature and experience. When we come to the names of Castell and Gulich in our historical review, we shall have occasion to enter into this more fully, and an opportunity will then present itself to show that an assiduous experience in taking advantage of every accident may, in fact, be said almost to exhaust the knowledge of the province to which it is confined. The high and complete result is then submitted to the theorist, who, if he examines facts with accuracy and reasons with candour, will find such materials eminently useful as a basis for his conclusions. Relation to physiology and pathology. 733. If the phenomena adduced in the chapter where colours were considered in a physiological and pathological view are for the most part generally known, still some new views, mixed up with them, will not be unacceptable to the physiologist. We especially hope to have given him cause to be satisfied by classing certain phenomena which stood alone, under analogous facts, and thus, in some measure, to have prepared the way for his further investigations. 734. The appendix on pathological colours, again, is admitted to be scanty and unconnected. We reflect, however, that Germany can boast of men who are not only highly experienced in this department, but are likewise so distinguished for general cultivation, that it can cost them but little to revise this portion to complete what has been sketched, and at the same time to connect it with the higher facts of organization. Relation to natural history. 735. If we may at all hope that natural history will gradually be modified by the principle of deducing the ordinary appearances of nature from higher phenomena, the author believes he may have given some hints and introductory views bearing on this object also. As colour, in its infinite variety, exhibits itself on the surface of living beings, it becomes an important part of the outward indications, by means of which we can discover what passes underneath. 736. In one point of view it is certainly not to be too much relied on account of its indefinite and mutable nature. Yet even this mutability, inasmuch as it exhibits itself as a constant quality, again becomes a criterion of mutable vitality, and the author wishes nothing more than that time may be granted him to develop the results of his observations on this subject more fully. Here they would not be in their place. Relation to general physics. 737. The state in which general physics now is appears again particularly favourable to our labours, for natural philosophy, owing to indefatigable and variously directed research, has generally attained such eminence that it appears not impossible to refer a boundless empiricism to one centre. 738. Without referring to subjects which are too far removed from our own province, we observe that the formulae under which the elementary appearances of nature are expressed altogether tend in this direction, and it is easy to see that through this correspondence of expression a correspondence in meaning will necessarily be soon arrived at. 739. True observers of nature, however they may differ in opinion in other respects, will agree that all which presents itself as appearance, all that we meet with as phenomenon, must either indicate an original division which is capable of union, or an original unity which admits of division, and that the phenomenon will present itself accordingly. To divide the united, to unite the divided, is the life of nature. This is the eternal systole and diastole, the eternal collapsion and expansion, the inspiration and expiration of the world in which we live and move. 740. It is hardly necessary to observe that what we here express as number and restrict to dualism is to be understood in a higher sense. The appearance of a third, a fourth order of facts progressively developing themselves is to be similarly understood, but actual observation should, above all, be the basis of all these expressions. 741. Iron is known to us as a peculiar substance, different from other substances. In its ordinary state we look upon it as a mere material remarkable only on account of its fitness for various uses and applications. How little, however, is necessary to do away with the comparative insignificancy of this substance. A twofold power is called forth, which, while it tends again to a state of union, and, as it were, seeks itself, acquires a kind of magical relation with its like, and propagates this double property, which is in fact but a principle of reunion throughout all bodies of the same kind. We here first observe the mere substance, iron. We see the division that takes place in it propagate itself and disappear, and again easily become re-excited. This, according to our mode of thinking, is a primordial phenomenon in immanent relation with its idea, and which acknowledges nothing earthly beyond it. 742. Electricity is again peculiarly characterized. As a mere quality we are unacquainted with it. For us it is nothing, a zero, a mere point, which, however, dwells in all apparent existences, and at the same time is the point of origin whence, on the slightest stimulus, a double appearance presents itself, an appearance which only manifests itself to vanish. The conditions under which this manifestation is excited are infinitely varied, according to the nature of particular bodies. From the rudest mechanical friction of very different substances with one another, to the mere contiguity of two entirely similar bodies, the phenomenon is present and stirring, nay, striking and powerful, and so decided and specific, that when we employ the terms or formulae polarity, plus and minus, for north and south, for glass and resin, we do so justifiably and in conformity with nature. 743. This phenomenon, although it especially affects the surface, is yet by no means superficial. It influences the tendency or determination of material qualities, and connects itself in immediate cooperation with the important double phenomenon which takes place so universally in chemistry, oxidation and deoxidation. 744. To introduce and include the appearances of colour in this series, this circle of phenomena was the object of our labours. What we have not succeeded in, others will accomplish. We found a primordial vast contrast between light and darkness, which may be more generally expressed by light and its absence. We looked for the intermediate state, and sought by means of it to compose the visible world of light, shade, and colour. In the prosecution of this we employed various terms applicable to the development of the phenomena, terms which we adopted from the theories of magnetism, of electricity, and of chemistry. It was necessary, however, to extend this terminology, since we found ourselves in an abstract region and had to express more complicated relations. 745. If electricity and galvanism, in their general character, are distinguished as superior to the more limited exhibition of magnetic phenomena, it may be said that colour, although coming under similar laws, is still superior, for since it addresses itself to the noble sense of vision, its perfections are more generally displayed. Compare the varied effects which result from the augmentation of yellow and blue to red, from the combination of these two higher extremes to pure red, and the union of the two inferior extremes to green. What a far more varied scheme is apparent here than that in which magnetism and electricity are comprehended. These last phenomena may be said to be inferior again on another account, for though they penetrate and give life to the universe, they cannot address themselves to man in a higher sense in order to his employing them ascetically. The general, simple physical law must first be elevated and diversified itself in order to be available for elevated uses. 746. If the reader, in this spirit, recalls what has been stated by us throughout, generally and in detail, with regard to colour, he will himself pursue and unfold what has been here only lightly hinted at. He will augur well for science, technical processes, and art, if it should prove possible to rescue the attractive subject of the doctrine of colours from the atomic restriction and isolation in which it has been banished. In order to restore it to the general dynamic flow of life and action which the present age loves to recognise as nature, these considerations will press upon us more strongly when, in the historical portion, we shall have to speak of many an enterprising and intelligent man who failed to possess his contemporaries with his convictions. Relation to the theory of music. 747. Before we proceed to the moral associations of colour and the aesthetic influences arising from them, we have here to say a few words on its relation to melody. That a certain relation exists between the two has been always felt. This is proved by the frequent comparisons we meet with, sometimes as passing allusions, sometimes as circumstantial parallels. The error which writers have fallen into in trying to establish this analogy we would thus define. 748. Colour and sound do not admit of being directly compared together in any way, but both are referable to a higher formula, both are derivable, although each for itself, from this higher law. They are like two rivers which have their source in one and the same mountain, but subsequently pursue their way under totally different conditions, in two totally different regions, so that throughout the whole course of both no 2 points can be compared. Both are general, elementary effects, acting according to the general law of separation and tendency to union, of undulation and oscillation, yet acting thus in wholly different provinces, in different modes, on different elementary mediums, for different senses. 749. Could some investigator rightly adopt the method in which we have connected the doctrine of colours with natural philosophy generally, and happily supply what has escaped or been missed by us? The theory of sound, we are persuaded, might be perfectly connected with general physics. At present it stands, as it were, isolated within the circle of science. 750. It is true it would be an undertaking of the greatest difficulty to do away with the positive character which we are now accustomed to attribute to music, a character resulting from the achievements of practical skill, from accidental, mathematical, aesthetical influences, and to substitute for all this a merely physical inquiry tending to resolve the science into its first elements. Yet, considering the point at which science and art are now arrived, considering the many excellent preparatory investigations that have been made relative to this subject, we may, perhaps, still see it accomplished. Concluding observations on terminology. 751. We never sufficiently reflect that a language, strictly speaking, can only be symbolical and figurative, that it can never express things directly, but only, as it were, reflectedly. This is especially the case in speaking of qualities which are only imperfectly presented to observation, which might rather be called powers than objects, and which are ever in movement throughout nature. They are not to be arrested, and yet we find it necessary to describe them. Hence we look for all kinds of formulae in order, figuratively at least, to define them. 752. Metaphysical formulae have breadth as well as depth, but on this very account they require a corresponding import. The danger here is vagueness. Mathematical expressions may in many cases be very conveniently and happily employed, but there is always an inflexibility in them, and we presently feel their inadequacy, for even in elementary cases we are very soon conscious of an incommensurable idea. They are, besides, only intelligible to those who are especially conversant in the sciences to which such formulae are appropriated. The terms of the science of mechanics are more addressed to the ordinary mind, but they are ordinary in other senses, and always have something unpolished. They destroy the inward life to offer from without an insufficient substitute for it. The formulae of the corpuscular theories are nearly allied to the last. Through them the mutable becomes rigid, description and expression uncouth, while again moral terms, which undoubtedly can express nicer relations, have the effect of mere symbols in the end, and are in danger of being lost in a play of wit. 753. If, however, a writer could use all these modes of description and expression with perfect command, and thus give forth the results of his observations on the phenomena of nature in a diversified language, if he could preserve himself from predilections, still embodying a lively meaning in as animated an expression, we might look for much instruction communicated in the most agreeable of forms. 754. Yet how difficult it is to avoid substituting the sign for the thing, how difficult to keep the essential quality still living before us, and not to kill it with the word. With all this, we are exposed in modern times to a still greater danger by adopting expressions and terminologies from all branches of knowledge and science to embody our views of simple nature. Astronomy, cosmology, geology, natural history, nay, religion and mysticism, are called in aid, and how often do we not find a general idea in an elementary state rather hidden and obscured than elucidated and brought nearer to us by the employment of terms, the application of which is strictly specific and secondary. We are quite aware of the necessity which led to the introduction and general adoption of such a language. We also know that it has become in a certain sense indispensable, but it is only a moderate, unpretending recourse to it, with an internal conviction of its fitness, that can recommend it. 755. After all, the most desirable principle would be that writers should borrow the expressions employed to describe the details of a given province of investigation from the province itself, treating the simplest phenomenon as an elementary formula, and deriving and developing the more complicated designations from this. 756. The necessity and suitableness of such a conventional language where the elementary sign expresses the appearance itself has been duly appreciated by extending, for instance, the application of the term polarity, which is borrowed from the magnet to electricity, etc. The plus and minus, which may be substituted for this, have found as suitable an application to many phenomena. Even the musician, probably without troubling himself about these other departments, has been naturally led to express the leading difference in the modes of melody by major and minor. 757. For ourselves, we have long wished to introduce the term polarity into the doctrine of colours. With what right and in what sense the present work may show. Perhaps we may hereafter find room to connect the elementary phenomena together according to our mode, by a similar use of symbolic terms, terms which must at all times convey the directly corresponding idea. We shall thus render more explicit what has been here only alluded to generally, and perhaps too vaguely expressed. End of section 37.
Section 38 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in May 2017. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 38. Part 6. Effect of color with reference to moral associations. 758. Since color occupies so important a place in the series of elementary phenomena, filling as it does the limited circle assigned to it with fullest variety, we shall not be surprised to find that its effects are at all times decided and significant, and that they are immediately associated with the emotions of the mind. We shall not be surprised to find that these appearances presented singly are specific, that in combination they may produce an harmonious, characteristic, often even an inharmonious effect on the eye, by means of which they act on the mind, producing this impression in their most general elementary character, without relation to the nature or form of the object on whose surface they are apparent. Hence, color considered as an element of art may be made subservient to the highest aesthetical ends. 759. People experience a great delight in color, generally. The eye requires it as much as it requires light. We have only to remember the refreshing sensation we experience, if on a cloudy day the sun illumines a single portion of the scene before us, and displays its colors. That healing powers were ascribed to colored gems may have arisen from the experience of this indefinable pleasure. 760. The colors which we see on objects are not qualities entirely strange to the eye. The organ is not thus merely habituated to the impression. No, it is always predisposed to produce color of itself, and experiences a sensation of delight if something analogous to its own nature is offered to it from without, if its susceptibility is distinctly determined towards a given state. 761. From some of our earlier observations we can conclude that general impressions produced by single colors cannot be changed, that they act specifically and must produce definite, specific states in the living organ. 762. They likewise produce a corresponding influence on the mind. Experience teaches us that particular colors excite particular states of feeling. It is related of a witty Frenchman, Il prétendoit que son ton de conversation avec madame ait changé depuis qu'elle avoit changé en cramoisi le meuble de son cabinet, qui était bleu. 763. In order to experience these influences completely, the eye should be entirely surrounded with one color. We should be in a room of one color, or look through a colored glass. We are then identified with the hue. It attunes the eye and mind in mere unison with itself. 764. The colors on the plus side are yellow, red-yellow, orange, yellow-red, minium, cinnabar. The feelings they excite are quick, lively, aspiring. Yellow. 765. This is the color nearest the light. It appears on the slightest mitigation of light, whether by semi-transparent mediums or faint reflection from white surfaces. In prismatic experiments it extends itself alone and widely in the light space, and while the two poles remain separated from each other, before it mixes with blue to produce green, it is to be seen in its utmost purity and beauty. How the chemical yellow develops itself in and upon the white has been circumstantially described in its proper place. 766. In its highest purity it always carries with it the nature of brightness, and has a serene, gay, softly exciting character. 767. In this state, applied to dress, hangings, carpeting, etc., it is agreeable. Gold in its perfectly unmixed state, especially when the effect of polish is superadded, gives us a new and high idea of this color. In like manner, a strong yellow, as it appears on satin, has a magnificent and noble effect. 768. We find from experience, again, that yellow excites a warm and agreeable impression. Hence, in painting, it belongs to the illumined and emphatic side. 769. This impression of warmth may be experienced in a very lively manner if we look at a landscape through a yellow glass, particularly on a grey winter's day. The eye is gladdened, the heart expanded and cheered, a glow seems at once to breathe towards us. 770. If, however, this color in its pure and bright state is agreeable and gladdening, and in its utmost power is serene and noble, it is, on the other hand, extremely liable to contamination, and produces a very disagreeable effect if it is sullied, or in some degree tends to the minus side. Thus the color of sulphur, which inclines to green, has a something unpleasant in it. 771. When a yellow color is communicated to dull and coarse surfaces, such as common cloth, felt, or the like, on which it does not appear with full energy, the disagreeable effect alluded to is apparent. By a slight and scarcely perceptible change, the beautiful impression of fire and gold is transformed into one not undeserving the epithet foul, and the color of honor and joy reversed to that of ignominy and aversion. To this impression the yellow hats of bankrupts and the yellow circles on the mantles of Jews may have owed their origin. Red-yellow. 772. As no color can be considered as stationary, so we can very easily augment yellow into reddish by condensing or darkening it. The color increases in energy, and appears in red-yellow more powerful and splendid. 773. All that we have said of yellow is applicable here in a higher degree. The red-yellow gives an impression of warmth and gladness, since it represents the hue of the intenser glow of fire, and of the milder radiance of the setting sun. Hence it is agreeable around us, and again, as clothing, in greater or less degrees is cheerful and magnificent. A slight tendency to red immediately gives a new character to yellow, and while the English and Germans content themselves with bright pale yellow colors in leather, the French, as Castel has remarked, prefer a yellow enhanced to red. Indeed, in general, everything in color is agreeable to them which belongs to the active side. Yellow red. 774. As pure yellow passes very easily to red yellow, so the deepening of this last to yellow red is not to be arrested. The agreeable, cheerful sensation which red yellow excites increases to an intolerably powerful impression in bright yellow red. 775. The active side is here in its highest energy, and it is not to be wondered at that impetuous, robust, uneducated men should be especially pleased with this color. Among savage nations the inclination for it has been universally remarked, and when children, left to themselves, begin to use tints, they never spare vermilion and minium. 776. In looking steadfastly at a perfectly yellow-red surface, the color seems actually to penetrate the organ. It produces an extreme excitement, and still acts thus when somewhat darkened. A yellow-red cloth disturbs and enrages animals. I have known men of education to whom its effect was intolerable if they chanced to see a person dressed in a scarlet cloak on a grey, cloudy day. 777. The colors on the minus side are blue, and blue-red. They produce a restless, susceptible, anxious impression. Blue. 778. As yellow is always accompanied with light, so it may be said that blue still brings a principle of darkness with it. 779. This color has a peculiar and almost indescribable effect on the eye. As a hue it is powerful, but it is on the negative side, and in its highest purity is, as it were, a stimulating negation. Its appearance, then, is a kind of contradiction between excitement and repose. 780. As the upper sky and distant mountains appear blue, so a blue surface seems to retire from us. 781. But as we readily follow an agreeable object that flies from us, so we love to contemplate blue, not because it advances to us, but because it draws us after it. Blue gives us an impression of cold, and thus again reminds us of shade. We have before spoken of its affinity with black. 783. Rooms which are hung with pure blue appear in some degree larger, but at the same time empty and cold. 784. The appearance of objects seen through a blue glass is gloomy and melancholy. 785. When blue partakes in some degree of the plus side, the effect is not disagreeable. Sea green is rather a pleasing color. Red-blue. 786. We found yellow very soon tending to the intense state, and we observed the same progression in blue. 787. Blue deepens very mildly into red, and thus acquires a somewhat active character, although it is on the passive side. Its exciting power is, however, of a very different kind from that of red-yellow. It may be said to disturb rather than enliven. 788. As augmentation itself is not to be arrested, so we feel an inclination to follow the progress of the color, not, however, as in the case of the red-yellow, to see it still increase in the active sense, but to find a point to rest in. 789. In a very attenuated state, this color is known to us under the name of lilac, but even in this degree it has a something lively without gladness. 790. This unquiet feeling increases as the hue progresses, and it may be safely assumed that a carpet of a perfectly pure deep blue red would be intolerable. On this account, when it is used for dress, ribbons, or other ornaments, it is employed in a very attenuated and light state, and thus displays its character as above defined, in a peculiarly attractive manner. 798. As the higher dignitaries of the Church have appropriated this unquiet color to themselves, we may venture to say that it unceasingly aspires to the cardinal's red through the restless degrees of a still impatient progression. Red. 792. We are here to forget everything that borders on yellow or blue. We are to imagine an absolutely pure red, like fine carmine suffered to dry on white porcelain. We have called this color purpur by way of distinction, although we are quite aware that the purple of the ancients inclined more to blue. 793. Whoever is acquainted with the prismatic origin of red will not think it paradoxical if we assert that this color partly actu, partly potentia, includes all the other colors. 794. We have remarked a constant progress or augmentation in yellow and blue, and seen what impressions were produced by the various states. Hence it may naturally be inferred that now, in the junction of the deepened extremes, a feeling of satisfaction must succeed, and thus, in physical phenomena, this highest of all appearances of color arises from the junction of two contrasted extremes which have gradually prepared themselves for a union. 795. As a pigment, on the other hand, it presents itself to us already formed, and is most perfect as a hue in cochineal, a substance which, however, by chemical action may be made to tend to the plus or the minus side, and may be considered to have attained the central point in the best carmine. 796. The effect of this color is as peculiar as its nature. It conveys an impression of gravity and dignity, and at the same time of grace and attractiveness. The first in its dark deep state, the latter in its light attenuated tint, and thus the dignity of age and the amiableness of youth may adorn itself with degrees of the same hue. 797. History relates many instances of the jealousy of sovereigns with regard to the quality of red. Surrounding accompaniments of this color have always a grave and magnificent effect. 798. The red glass exhibits a bright landscape in so dreadful a hue as to inspire sentiments of awe. 799. Kermes and cochineal, the two materials chiefly employed in dyeing to produce this color, incline more or less to the plus or minus state, and may be made to pass and repass the culminating point by the action of acids and alkalis. It is to be observed that the French arrest their operations on the active side, as is proved by the French scarlet, which inclines to yellow. The Italians, on the other hand, remain on the passive side, for their scarlet has a tinge of blue. 800. By means of a similar alkaline treatment, the so-called crimson is produced, a color which the French must be particularly prejudiced against, since they employ the expressions sot en cramoisi, méchant en cramoisi, to mark the extreme of the silly and the reprehensible. Green. 801. If yellow and blue, which we consider as the most fundamental and simple colors, are united as they first appear, in the state of their action, the color which we will call green is the result. 802. The eye experiences a distinctly grateful impression from this color. If the two elementary colors are mixed in perfect equality, so that neither predominates, the eye and the mind repose on the result of this junction as upon a simple color. The beholder has neither the wish nor the power to imagine a state beyond it. Hence, for rooms to live in constantly, the green color is most generally selected. End of section 38. Section 39 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in April 2017. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 39. Completeness and Harmony. 803. We have hitherto assumed, for the sake of clearer explanation, that the eye can be compelled to assimilate or identify itself with a single color, but this can only be possible for an instant. 804. For when we find ourselves surrounded by a given color which excites its corresponding sensation on the eye, and compels us by its presence to remain in a state identical with it, this state is soon found to be forced, and the organ unwillingly remains in it. 805. When the eye sees a color, it is immediately excited, and it is its nature, spontaneously and of necessity, at once to produce another, which with the original color comprehends the whole chromatic scale. A single color excites, by a specific sensation, the tendency to universality. 806. To experience this completeness, to satisfy itself, the eye seeks for a colorless space next every hue in order to produce the complemental hue upon it. 807. In this resides the fundamental law of all harmony of colors, of which every one may convince himself by making himself accurately acquainted with the experiments which we have described in the chapter on the physiological colors. 808. If, again, the entire scale is presented to the eye externally, the impression is gladdening, since the result of its own operation is presented to it in reality. We turn our attention, therefore, in the first place, to this harmonious juxtaposition. 809. As a very simple means of comprehending the principle of this, the reader has only to imagine a movable diametrical index in the colorific circle. The index, as it revolves round the whole circle, indicates at its two extremes the complemental colors, which, after all, may be reduced to three contrasts. 810. Yellow demands red-blue, blue demands red-yellow, red demands green, and contrariwise. 811. In proportion as one end of the supposed index deviates from the central intensity of the colors, arranged as they are in the natural order, so the opposite end changes its place in the contrasted gradation, and by such a simple contrivance the complemental colors may be indicated at any given point. A chromatic circle might be made for this purpose, not confined, like our own, to the leading colors, but exhibiting them with their transitions in an unbroken series. This would not be without its use, for we are here considering a very important point which deserves all our attention. 812. We before stated that the eye could be in some degree pathologically affected by being long confined to a single color; that, again, definite moral impressions were thus produced, at one time lively and aspiring, at another susceptible and anxious, now exalted to grand associations, now reduced to ordinary ones. We now observe that the demand for completeness, which is inherent in the organ, frees us from this restraint. The eye believes itself by producing the opposite of the single color forced upon it, and thus attains the entire impression which is so satisfactory to it. 813. Simple, therefore, as these strictly harmonious contrasts are, as presented to us in the narrow circle, the hint is important,
that nature tends to emancipate the sense from confined impressions by suggesting and producing the whole, and that in this instance we have a natural phenomenon immediately applicable to aesthetic purposes. 814. While, therefore, we may assert that the chromatic scale, as given by us, produces an agreeable impression by its ingredient hues, we may here remark that those have been mistaken who have hitherto adduced the rainbow as an example of the entire scale, for the chief color, pure red, is deficient in it, and cannot be produced, since in this phenomenon, as well as in the ordinary prismatic series, the yellow red and blue red cannot attain to a union. 815. Nature perhaps exhibits no general phenomenon where the scale is in complete combination. By artificial experiments such an appearance may be produced in its perfect splendor. The mode, however, in which the entire series is connected in a circle is rendered most intelligible by tints on paper, till after much experience and practice, aided by due susceptibility of the organ, we become penetrated with the idea of this harmony, and feel it present in our minds. 816. Besides these pure, harmonious, self-developed combinations, which always carry the conditions of completeness with them, there are others which may be arbitrarily produced, and which may be most easily described by observing that they are to be found in the colorific circle, not by diameters, but by chords, in such a manner that an intermediate color is passed over. 817. We call these combinations characteristic, because they have all a certain significancy, and tend to excite a definite impression, an impression, however, which does not altogether satisfy, inasmuch as every characteristic quality of necessity presents itself only as a part of a whole, with which it has a relation, but into which it cannot be resolved. 818. As we are acquainted with the impressions produced by the colors singly as well as in their harmonious relations, we may at once conclude that the character of the arbitrary combinations will be very different from each other as regards their significancy. We proceed to review them separately. Yellow and blue. 819. This is the simplest of such combinations. It may be said that it contains too little, for since every trace of red is wanting in it, it is defective as compared with the whole scale. In this view it may be called poor, and as the two contrasting elements are in their lowest state, may be said to be ordinary. Yet it is recommended by its proximity to green, in short, by containing the ingredients of an ultimate state. Yellow and red. 820. This is a somewhat preponderating combination, but it has a serene and magnificent effect. The two extremes of the active side are seen together without conveying any idea of progression from one to the other. As the result of their combination in pigments is yellow-red, so they, in some degree, represent this color. Blue and red. 821. The two ends of the passive side, with the excess of the upper end of the active side. The effect of this juxtaposition approaches that of the blue-red produced by their union. Yellow-red and blue-red. 822. These, when placed together, as the deepened extremes of both sides, have something exciting, elevated. They give us a presentiment of red, which in physical experiments is produced by their union. 823. These four combinations have also the common quality of producing the intermediate color of our colorific circle by their union, a union which actually takes place if they are opposed to each other in small quantities and seen from a distance. A surface covered with narrow blue and yellow stripes appears green at a certain distance. 824. If, again, the eye sees blue and yellow next each other, it finds itself in a peculiar disposition to produce green without accomplishing it, while it neither experiences a satisfactory sensation in contemplating the detached colors, nor an impression of completeness in the two. 825. Thus it will be seen that it was not without reason we called these combinations characteristic, the more so since the character of each combination must have a relation to that of the single colors of which it consists. Combinations non-characteristic. 826. We now turn our attention to the last kind of combinations. These are easily found in the circle. They are indicated by shorter chords, for in this case we do not pass over an entire intermediate color, but only the transition from one to the other. 827. These combinations may justly be called non-characteristic, inasmuch as the colors are too nearly alike for their impression to be significant. Yet most of these recommend themselves to a certain degree, since they indicate a progressive state, though its relations can hardly be appreciable. 828. Thus yellow and yellow-red, yellow-red and red, blue and blue-red, blue-red and red, represent the nearest degrees of augmentation and culmination, and in certain relations as to quantity may produce no unpleasant effect. 829. The juxtaposition of yellow and green has always something ordinary, but in a cheerful sense. Blue and green, on the other hand, is ordinary in a repulsive sense. Our good forefathers called these last fool's colors. Relation of the combinations to light and dark. 830. These combinations may be very much varied by making both colors light or both dark, or one light and the other dark, in which modifications, however, all that has been found true in a general sense is applicable to each particular case. With regard to the infinite variety thus produced, we merely observe 831. The colors of the active side placed next to black gain in energy, those of the passive side lose. The active conjoined with white and brightness lose in strength, the passive gain in cheerfulness. Red and green with black appear dark and grave, with white they appear gay. 832. To this we may add that all colors may be more or less broken or neutralized, may to a certain degree be rendered nameless, and thus combined partly together and partly with pure colors, but although the relations may thus be varied to infinity, still all that is applicable with regard to the pure colors will be applicable in these cases. Considerations derived from the evidence of experience and history. 833. The principles of the harmony of colors having been thus far defined, it may not be irrelevant to review what has been adduced in connection with experience and historical examples. 834. The principles in question have been derived from the constitution of our nature and the constant relations which are found to obtain in chromatic phenomena. In experience we find much that is in conformity with these principles, and much that is opposed to them. 835. Men in a state of nature, uncivilized nations, children, have a great fondness for colors in their utmost brightness, and especially for yellow-red. They are also pleased with the motley. By this expression we understand the juxtaposition of vivid colors without an harmonious balance. But if this balance is observed, through instinct or accident, an agreeable effect may be produced. I remember a Hessian officer returned from America, who had painted his face with the positive colors in the manner of the Indians. A kind of completeness or due balance was thus produced, the effect of which was not disagreeable. 836. The inhabitants of the south of Europe make use of very brilliant colors for their dresses. The circumstance of their procuring silk stuffs at a cheap rate is favorable to this propensity. The women especially, with their bright-colored bodices and ribbons, are always in harmony with the scenery, since they cannot possibly surpass the splendor of the sky and landscape. 837. The history of dyeing teaches us that certain technical conveniences and advantages have had great influence on the costume of nations. We find that the Germans wear blue very generally because it is a permanent color in cloth. So in many districts all the country people wear green twill, because that material takes a green dye well. If a traveler were to pay attention to these circumstances, he might collect some amusing and curious facts. 838. Colors, as connected with particular frames of mind, are again a consequence of peculiar character and circumstances. Lively nations, the French for instance, love intense colors, especially on the active side. Sedate nations, like the English and Germans, wear straw-colored or leather-colored yellow accompanied with dark blue. Nations aiming at dignity of appearance, the Spaniards and Italians for instance, suffer the red color of their mantles to incline to the passive side. 839. In dress we associate the character of the color with the character of the person. We may thus observe the relation of colors singly and in combination to the color of the complexion, age, and station. 840. The female sex in youth is attached to rose color and sea green, in age to violet and dark green. The fair-haired prefer violet as opposed to light yellow, the brunettes blue as opposed to yellow-red, and on all good grounds. The Roman emperors were extremely jealous with regard to their purple. The robe of the Chinese emperor is orange embroidered with red, his attendants and the ministers of religion wear citron yellow. 841. People of refinement have a disinclination to colors. This may be owing partly to weakness of sight, partly to the uncertainty of taste, which readily takes refuge in absolute negation. Women now appear almost universally in white, and men in black. 842. An observation, very generally applicable, may not be out of place here, namely that man, desirous as he is of being distinguished, is quite as willing to be lost among his fellows. 843. Black was intended to remind the Venetian noblemen of republican equality. 844. To what degree the cloudy sky of northern climates may have gradually banished color may also admit of explanation. 845. The scale of positive colors is obviously soon exhausted. On the other hand, the neutral, subdued, so-called fashionable colors present infinitely varying degrees and shades, most of which are not unpleasing. 846. It is also to be remarked that ladies, in wearing positive colors, are in danger of making a complexion which may not be very bright still less so, and thus to preserve a due balance with such brilliant accompaniments, they are induced to heighten their complexions artificially. 847. An amusing inquiry might be made which would lead to a critique of uniforms, liveries, cockades, and other distinctions, according to the principles above hinted at. It might be observed, generally, that such dresses and insignia should not be composed of harmonious colors. Uniforms should be characteristic and dignified. Liveries might be ordinary and striking to the eye. Examples both good and bad would not be wanting, since the scale of colors usually employed for such purposes is limited, and its varieties have been often enough tried. End of section 39. Section 40 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in March 2017. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 40. Aesthetic Influence. 848. From the moral associations connected with the appearance of colors, single or combined, their aesthetic influence may now be deduced for the artist. We shall touch the most essential points to be attended to, after first considering the general condition of pictorial representation, light and shade, with which the appearance of color is immediately connected. Chiaroscuro. 849. We apply the term chiaroscuro, hell-dunkel, to the appearance of material objects when the mere effect produced on them by light and shade is considered. 850. In a narrower sense, a mass of shadow lighted by reflexes is often thus designated, but we here use the expression in its first and more general sense. 851. The separation of light and dark from all appearance of color is possible and necessary. The artist will solve the mystery of imitation sooner by first considering light and dark independently of color, and making himself acquainted with it in its whole extent. 852. Chiaroscuro exhibits the substance as substance, inasmuch as light and shade inform us as to degrees of density. 853. We have here to consider the highest light, the middle tint, and the shadow, and in the last the shadow of the object itself, the shadow it casts on other objects, and the illuminated shadow or reflection. 851. The globe is well adapted for the general exemplification of the nature of chiaroscuro, but it is not altogether sufficient. The softened unity of such complete rotundity tends to the vapory, and in order to serve as a principle for effects of art, it should be composed of plane surfaces, so as to define the gradations more. 855. The Italians call this manner il piazzoso. In German it might be called das Flächenhafte. If, therefore, the sphere is a perfect example of natural chiaroscuro, a polygon would exhibit the artist-like treatment in which all kinds of lights, half-lights, shadows, and reflections would be appreciable. 856. The bunch of grapes is recognized as a good example of a picturesque completeness in chiaroscuro, the more so as it is fitted, from its form, to represent a principal group, but it is only available for the master who can see in it what he has the power of producing. 857. In order to make the first idea intelligible to the beginner, for it is difficult to consider it abstractedly even in a polygon, we may take a cube, the three sides of which that are seen represent the light, the middle tint, and the shadow in distinct order. 858. To proceed again to the chiaroscuro of a more complicated figure, we might select the example of an open book, which presents a greater diversity. 859. We find the antique statues of the best time treated very much with reference to these effects. The parts intended to receive the light are wrought with simplicity. The portion originally in shade is, on the other hand, in more distinct surfaces to make them susceptible of a variety of reflections. Here the example of the polygon will be remembered. 860. The pictures of Herculaneum and the Aldobrandini marriage are examples of antique painting in the same style. 861. Modern examples may be found in single figures by Raphael, in entire works by Correggio, and also by the Flemish masters, especially Rubens. Tendency to color. 862. A picture in black and white seldom makes its appearance. Some works of Polidoro are examples of this kind of art. Such works, inasmuch as they can attain form and keeping, are estimable, but they have little attraction for the eye, since their very existence supposes a violent abstraction. 863. If the artist abandons himself to his feeling, color presently announces itself. Black no sooner inclines to blue than the eye demands yellow, which the artist instinctively modifies, and introduces partly pure in the light, partly reddened and subdued as brown in the reflexes, thus enlivening the whole. 864. All kinds of camailleux, or color on similar color, end in the introduction either of a complemental contrast or some variety of hue. Thus, Polidoro in his black and white frescoes sometimes introduced a yellow vase or something of the kind. 865. In general, it may be observed that men have at all times instinctively striven after color in the practice of the art. We need only observe daily how soon amateurs proceed from colorless to colored materials. Paolo Uccello painted colored landscapes to colorless figures. 866. Even the sculpture of the ancients could not be exempt from the influence of this propensity. The Egyptians painted their bas-reliefs. Statues had eyes of colored stones. Porphyry draperies were added to marble heads and extremities, and variegated stalactites were used for the pedestals of busts. The Jesuits did not fail to compose the statue of their Saint Luigi in Rome in this manner, and the most modern sculpture distinguishes the flesh from the drapery by staining the latter. Keeping. 867. If linear perspective displays the gradation of objects in their apparent size as affected by distance, aerial perspective shows us their gradation in greater or less distinctness, as affected by the same cause. 868. Although from the nature of the organ of sight we cannot see distant objects so distinctly as nearer ones, yet aerial perspective is grounded strictly on the important fact that all mediums called transparent are in some degree dim. 869. The atmosphere is thus always, more or less, semi-transparent. This quality is remarkable in southern climates, even when the barometer is high, the weather dry, and the sky cloudless, for a very pronounced gradation is observable between objects but little removed from each other. 870. The appearance on a large scale is known to everyone. The painter, however, sees or believes he sees the gradation in the slightest varieties of distance. He exemplifies it practically by making a distinction, for instance, in the features of a face according to their relative position as regards the plane of the picture. The direction of the light is attended to in like manner. This is considered to produce a gradation from side to side, while keeping has reference to depth, to the comparative distinctness of near and distant things. 871. In proceeding to consider this subject, we assume that the painter is generally acquainted with our sketch of the theory of colors, and that he has made himself well acquainted with certain chapters and rubrics which especially concern him. He will thus be enabled to make use of theory as well as practice in recognizing the principles of effect in nature, and in employing the means of art. Color in general nature. 872. The first indication of color announces itself in nature together with the gradations of aerial perspective, for aerial perspective is intimately connected with the doctrine of semi-transparent mediums. We see the sky, distant objects, and even comparatively near shadows, blue. At the same moment, the illuminating and illuminated objects appear yellow, gradually deepening to red. In many cases, the physiological suggestion of contrasts comes into the account, and an entirely colorless landscape, by means of these assisting and counteracting tendencies, appears to our eyes completely colored. 873. Local colors are composed of the general elementary colors, but these are determined or specified according to the properties of substances and surfaces on which they appear. This specification is infinite. 874. Thus, there is at once a great difference between silk and wool similarly dyed. Every kind of preparation and texture produces corresponding modifications. Roughness, smoothness, polish, all are to be considered. 875. It is therefore one of the pernicious prejudices of art that the skilful painter must never attend to the material of draperies, but always represent, as it were, only abstract folds. Is not all characteristic variety thus done away with, and is the portrait of Leo X less excellent because velvet, satin, and moreen are imitated in their relative effect? 876. In the productions of nature, colors appear more or less modified, specified, even individualized. This may be readily observed in minerals and plants, in the feathers of birds and the skins of beasts. 877. The chief art of the painter is always to imitate the actual appearance of the definite hue, doing away with the recollection of the elementary ingredients of color. This difficulty is in no instance greater than the imitation of the surface of the human figure. 878. The color of flesh, as a whole, belongs to the active side, yet the bluish of the passive side mingles with it. The color is altogether removed from the elementary state and neutralized by organization. 879. To bring the coloring of general nature into harmony with the coloring of a given object will perhaps be more attainable for the judicious artist after the consideration of what has been pointed out in the foregoing theory. For the most fancifully beautiful and varied appearances may still be made true to the principles of nature. Characteristic coloring. 880. The combination of colored objects, as well as the color of their ground, should depend on considerations which the artist pre-establishes for himself. Here a reference to the effect of colors, singly or combined, on the feelings, is especially necessary. On this account the painter should possess himself with the idea of the general dualism, as well as of particular contrasts, not forgetting what has been adverted to with regard to the qualities of colors. 881. The characteristic in color may be comprehended under three leading rubrics, which we here define as the powerful, the soft, and the splendid. 882. The first is produced by the preponderance of the active side, the second by that of the passive side, and the third by completeness, by the exhibition of the whole chromatic scale in due balance. 883. The powerful impression is attained by yellow, yellow-red, and red, which last color is to be arrested on the plus side. But little violet and blue, still less green, are admissible. The soft effect is produced by blue, violet, and red, which in this case is arrested on the minus side, a moderate addition of yellow and yellow-red, but much green may be admitted. 884. If it is proposed to produce both these effects in their full significancy, the complemental colors may be excluded to a minimum, and only so much of them may be suffered to appear as is indispensable to convey an impression of completeness. End of section 40. Section 41 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avayi in March 2017. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 41. Harmonious Coloring. 885. Although the two characteristic divisions as above defined may in some sense be also called harmonious, the harmonious effect, properly so called, only takes place when all the colors are exhibited together in due balance. 886. In this way the splendid as well as the agreeable may be produced. Both of these, however, have of necessity a certain generalized effect, and in this sense may be considered the reverse of the characteristic. 887. This is the reason why the coloring of most modern painters is without character, for, while they follow their general instinctive feeling only, the last result of such a tendency must be mere completeness. This they more or less attain, but thus at the same time neglect the characteristic impression which the subject may demand. 888. But if the principles before alluded to are kept in view, it must be apparent that a distinct style of color may be adopted on safe grounds for every subject. The application requires, it is true, infinite modifications, which can only succeed in the hands of genius. Genuine tone. 889. If the word tone, or rather tune, is to be still borrowed in future from music and applied to coloring, it might be used in a better sense than heretofore. 890. For it would not be unreasonable to compare a painting of powerful effect with a piece of music in a sharp key, a painting of soft effect with a piece of music in a flat key, while other equivalents might be found for the modifications of these two leading modes. False tone. 891. The word tone has been hitherto understood to mean a veil of a particular color spread over the whole picture. It was generally yellow, for the painter instinctively pushed the effect towards the powerful side. 892. If we look at a picture through a yellow glass, it will appear in this tone. It is worthwhile to make this experiment again and again, in order to observe what takes place in such an operation. It is a sort of artificial light, deepening and at the same time darkening the plus side and neutralizing the minus side. 893. This spurious tone is produced instinctively through uncertainty as to the means of attaining a genuine effect, so that instead of completeness, monotony is the result. Weak coloring. 894. It is owing to the same uncertainty that the colors are sometimes so much broken as to have the effect of the grey camailleux, the handling being at the same time as delicate as possible. 895. The harmonious contrasts are often found to be very happily felt in such pictures, but without spirit, owing to a dread of the motley. The motley. 896. A picture may easily become partly colored or motley when the colors are placed next each other in their full force, as it were only mechanically and according to uncertain impressions. 897. If, on the other hand, weak colors are combined, even although they may be dissonant, the effect, as a matter of course, is not striking. The uncertainty of the artist is communicated to the spectator, who, on his side, can neither praise nor censure. 898. It is also important to observe that the colors may be disposed rightly in themselves, but that a work may still appear motley if they are falsely arranged in relation to light and shade. 899. This may the more easily occur as light and shade are already defined in the drawing, and are, as it were, comprehended in it, while the color still remains open to selection. Dread of theory. 900. A dread of, nay, a decided aversion for all theoretical views respecting color and everything belonging to it has been hitherto found to exist among painters, a prejudice for which, after all, they were not to be blamed, for what has been hitherto called theory was groundless, vacillating, and akin to empiricism. We hope that our labors may tend to diminish this prejudice, and stimulate the artist practically to prove and embody the principles that have been explained. Ultimate aim. 901. But without a comprehensive view of the whole of our theory, the ultimate object will not be attained. Let the artist penetrate himself with all that we have stated. It is only by means of harmonious relations in light and shade, in keeping, in true and characteristic coloring, that a picture can be considered complete, in the sense we have now learned to attach to the term. Grounds. 902. It was the practice of the earlier artists to paint on light grounds. This ground consisted of gypsum and was thickly spread on linen or panel, and then levigated. After the outline was drawn, the subject was washed in with a blackish or brownish color. Pictures prepared in this manner for coloring are still in existence, by Leonardo da Vinci and Fra Bartolomeo. There are also several by Guido. 903. When the artist proceeded to color, and had to represent white draperies, he sometimes suffered the ground to remain untouched. Titian did this latterly when he had attained the greatest certainty in practice, and could accomplish much with little labor. The whitish ground was left as a middle tint, the shadows painted in, and the highlights touched on. 904. In the process of coloring, the preparation merely washed, as it were, underneath, was always effective. A drapery, for example, was painted with a transparent color. The white ground shone through it and gave the color life, so the parts previously prepared for shadows exhibited the color subdued, without being mixed or sullied. 905. This method had many advantages, for the painter had a light ground for the light portions of his work, and a dark ground for the shadowed portions. The whole picture was prepared, the artist could work with thin colors in the shadows, and had always an internal light to give value to his tints. In our own time, painting in watercolors depends on the same principles. 906. Indeed, a light ground is now generally employed in oil painting, because middle tints are thus found to be more transparent, and are in some degrees enlivened by a bright ground. The shadows, again, do not so easily become black. 907. It was the practice for a time to paint on dark grounds. Tintoret probably introduced them. Titian's best pictures are not painted on a dark ground. 908. The ground in question was red-brown, and when the subject was drawn upon it, the strongest shadows were laid in, the colors of the lights impasted very thickly in the bright parts, and scumbled towards the shadows, so that the dark ground appeared through the thin color as a middle tint. Effect was attained in finishing by frequently going over the bright parts and touching on the highlights. 909. If this method especially recommended itself in practice on account of the rapidity it allowed of, yet it had pernicious consequences. The strong ground increased and became darker, and the light colors losing their brightness by degrees, gave the shadowed portions more and more preponderance. The middle tints became darker and darker, and the shadows at last quite obscure. The strongly impasted lights alone remained bright, and we now see only light spots on the painting. The pictures of the Bolognese school and of Caravaggio afford sufficient examples of these results. 910. We may here in conclusion observe that glazing derives its effect from treating the prepared color underneath as a light ground. By this operation colors may have the effect of being mixed to the eye, may be enhanced, and may acquire what is called tone, but they thus necessarily become darker. Pigments. 911. We receive these from the hands of the chemist and the investigator of nature. Much has been recorded respecting coloring substances, which is familiar to all by means of the press. But such directions require to be revised from time to time. The master meanwhile communicates his experience in these matters to his scholar, and artists generally to each other. Those pigments which according to their nature are the most permanent are naturally much sought after, but the mode of employing them also contributes much to the duration of a picture. The fewest possible coloring materials are to be employed, and the simplest methods of using them cannot be sufficiently recommended. 913. For from the multitude of pigments coloring has suffered much. Every pigment has its peculiar nature as regards its effect on the eye. Besides this, it has its peculiar quality, requiring a corresponding technical method in its application. The former circumstance is a reason why harmony is more difficult of attainment with many materials than with few. The latter why chemical action and reaction may take place among the coloring substances. 914. We may refer, besides, to some false tendencies which the artists suffer themselves to be led away with. Painters are always looking for new coloring substances, and believe, when such a substance is discovered, that they have made an advance in the art. They have a great curiosity to know the practical methods of the old masters, and lose much time in the search. Towards the end of the last century we were thus long tormented with wax painting. Others turn their attention to the discovery of new methods, through which nothing new is accomplished, for, after all, it is the feeling of the artist only that informs every kind of technical process. End of section 41. Section 42 of Theory of Colors. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in March 2017. Theory of Colors by Johann Wolfgang von Goethe. Translated by Charles Eastlake. Section 42. Allegorical, symbolical, mystical application of color. 915. It has been circumstantially shown above that every color produces a distinct impression on the mind, and thus addresses at once the eye and feelings. Hence it follows that color may be employed for certain moral and aesthetic ends. 916. Such an application, coinciding entirely with nature, might be called symbolical, since the color would be employed in conformity with its effect, and would at once express its meaning. If, for example, pure red were assumed to designate majesty, there can be no doubt that this would be admitted to be a just and expressive symbol. All this has been already sufficiently entered into. 917. Another application is nearly allied to this. It might be called the allegorical application. In this there is more of accident and caprice, inasmuch as the meaning of the sign must be first communicated to us before we know what it is to signify. What idea, for instance, is attached to the green color which has been appropriated to hope? 918. That, lastly, color may have a mystical allusion may be readily surmised, for since every diagram in which the variety of colors may be represented points to those primordial relations which belong both to nature and the organ of vision, there can be no doubt that these may be made use of as a language, in cases where it is proposed to express similar primordial relations which do not present themselves to the senses in so powerful and varied a manner. The mathematician extols the value and applicability of the triangle. The triangle is revered by the mystic. Much admits of being expressed in it by diagrams, and, among other things, the law of the phenomena of colors. In this case, indeed, we presently arrive at the ancient mysterious hexagon. 919. When the distinction of yellow and blue is duly comprehended, and especially the augmentation into red, by means of which the opposite qualities tend towards each other and become united in a third, then, certainly, an especially mysterious interpretation will suggest itself, since a spiritual meaning may be connected with these facts. And when we find the two separate principles producing green on the one hand and red in the intenser state, we can hardly refrain from thinking in the first case on the earthly, in the last on the heavenly generation of the Elohim. 920. But we shall do better not to expose ourselves, in conclusion, to the suspicion of enthusiasm, since, if our doctrine of colours finds favour, applications and allusions, allegorical, symbolical, and mystical, will not fail to be made, in conformity with the spirit of the age. Concluding observations. In reviewing this labour, which has occupied me long, and which at last I give but as a sketch, I am reminded of a wish once expressed by a careful writer, who observed that he would gladly see his works printed at once as he conceived them, in order then to go to the task with a fresh eye, since everything defected presents itself to us more obviously in print than even in the cleanest manuscript. This feeling may be imagined to be stronger in my case, since I had not even an opportunity of going through a fair transcript of my work before its publication, these pages having been put together at a time when a quiet, collected state of mind was out of the question. Some of the explanations I was desirous of giving are to be found in the introduction, but in the portion of my work to be devoted to the history of the doctrine of colours, I hope to give a more detailed account of my investigations and the vicissitudes they underwent. One inquiry, however, may not be out of place here, the consideration, namely, of the question, what can a man accomplish who cannot devote his whole life to scientific pursuits? What can he perform as a temporary guest on an estate not his own, for the advantage of the proprietor? When we consider art in its higher character, we might wish that masters only had to do with it, that scholars should be trained by the severest study, that amateurs might feel themselves happy in reverentially approaching its precincts. For a work of art should be the effusion of genius, the artist should evoke its substance and form from his inmost being, treat his materials with sovereign command, and make use of external influences only to accomplish his powers. But if the professor in this case has many reasons for respecting the dilettante, the man of science has every motive to be still more indulgent, since the amateur here is capable of contributing what may be satisfactory and useful. The sciences depend much more on experiment than art, and for mere experiment many a votary is qualified. Scientific results are arrived at by many means, and cannot dispense with many hands, many heads. Science may be communicated, the treasury may be inherited, and what is acquired by one may be appropriated by many. Hence, no one, perhaps, ought to be reluctant to offer his contributions. How much do we not owe to accident, to mere practice, to momentary observation? All who are endowed only with habits of attention, women, children, are capable of communicating striking and true remarks. In science it cannot therefore be required that he who endeavours to furnish something in its aid should devote his whole life to it, should survey and investigate it in all its extent, for this, in most cases, would be a severe condition even for the initiated. But if we look through the history of science in general, especially the history of physics, we shall find that many important acquisitions have been made by single inquirers, in single departments, and very often by unprofessional observers. To whatever direction a man may be determined by inclination or accident, whatever class of phenomena especially strike him, excite his interest, fix his attention, and occupy him, the result will still be for the advantage of science, for every new relation that comes to light, every new mode of investigation, even the imperfect attempt, even error itself, is available. It may stimulate other observers, and is never without its use as influencing future inquiry. With this feeling the author himself may look back without regret on his endeavours. From this consideration he can derive some encouragement for the prosecution of the remainder of his task, and although not satisfied with the result of his efforts, yet reassured by the sincerity of his intentions, he ventures to recommend his past and future labours to the interest of his contemporaries and posterity. Multi per transibunt et augebitur scientia. End of section 42. End of Theory of Colours by Johann Wolfgang von Goethe. Translated by Charles Eastlake.